We are live. Okay, we are back. Hopefully, many of you are coming back with me now. Welcome, everyone. We have just begun hour 9 of our live stream. Welcome back if you're staying with us. Welcome if you're just joining. My name is Claire, and I'm back here with the cloud again. So hopefully everyone remembers that from last year, or you can appreciate it now. Okay, so we have just done our first stream reset. Very exciting, a little bit of a hassle. As you see, we're now in hour 9, and we're going to have an excellent lineup of talks. I will be your host for the next 2 hours. So let's get started. Before we bring on our next speaker, I want to remind us all why we are here tonight. And that is to celebrate and appreciate the amazing science that we do in the weather and climate community. Our science is made possible by, in very large part, the tax dollars that all of us pay every year. Our funding comes from federal resources, through federal labs, through federal agencies, and has supported such amazing science over the many decades. The US has been a world leader in developing weather and climate science for many years. The first computerized weather forecasts were built in the US. The first computer models of climate change and the impacts of carbon dioxide and air pollution were done in the United States. And a lot of that funding is currently under threat. So we need all of you to speak up, let your voice be heard, call or write to your representatives. We have a lot of information on our website to assist you, help make that possible. And we just would love for your enthusiasm that we have been seeing in the chat all day to make it to the ears of our representatives in Congress. So please go ahead and do that. Without further ado, I would like to invite the first speaker in my session onto the stage. We're going to be hearing from Duncan Watson-Parris, who is an excellent friend and collaborator of mine. So I'm very excited to hear what he has to say. He is a professor at Scripps Institute of Oceanography and University of California, San Diego. And he's going to be talking about a very exciting project that is really at the cutting edge of all of our AI world, bringing that into our climate modeling land. So please take it away, Duncan.
Fantastic. Thank you so much, Claire. Thanks for hosting, and thanks for all the great work everyone's doing behind the scenes to make this possible. So I'm excited to talk about this new work. As you say, it's at the cutting edge. It's kind of hot off the press. We just had this paper accepted in GMD, so I'm excited to share it here today. I'm going to be talking about JAX GCM, which is a differentiable intermediate complexity atmospheric model, and I'll break down a little bit what that means as we go. And this work is made possible by the NSF, and I'll talk a little bit about that at the end. So for those of you who maybe aren't familiar, the way we model climate, and this may have been introduced once or twice already through the live stream, but bears repeating, to model the Earth over the multiple timescales that we're interested in the climate, climate scientists break the world up into these little grid boxes, these little chunks that we use to move the atmosphere around the world and understand how that evolves through time. And each of those little boxes is about something like 100 kilometers across. And so everything inside those boxes, we have to parameterize. We have to come up with a representation that encodes the behaviors of the clouds and the turbulence and the radiation and the mixing. And that's where a lot of the complexity in climate modeling lies. So you might see these impressive videos of clouds and moisture moving around, but a lot of the detail is in what we call the physics here of how these different multi-scale processes interact. And traditionally, we write those models in Fortran, which is great because it can be compiled to perform very efficiently on large, high-performance computers such as the Director machine run by the NSF in Wyoming. But there are a lot of optimizations that are hardware specific that makes it very hard to port the code. So you don't need to understand what this is, but this is kind of a representative snapshot of some of that Fortran code from a model, which I won't name, which has these kind of directives in here that you have to put in order to tell the compiler, whether to unroll this loop or not, do whatever optimization it needs to do, depending on whether it's going to be run on a CPU or a GPU or whatever else. We also, what we'd really like to be able to do, so some of these variables in here are parameters. They're things in the model. So gravity we know pretty well, but some of these other variables, we might not know exactly how to, what the value of them should be in the model. And we'd like to be able to update those parameters to make the model look more like the real world. There's a lot of complexity and a lot of different knobs we can turn in the model. And so traditionally, this has required doing something called gradient-free optimization. And this is something I had spent a lot of my time doing. So we build parameter ensembles where basically we create an ensemble of model simulations with different parameters. We fit an emulator across those different configurations, and that enables us to do this inference, this task of asking which model configuration looks most like the observations. And this is hard. It's expensive, it's time consuming, and it doesn't really scale to fully coupled models. So we've done this for atmospheric models, but not so much for ocean, atmosphere, ice, and land models. And so this kind of motivated development of JCM, which is the first fully differentiable physical atmospheric model written in Python. And it's written in a numerical library called JAX, which Google developed for all its machine learning architecture. So it has some nice properties in that it keeps the gradients through all the operations that it performs. So the magic of training a neural network is that all those little nonlinear operations, the gradients of those are tracked so that we can backpropagate through that network in order to find the update to these parameters to make the model look like the data. And so we can harness that capability, so-called auto-differentiability, for our physical models. And that enables calibration, but also sensitivity analysis. And I'll talk a little bit about that later on. We designed the models so that you can switch in these different physics schemes. So different physics schemes might be more complex or more simple, and that's very straightforward to do. And because of this architecture, this JAX library and the Python language that we're writing it in, we can very easily run this model on those big HPC CPUs that I described before, but also GPUs, which have become much more available, and less so recently with the demand for GPUs for machine learning. But a lot of the big computers now come with a lot of GPUs, so we can harness those, as well as novel architectures such as the TPUs that Google are developing. And so we've developed the validation against the original Fortran. So we're pretty happy it's producing a similar climate with these new capabilities and with these new performant capabilities. So we are already now, so that as I say, is published, and we had in that paper a simple physical scheme based on the original Speedy model, some of you might be familiar with, which is it has convection, it has clouds, but it's very, very simple. But we are already now developing more complex physical representations of those processes in this model, and also developing a coupled version of the model, so JAX ESM. And this is already now starting to be able to couple an atmosphere from JCM together with an ocean model, and perhaps even a slab ocean model, in very simple Python that you can just configure and hit run, and it will run this for days and years with the gradients all the way through that, so that we can so that we can calibrate these coupled simulations. There are a couple of other models that we're leaning on. So the Veros ocean model developed in Copenhagen, as pre-existing JAX ocean library, as well as the Differland model from a team in Colombia. And this approach is really going to enable us to I think, realized this vision from a paper from Tapio Schneider et al. In 2017 of a system that is continuously learning from observations, driving high resolution simulations, which it can then also learn from, and combining observations, high resolution simulations with these global models. As I say, traditionally and kind of even fairly recently, the ways to calibrate those have been through ensemble approaches, but these gradients give us the opportunity to just directly step to the optimal solution. And we're making very early strides in this direction. I just wanted to kind of tease some early results in that regard. So one of my one of the students who have been working on this is a student of Matthew Morsfeld here in UCSD. Rebecca Genie is working on gradient-based calibration. So I don't want to go too much into the maths here, but we define a loss, which is essentially a difference between the observations and our model. And our model is a function of some parameters U. And those parameters include things like the brightness of shallow clouds, some humidity thresholds in the convection scheme, and so on. And we're targeting in this first instance just a specific configuration of JCM. So we pretend that these are the observations, and we just see if we can recapture the parameters that we use to generate those. And some of the variables we include are things like shortwave radiation, longwave radiation, humidity, things that in principle we can go and measure. And what's interesting, if we look at these loss values, is that we get very smooth, convex losses across these different parameter ranges. At short timescales, these look very, very smooth, and we can expect to just optimize directly to the true value, which is 0.5 in this case. Over medium timescales, chaos takes over, and the different weather trajectories diverge, which means that for any given parameter combination, you might get different observable outcomes, and makes it a bit harder for the optimizer to work. But then as we go to longer timescales, we recover this smooth convex loss that we can just directly optimize. And we've shown a couple of nice examples. This actually made it into the paper, this plot of two-parameter optimization, just with a simple optimization scheme using the jax.grad built-in optimizers to step directly to the true configuration, in this case, that we knew a priori of the model. The other thing I'm excited in, I'm going to skip this slide, but one of the key things that we do in climate science is ask what is the sensitivity of the atmosphere or an atmospheric process to a change in boundary conditions. The climate is all about boundary conditions. It's about changing either the top of atmosphere boundary by perturbing the energy balance, or perhaps looking at the atmospheric component and perturbing the sea surface temperature to understand how the atmosphere adjusts to warming or other perturbations. And we can, with the gradients in JAX, we can actually directly probe those sensitivities. We can ask for you don't need to know what this is, but if you know the terminology, this is a Jacobian vector product, and this is telling us exactly what the sensitivity of these different atmospheric fields, in this case it's convective precipitation and large-scale precipitation, to a perturbation in the sea surface temperature after over different timescales. And we can, as I say, get these directly from the model without having to do large ensembles. I briefly want to talk about how we did this. So this originally started nearly 2 years ago now, and we used ChatGPT in its early incarnations to support conversion of specific Fortran routines into this JAX library. And we're pretty heavily now, and that actually then turned into a little hackathon which we ran. But we're pretty heavily now using Claude Code and these other tools that have got very good to routinely convert these Fortran codes into Python. And I would say now we're at the point where we're generating thousands of, I've come up with this kind of metric of like lines of usefully generated lines of code. So if I type in a prompt, how many lines can I expect to get back that are actually useful for the task at hand? And just purely empirically, over the last even couple of months, we're now getting thousands of lines of code. Given some Fortran code, say, here's parameterization, bring this into the JAX framework. And so, the idea that we might be able to convert some of these very large, very complex models like CSM, which are, of order 1 million lines of code, isn't quite the kind of, fantasy that it used to be. I think it's actually very much in the realms of possibility and brings all these tools to those full complexity models. Yeah, I'm excited about where this will build. If you're interested, the code's all open source. Feel free to just jump on the repo, check out the code, pip install it, raise an issue if you find anything amiss. I briefly wanted to talk about the funding for this. So this is supported by an NSF Career Award that I won a year or so ago, 2 years ago, which didn't envisage JAX at all. It's focused on perturbations and adjustments to the atmosphere in response to aerosol. But the flexibility and pretty much the unique flexibility of these NSF awards means that we can follow the science and follow the new developments and really harness the best kind of science, which is just curiosity driven. And it would be a terrible shame if these new changes are allowed to erode that scientific freedom. It's one of the reasons I came to the US, as in Claire's nice intro. It's a world-leading country in terms of its development and historical developments in weather and climate. And so hopefully we can convince our peers and colleagues and leaders to respect that and properly fund these scientific endeavors. Thank you.
Thank you so much, Duncan. That was amazing. And there has been a lot of excitement and questions, curiosity in the chat about how Excellent. You're using AI. So I want to bring up this first question. What got you into AI for climate modeling? Was it anything specific? Have you always had an interest? How did you get started?
Good question. So actually, I had a interest kind of pretty much as soon as I was a postdoc in atmospheric sciences. My PhD was in something different, and then I was a consultant for a few years doing kind of data analytics and stuff for a consultancy. And so I kind of was already aware of these tools and where they were headed. And so when I came to the climate sciences, I was, I guess, a little bit ahead of the curve. But I'm really excited about how we can use them to better harness the observational data that we have and how we can improve our models. I don't see these tools supplanting what we have, but really accelerating and improving the things we do.
Yeah, definitely. And then I guess you kind of talked about using these tools in two different ways. One of them is kind of how we're the types of tools we have to do the science, but the other one is how we're actually doing it day to day. And so there was a question about that. How do you expect the role of coding by hand to change as LLMs become more popular? So how are we really implementing it?
It's a great question. So as someone who, is a pretty experienced coder, I have written thousands of lines of code over the last 6 months. I haven't written. I've produced thousands of lines of code, and it's fascinating. It's kind of it's addictive, but I know how to read it, and I can spot the mistakes, and I can say, "Oh no, don't do it like that. Do it like this," and that'll end up better. I think the real question for me at the moment, particularly as a professor at a school where we teach data science and programming, is like, what do we teach? How do we, encode those skills of this is the high level architecture that you're aiming for, and these are the reasons we want those things, and how do we teach those skills to be critical of the things that these LLMs are producing if it's so easy just to ask the LLM in the first place? And it's it's a real challenge. If anyone has any ideas, I'm all ears.
How do you become an expert before you've been a novice? It's a great challenge we have. Maybe we can end just with your quick thoughts. LEB had a question. I would love to learn about coding, but I get so discouraged. What advice do you have for people who are watching the stream who want to learn how to code?
Now is a great time to get coding. I know, if you have the motivation to learn, these tools are actually fantastic for helping you to learn. In the classroom where you have, you just need to get that next exam in or the next assignment in to get your grade, it's very easy to just reach for the tool and have it do it for you. But equally, if you are curious, you can have Claude or any of these other tools, have it test you, have it say, hey, teach me how to code. What are the main structures? What are the things I should look for? Go build a side project. Vibe coding gets a bad rep, but for building, just based on curiosity, it can be pretty fun. And I think you'll learn just by doing.
I love that. I think that's something that we all love about our job as scientists, is that we just do it sometimes just for fun.
Right.
And it's a lot of fun.
Absolutely.
Okay. Thank you so much, Duncan.
Fantastic.
You have a great
night.
Thank
you so much, Claire. You too. Bye.
So before we bring on our next speaker, I'm just going to remind us all why we're here. Thank you so much for those of you just joining, and for those of you who've been watching. We're now in hour 9, and we are here to get excited to learn more about weather and climate science. I am wearing the cloud again. I came all the way out here to California. I'm out here at a science conference, spending my whole day talking about measuring things from space and with Argo floats. So put your Argo love in the chat. But we are here tonight on this live stream to remember just how important federal funding has been for the development of our science in the United States. The United States is a world leader in weather and climate science. We have been for many decades, and we want to continue to be, but that leadership is reliant on having a stable and secure and continuous funding source. The administration has currently proposed, again, huge budget cuts for the fiscal year 2027 that are being considered right now by Congress. So if you love the science that you've been seeing and you want it to continue and be supported, please let your voice be heard to your representatives. The proposed cuts would slash the budgets at places like the National Science Foundation, the NSF, that was supporting the work you just heard about from Duncan, slash the budgets at NASA, at NOAA, would completely eliminate all of the NOAA research laboratories, including the one that I used to work at, the one that won the Nobel Prize for creating our first climate model in the world. And these are just irreplaceable. These kind of cuts are devastating to our field. They're going to destroy the careers of many of our young scientists who are just getting started or who are still coming down the pipeline in school. And that is why we want you to all make your voice heard to your representatives. Please go to our website, wclivestream.com/act. You can find more information on how to call or write to your representatives today. And I think without further ado, we will now bring on our next speaker, who is an early career climate scientist. Please welcome Sean Cohen to the stage. I had the pleasure of getting to know Sean when he was still a Ph.D. student, and he has been doing many wonderful things in the years since. Today, he's going to share some of his very cool recent work about how CO2 cools the stratosphere. So we're talking way up high, no clouds up there, but a very special, important place. Take it away, Sean.
Thanks so much for that very sweet introduction, Claire. Like Claire said, my name is Sean Cohen, and I'm going to be talking to you today about some of the work that my colleagues, Robert Pincus, Lorenzo Polvani, and I have been doing at the Lamont Doherty Earth Observatory on stratospheric cooling. But before I do, I just want to give another really big thank you to the folks hosting this live stream. And even more importantly, a big thank you to the organizations that were out here to support: the NSF, NOAA, NCAR, NASA. All of them really make this work and the other work that you've seen here possible. So just as an introduction to everything, when the amount of carbon dioxide in the atmosphere increases, the stratosphere as a whole actually cools. This is a result that goes all the way back to some of the early work of Minabe and Weatherald in their early climate models from the 1960s, where they saw that as they increased the amount of CO2 in their climate model, while the surface warmed, the stratosphere actually cooled, and it cooled quite a bit more than the surface warmed. Since then, this has been a prediction that's been robustly borne out in both observations of the stratosphere and then also in more comprehensive climate simulations since then, such as the CMIP6 suite of modern climate models. And so the reason why this occurs in the first place actually comes from the way that CO2 modifies Earth's energy balance. CO2 is fundamentally a greenhouse gas, which means that as it increases, it's going to replace the infrared light coming from the surface with infrared light coming from higher up in the atmosphere, most notably the stratosphere. One relatively intuitive way that you can understand this is through a metaphor that I'm sure many of you have heard before, which is the idea of putting on a coat. Or in the case here of this infrared photo of a dog, you can think about the fur on the dog as replacing the dog's skin temperature, which is much warmer, with its fur temperature, which is much cooler. And in the process of replacing that warm temperature with that cooler temperature, it reduces the overall emission and then allows the dog as a whole to warm up, much in the same way that the surface warms when atmospheric carbon dioxide increases. However, if you look locally at the stratosphere, increases in CO2 actually increase infrared emission, which means that locally you'll see the opposite effect, which is cooling. So why does any of this matter? At the end of the day, most of us and most living things in general live in the lowest level of the atmosphere down here in the troposphere. Why would we care about what's going on way up in the stratosphere? Well, for one, stratospheric cooling is actually one of the first ways that we knew that the surface warming that we were observing was due to CO2 and human-made impacts as opposed to something like sunlight. The reason being that if this surface warming were caused by sunlight, we wouldn't actually expect to see surface cooling at all, or stratospheric cooling. We would instead expect to see the stratosphere warm along with the surface. And so the fact that it cools tells us that the surface warming that we're observing is coming from CO2 and not from, for example, something like changes in sunlight. The other reason why stratospheric cooling matters is because it actually affects the overall warming that CO2 generates at the surface through impacting the energy imbalance that it creates at the top of the atmosphere. And functionally, what that means is that if you want to understand how much surface warming CO2 is going to cause for the things we care about down here near the surface, you first need to know how much CO2 will cool the stratosphere. And so you might be asking, if we can simulate and observe stratospheric cooling incredibly well, what's left to learn? This is a result that goes back, over 50 years now. What was the point of really looking at stratospheric cooling in the first place? And what me and my colleagues learned as we dug into the literature is that while this existing work exists to qualitatively explain stratospheric cooling, as of a couple years ago, we really lacked a quantitative theory for why CO2 cools the stratosphere in the first place. And what this meant is that some relatively fundamental questions about this process remained unanswered. Questions like, why does CO2 cool the stratosphere more aloft than it does below? And what sets the magnitude of this cooling? Why is it roughly 1 degree Celsius per decade that we observe and not, 100 times larger or 100 times smaller than that amount? And what we found is that one of the reasons for this lack of fundamental understanding actually came from one of the really wonderful things about our climate models, which is that they're quite complex. And this complexity is really great for things like predicting what's going to happen in the future. But the downside of this complexity is that oftentimes it steals clarity, meaning that it's harder to really get at the essence of what's going on with a particular phenomena. And so what we really wanted to do in our work was do the opposite, which was strip out the complexity, try and really make things simple, and really get at what you might call a minimum ingredient list that's needed to simulate stratospheric cooling so we could get at the essence of this phenomena. And what we found when we did this is primarily you need two ingredients. One of them is something we've already talked about, which is energy balance. So the stratosphere is in what's called radiative equilibrium, which means that infrared cooling by carbon dioxide, water vapor, and ozone is going to be balanced by heating by absorbed sunlight via ozone. And the other really important aspect or important ingredient is what you might call a spectral view. And by this, all that I mean is an understanding of the very different ways that CO2 absorbs light at different wavelengths in the infrared. And the reason why we care about this is because this is ultimately going to determine how much CO2 cools each level of the stratosphere. To get a more palpable understanding of what I'm talking about, I think it's helpful to look at, really how much CO2 absorbs at different wavelengths of light in the infrared. And so I have a plot of that right here, right now. You can see that, you have all these really messy spectral lines that CO2 creates. And the reason why this absorption matters is because this absorption is really just a proxy for emission level, where these wavelengths at the center of the CO2 band that are really absorbent are going to be the ones that are emitting high up in the atmosphere, in the stratosphere, whereas these wavelengths that are less absorbent, more at the edges of the band, are going to be the ones that are emitting further down near the surface, much like you can think of the thick fur or the thin fur in the parallel that we used with the dog. And so what we can use this for is to get a better sense of, how many wavelengths of light is CO2 emitting from at each level of the stratosphere. And the way that we can do that is actually quite simple. What we can do is bin these wavelengths by emission level. So really, we're just going to run across each emission level and just count how many dots we run into. And that's what's plotted here. And what you can see is that the number of wavelengths that you see at each emission level stays relatively constant low down in the atmosphere until you get further up and you approach the peak of the CO2 band, and the number of wavelengths really falls off to zero. And so we can parameterize this relationship relatively simply, and we can use that to get at what we're really interested in, which is how does this picture change when CO2 increases, because that's going to be ultimately what drives stratospheric cooling. And the answer to this is ultimately quite simple as well. Really, all that's going to happen is this curve is just going to shift up or down as the amount of CO2 in the atmosphere changes. So here I have plotted pretty much the same thing as you see here on the left, except that we're looking at different concentrations of CO2. So here in black, we have pre-industrial CO2 concentrations, and all we've done is we've quartered it and quadrupled it to get a sense of how does the number of wavelengths emitting in the IR and the CO2 band change at each altitude. And what we see is that as you increase the amount of CO2 in the atmosphere, the number of wavelengths in the CO2 band that emit from each pressure level is ultimately going to change. And more important than that, it's going to change to different extents depending on where in the stratosphere you're looking. So here, further down in the stratosphere, you actually don't see very much of a change at all, versus further up, you see a much larger change. And so, as you can expect, this is ultimately going to be what explains why the stratosphere cools more aloft than it does below, and ultimately going to be what explains its magnitude as well. To get a sense of this, we can look at the same quantity that we were looking at before, this number of emitting wavelengths. And now we're just looking at the change as you move from pre-industrial to doublings and quadruplings of CO2 and halvings and quarterings. And what you see when you look at this fractional change is that it looks very similar to the change in stratospheric temperature that you would expect. And more important than that, it really tells us that in order to simulate stratospheric cooling, at least to first order, really the only two things we need are an understanding of energy balance in the stratosphere and this spectral view that allows us to recreate some of the more complex behavior that we would see both in observations and in more comprehensive climate models. And so what are the looping things back to kind of the central takeaways? We know that increases in CO2 cool the stratosphere. we know that this cooling matters, not only because it's a fingerprint of human effects on climate, but also because it fundamentally impacts how much the surface is going to warm. And then we know that this cooling stems from two main ingredients. One is energy balance in the stratosphere, and the other is the different ways that CO2 interacts with light at different wavelengths in the infrared. And so if you want to learn more about this work, fundamentally these two main mechanisms that I was just talking about, you can read more about our work that we recently had published as of about a month ago. But more importantly, none of this work would have been possible without the funding and expertise that the organizations like NSF, NASA, NOAA, and NCAR provide. And so with that, I'll close things out and open things up for questions. Thank you very much.
Amazing. Thank you, Sean. So exciting. I have seen you present this work before, but it's always fun to hear it again. And I think our audience also enjoyed it. So if anyone has questions, please drop them into the chat for Sean. But Sean, I'm wondering if you can tell us maybe a bit about yourself, because we've heard about your awesome science. How did you first get interested in studying the climate?
That's a great question. So I feel like I backed into climate science in a little bit of a roundabout way, where in undergrad, I actually studied mechanical engineering. And some of my favorite courses in mechanical engineering, and this was a very unpopular opinion at the time, were thermodynamics and heat transfer and fluid dynamics. Those were some of the least popular classes amongst the mechanical engineers, but I just found them really fascinating. And when I was looking to go back to school after working as an engineer for a couple of years, I found that a lot of the coursework that I saw online for the folks studying climate science was really relatable, because in many ways, Earth's atmosphere is just a giant heat engine. And a lot of those same concepts that I really loved from mechanical engineering applied to Earth as well, just on much larger scales and in many more unique ways. And so it's been a really, really cool pivot to get to, study a lot of these questions that have more similarities to a lot of these other things that I studied before than I would have expected.
That is super cool. And it's always fun to make connections across disciplines and things that you don't expect to necessarily be similar. Okay, we've got a question here that is, how fast or how understood is the recovery time, the return of stratospheric cooling, if CO2 emissions slow down or stop?
Great question. So one of the really interesting things about stratospheric cooling is that it occurs on much faster timescales than the warming of the surface. The warming of the surface, as you might know, takes on the order of centuries in many cases, whereas stratospheric cooling really occurs on the order of days, weeks, months. And so what we saw in our work is that not only does the stratosphere respond quite quickly, but it's also, to again, first order, largely decoupled from what's going on in the troposphere and at the surface. And so the stratospheric temperature we found ends up being primarily just a function of the CO2 in the atmosphere. And as you change that CO2 concentration, the stratospheric cooling adjusts pretty quickly.
Yeah, that's so true. That's why we call it the fast adjustment sometimes.
Exactly. Yeah.
Okay, I'll throw up this one last question that just came in. It's from someone that we might know. Who's your favorite person that you've ever worked with on a paper?
And I believe this is coming from Robert's daughter here, Layla. So this is really sweet. So this was, really a continuation of a lot of the work that I got to do with Robert, Layla's father, during my PhD on the spectroscopy related to rainfall. And this was a really great continuation of that, where we got to work with Lorenzo as well, and take a pivot from the troposphere into his world, which was the stratosphere. And so it's been a really, really fun collaboration getting to work with the two of them. And yeah, I think it's as Layla, as you know, it is your dad is a really special person, and he's been a phenomenal mentor to me, along with Lorenzo.
That's super sweet. Okay, well, actually, I lied. We have one more question. I think this one is super interesting, so I want to know the answer. Since we had some emissions reduction in 2020 during the COVID pandemic, did we see any changes in the stratosphere? Is it fast enough that we were able to observe that?
That is a really great question. I actually haven't looked into that. My gut response would be to say that yes. I mean, like we talked about, the prediction that I would make would be that those reductions would have shown up, but I haven't looked at that explicitly. So really that would be speculation. So that's a really great question. I should look into that.
I love that. Getting new research ideas from the
Yeah,
live stream.
absolutely.
Okay, thank you so much, Sean. You have a good night.
Thank you very much, Claire. Have a good one.
Okay, everyone. So we're well into hour 9. Before we move on to our next final speaker of this hour, I want to just remind us all what we are doing here. So if you are just joining us, welcome. If you've been here already, you've heard a bit of this spiel before, but we are here to get excited and learn more about weather and climate science and understand a bit about what has made it possible and what has made it possible in the United States for the past several decades has been really sustained support from the federal government through funding, through the amazing research laboratories that the federal government runs, and through funding that goes out to universities to support research that's happening in the universities. We are here because we want all of you to recognize the importance of that funding to support this science, and also to recognize what is happening right now in the current administration with the proposed budget cuts and the implementation and proposal of new rules that would hamper the production of this amazing science that we are so privileged to have had over the past several decades. We have heard a bit today about the amazing resources at the National Center for Atmospheric Research, or NCAR. NCAR is one of these federal laboratories. They build what's called the Community Earth System Model. This is a tool, a climate model that can be used by anyone in the country. It's fully accessible. It's supported by a whole team, dozens of amazing scientists and engineers who build it and maintain it for the community to use. And NCAR is under threat. The administration is trying to actively dismantle the center. They're trying to cut its funding. They're trying to sell it for parts. And this is one of the big things that is at risk that we are out here advocating and sharing with you all about how amazing it is and how much we want to keep it. So if you feel inspired by the science that you've seen here today, and want it to continue for the next many decades, want to continue to support early career researchers like Sean, please go to w3livestream.com/act. We have instructions there on how you can call or write to your representatives and let your voice be heard about why you love and think that weather and climate science is so important and should be supported in the US. So now, without further ado, I would like to bring on our next speaker, who is Professor Henri Drake. You might remember Henri from last year. We're so excited to have him back. And Henri is an assistant professor at the University of California, Irvine. We're getting the whole California crew at this late hour of the night. And he's going to be sharing his talk today on a mathematical model of climate change. Henri does a lot of really interesting stuff, so I'm excited to hear about this one.
Thanks, Claire. Before I start, I want to say 3 things. So one, the work that I'm going to share today was funded by the National Science Foundation on a graduate research fellowship program, fellowship that I got in graduate school. So it's a bit of older work. I'm now like 6 years out of grad school, but my career I really owe to this fellowship. And this, I hope you'll find, is very creative work that is very different than a lot of the other research I do. And this kind of creative science would not be possible without the support of foundations like the National Science Foundation that is just there to fund our science. And their support hasn't ended there. And at this stage of my career as a professor, now my job is to raise money for the next generation. I currently have 2 pending grants at the National Science Foundation. Both of them would take on a PhD student. If they're not funded, I won't be able to probably take new PhD students. So that's the kind of thing we're talking about here. And just to tie into what Claire was just saying, both of these NSF grants that are pending that I applied for, both of them would make use of the NCAR computer resources and the climate models and ocean models that they support. And without that center, the research wouldn't be possible, even if it did get funded. Okay, so all that said, I'm going to talk today about climatemargot.jl. This is a model that I developed in grad school. It's what I think of as the simplest possible mathematical model of climate change. And I was really after 2 questions. One, how can we think about the optimal way to move forward in climate change? And then also, what do we do about the fact that reality is very much not optimal? And so how do we respond when something suboptimal happens to us? So this is some work I did with a very eclectic group of collaborators. These are all senior professors at MIT. And I can talk about that more in the Q&A as well. Okay, so what is Margot? So it starts with emissions. So this is an example of, let's say, a coal plant where we burn some fossil fuels and we emit some carbon dioxide at a rate Q into the atmosphere, which might be a function of time. And what we can do is we can not emit those. So we could use, for example, renewable energy resources instead of coal, and we would emit less emissions. So in this mathematical model, the baseline is that we emit Q, and we have the control to mitigate. And so we can either mitigate anywhere from 0 to 100%. If we mitigate 100%, this is 1 minus 1 times Q, that's 0. We have no emissions. Okay, so downstream of emissions, we have concentration. So when you emit carbon, it accumulates in the atmosphere. In general, about half of those emissions stay in the atmosphere for a really long time. The other half get taken up by the land, the forests and soils and ocean. But the rest accumulates, and it stays there for a long time, hundreds or thousands of years. So what can we do about that? Well, once it's in the atmosphere, we can't really mitigate anymore. But people have started talking about these carbon dioxide removal strategies where in this mathematical model, we just subtract it. In reality, this means, maybe fertilizing the oceans to grow a bunch of phytoplankton that take up carbon and sink to the bottom of the ocean. Or you engineer some machine to suck up all the carbon out of the atmosphere and store it underground. So you have mitigation, you have carbon dioxide removal, and whatever you're left with in the atmosphere, you have some concentration of greenhouse gases like CO2 being the dominant one. And then what that does is it messes with our radiative balance in the atmosphere. So we have sunlight coming in, it warms the planet up. The planet tries to cool down by sending radiation back to space. Unfortunately, greenhouse gases block some of that, send it back down, make it even warmer. It turns out that this effect, the amount of radiation that gets trapped, is actually a logarithmic function of carbon dioxide. And so it's a pretty simple mathematical function here. And what this radiative forcing does is it warms the planet. So what people have also started talking about is intervening in this radiative forcing. Instead of changing how much greenhouse gas there is, they say, oh, well, what if we put stuff in the atmosphere that just reflects some sunlight? So you can put some sulfates in the stratosphere, for example, and these tiny little droplets will reflect some of the sunlight and cool the planet down kind of directly. And so here I have that in a very simple way where you just scale up this parameter G from 0 to 100. 100 would be offsetting all of the greenhouse effect of added CO2 due to this solar radiation modification, also known as geoengineering. Okay, so let's say you've done all those things, you have some net radiative forcing. What does that do? Well, it raises the temperature. And there are 2 parts of this, or 3 parts. There is the temperature you had at the beginning, the fast response of temperature. So this is all the climate feedbacks. And then there's this slow response that has to do with the ocean. It's a more complicated formula, so I'm not showing it here, but this is a lot of what my research is about, is how the oceans take up heat. Okay, and so now we have this temperature. It's going to cause a whole bunch of different climate changes around the world. What can we do? Well, we can adapt to them. So typically, the way we think about temperatures affecting society in a simple way is that it causes some monetary damage. So this is like the amount of damage to GDP, for example. And it's just written as some function of temperature. And so the higher the temperature rises, the more damage that we'll do. Unfortunately, the economists think this is a quadratic function, meaning that if you double the temperature anomaly, so you go from 2 degrees to 4 degrees, that will quadruple the amount of damage. Okay, so this is what I think of as like the chain of climate change, how you go all the way from emissions to concentrations to forcing to temperature to damage. But really what we want to do is we want to do some kind of balance or cost-benefit analysis or optimization to figure out, well, what is the best combination of these strategies like mitigation, carbon dioxide removal, geoengineering, adaptation, given the costs of those things. And we can think about the costs in a very general way. That could be the actual cost of the technology or of the implementation. But then there also might be costs of side effects. For example, with geoengineering, it might be really cheap to take some planes up and put these sulfates in the stratosphere, but there might be some extra costs of side effects. Okay, so the point is that there are multiple different ways of reducing climate damage in principle, but none of them are free. So here's kind of how the model works. You give it some rules. So in this case, I want to minimize how much it costs to keep temperatures below some threshold. So that's what this complicated formula here shows. It's I want to minimize the cost of mitigation, carbon dioxide removal, geoengineering, and adaptation. It's an integrated cost, meaning that it's like over a long time horizon of the next 100 or 200 years. And I want to minimize all those costs while staying under, let's say, 1.5 degrees or 2 degrees. And so in this case, to stay under 2 degrees, we have to mitigate. If mitigation is the only thing we're doing, we'd have to mitigate about 85% of our emissions over the next century. So this is just kind of a simple visualization of how this optimization works. But now I'll kind of walk you through a short scenario. So here is what a typical run of the model looks like. So we start out here. Well, when I did the work, it was 2020. So the temperature anomaly from relative to pre-industrial was about 1.2 degrees C. And the no policy baselines is like the absolute worst case scenario. You burn all the fossil fuels, you just take off in a straight line, and you warm a ton by 2100. But here I put in a rule, which is that after 2100, the temperature cannot be more than 1.5 degrees above pre-industrial. So you can overshoot it a little bit in the sense that you can, in this case, we get all the way up to 1.6, but eventually it brings it back down to 1.5, and then it stays below 1.5 the whole time. And so this scenario in dark gray here, this is the most cost-effective way in this model of achieving that trajectory. The question I have is, when I do this optimal policy, right, this is the best case scenario. This is like, if you did all of the right things, what is the cheapest way you could meet your climate goals? But reality is more complicated. Oh, sorry, I forgot to mention this. And this is how we get there. So the top is the temperature. So this is how much it warms. And this is what you need to do to get there. So in this case, the optimal strategy is that you increase your mitigation to about 75% by 2050, meaning that relative to today, you would stop emitting about 75% of our current emissions. And then you would ramp that up all the way to 100 by 2080 or 2100. And then it drops down a little bit here, but that's because you've also turned on carbon dioxide removal. So you've started also sucking up some CO2. So you can be a little bit more relaxed about how much you stop emitting later on. Okay, so this is still the best case scenario. the question I had is, what happens if we don't do that? So we say, we know the best scenario is that we do this amount of mitigation and we suck up this amount of CO2, and that will give us this temperature. But what if we don't do that? What if we only actually mitigate 60% of what we said we did? So I frame this in terms of a shortfall of 40%. So we miss 40% of our mitigation and 40% of our emissions reductions. Well, then the temperature is going to go higher than what we originally thought. And actually, if you just do 40% of the entire mitigation, you get this line. This is the kind of trajectory that we're on now that we missed our original goal. So what I had the model do is I had it step forward and say, okay, suppose we're now decision makers in 2040. What is our new optimal trajectory? So I re-optimize, and now it tells me, well, the optimal thing now is to follow this purple line. So we can still bring the temperature back down by 2100. But if you look at where the purple line goes in these, it means we have to ramp up our ambition and get to 100% mitigation or net zero even faster by 2070. And we have to suck up about twice as much CO2 in order to do that. And so we can play the same game and we can say, okay, well, what if from 2040 to 2060, we also don't do what we said we were going to do? And so you can step forward like this, and this orange line gives you what the actual outcome is if you're always doing a shortfall of about 40% of what you wanted your policy goals to be. And so in this case, it's not too bad, as long as you keep correcting yourself and trying to follow the best. Even if you're not doing your best, you can still stabilize around 1.8 degrees C. So this exercise, when I first did it, gave me a lot of hope, which is that if we just course correct, even if we're not perfect every time we do a course correction, we can still stop things from getting to the worst case scenario. So I hope you found that interesting, and I'm happy to answer some questions.
Yay, thank you, Henri. That was so cool. I love that we are bridging from all the way from the economics into the climate science here. Please, if you have questions for Henri about any of the very large range of things he talked about just now, put them in the chat. I'll start off with a question that I had, which is, you were talking about doing this optimization with a specific goal in mind, like limiting warming to 1.5 degrees C. What if I don't care so much about the global mean temperature, but I want to know what we can do to limit the warming in a specific region, say like the Arctic, or where I live? How would I write that in their beautiful mathematical framework you've shown?
Yeah, that's a great question. So that's a funny question, because it happens that one of my collaborators here at UC Irvine built a model that kind of does just that. So once you add in temperature patterns, so you don't just have one number that you're trying to predict, it gets much more complicated, because now you have to account for the whole pattern of temperatures around the world. And it turns out that there's this mathematical framework called Green's functions, which lets you take some emissions and then you kind of wrap this Green's function around those emissions, and it gives you like a prediction of the temperature patterns all around the world. So the reason I would say using that approach as to running like a climate model or something is that these simple mathematical tools are really, really efficient, cost efficient. Like they run really fast. So I didn't show it here, but like you can do these calculations that I showed in this talk on a laptop in just a couple of seconds, because the model I built is so fast. So I think I would do something like that is really fast, but gives you an accurate prediction of temperature change, like in any location.
Super cool. Thank you. And maybe you can tell our viewers a little bit about kind of the scale that we're talking about when you're talking about the complexity of models. You said you could run this in just a few seconds. When we're talking about a model that we're running on the NCAR computers, what kind of scale is that? How much bigger is that?
Sure. So let's see, there's a lot of ways to quantify it, but I'll pick two. So one way you can quantify the complexity of model is just how many lines of code there are in the model, right? These are computer models, so they just are running tons of lines of code. This simple model I showed, I wrote myself in about a year, and it's maybe like 500 lines of code or something. Now, the model that I run on the NCAR supercomputer, that I haven't checked recently, but the whole thing, when you account for the atmosphere and the ocean and the sea ice and the aerosols and everything, all the bells and whistles, it's like got to be over 1 million lines of code. And so there's already a lot of complexity. So that's in terms of the complexity of the actual code, but then it's also just a really heavy calculation. So you need a supercomputer, which is basically just a ton of computer chips stacked together that are all talking to each other. And so you're running it on like tens of thousands of computers at once, essentially. Whereas like on my laptop, I have like 4 little CPUs, and that's all I need.
That's super helpful. Thank you so much. And you guys have a good night. For everyone who is watching us on the stream, we've made it to hour 10. So celebrate. Very exciting. I will be your host for the next hour. And before we move on to our next talk, I want to remind us all what we're doing here at the Weather and Climate live stream. So we're here to celebrate and learn about the amazing weather and climate science that we do in the US, and understand kind of how this science has been made possible over the decades. And that is through really amazing, sustained, supportive federal funding. This is money that comes from your tax dollars, my tax dollars, to support the science that is benefiting all of us, to make our weather forecasts when you want to know if you need an umbrella tomorrow, to help plan our city infrastructure when we need to know how big to build the dams or how tall to make the curbs for when we have flash floods, all those sorts of things. We need information about the future climate, things that are going to happen in the next 10, 20, 30 years. And that's why we connect all of these scales together, weather to climate, in this kind of continuous way. This science is done everywhere from universities, places like UC Irvine, where Henri is from. It's done at national research laboratories, NCAR, the NOAA research labs, NASA research labs, Department of Energy labs, that are doing all of this amazing work, building models and tools like the Community Earth System model, and running these supercomputer systems that we need to do these really intensive computational tasks. We had a question just now in the chat that I will take a moment to go and answer, which is, what kind of collaborations are needed to make such a complex model? How many experts do we need? And I'll just give you a taste from an example of the research lab that I used to work at, NOAA's Geophysical Fluid Dynamics Laboratory, or GFDL, the place that built the first climate model in the world. We heard a bit about that earlier this afternoon from my colleague Nader Giovanji. But at one of these modeling centers, we have dozens, up to about 100 people that are working at the lab. We need experts in all different sorts of processes, everything from clouds to how plants respire, things about the soil, the oceans, like Henri studies. We have tons of different scientists with domain expertise. We've got engineers, we've got software wizards, we've got the hardware wizards, we've got tons of people who are being trained at these sort of facilities, students, postdocs, who are building up the next generation of climate science. These labs are really an incubation place for our field, and they're under threat. So if you feel inspired by what you have heard today, you want to continue the sustained support for climate and weather science, please go and act, wclivestream.com/act. We have instructions and tips on how to call and write to your representatives, let your voice be heard. So please go ahead and do that and share this stream, share this link with all of your friends. So now we're going to move on, and I'm going to invite our next speaker onto the stage. We have Ross Salawitch from the University of Maryland. He's a professor of atmospheric science, and he's going to tell us today, I think building nicely on what we just heard from Henri, about the likelihood of limiting global warming to 2 degrees by the end of the century. and what sort of emissions reductions we need to make that happen. So I'm excited to hear this. Please take it away.
Thanks, Claire. I'll go quickly through the title slide. Let's see if I can advance. Well, let's see. There we go. Okay, a bit of publicity for a book that we wrote with a shout out to my colleagues, more colleagues named. The generous support of NASA, not only supporting our research, but supporting the open access fee. We're at 109K downloads and we're counting, or the website's counting. I'm not going to go through all the jargon. It's late at night, and I have a typo there already. But you all know what this all is. The one thing I'll say is when I get to the SSPs and RCPs, the most important thing is the number at the end is the watt per meter squared radiative forcing at the end of century. Speaking of radiative forcing, here's an update to the AR6 famous figure about radiative forcing of climate. Greenhouse gases warm, aerosols cool. What are we talking about? This is the work of Kevin Trenberth from NCAR, my colleague Rachel Pinker at University of Maryland, huge number of PhDs into all of these arrows. But the prior slide talks about the increase in this number as we add greenhouse gases to the atmosphere, offset somewhat by aerosols. So the issue that's going to motivate the rest of my talk is, of course, greenhouse gases, as everyone knows, warm. Here's an estimate of the uncertainty over this time period. Aerosols cool, suspended particulate matter, and most importantly, the amount of offset is quite uncertain, leading to a fairly substantial uncertainty in how much we've actually forced the climate system over time. So this is a figure from our book, Paris Climate Agreement, Beacon of Hope, where what we compare is for one of these future greenhouse gas scenarios, how much we warm due to the three big greenhouse gases, and oh my goodness, how much we might be offsetting the warming by. Now, one thing that's clear, the bottom panel comes from the work of Steve Smith and Tammy Bond, lots of PhDs behind all of this. One thing that's clear is that this masking of global warming by aerosols is going away due to public health. AR5, the N-1 IPCC report, had their best estimate of how much cooling we had being at this point. AR6, for some reason, went out further in time and said there's more cooling, more offsetting, and that's interesting. Lots of debate over this, what this all means. I just want to say that if we live in this world where we've masked very little warming, or we live in this world, these are vastly different worlds, and we don't know which of these worlds we live in. Let me explain. First off, we have a particle zoo. We know that sulfates, I tell my class, act as little mirrors reflecting sunlight. They cool. Black carbon in this figure is warming a lot, offsetting a lot of the sulfate cooling. And there's other aerosols that cool. So the net effect is here. And this is a figure from our book where we go into all this. So it's a particle zoo out there. But again, end of century, it's going down. The other conundrum we face is climate feedback. So I'm not going to explain what the units mean and all that. It's from AR6. Basically, we have water vapor and lapse rate together, provide feedback, surface albedo. As you melt ice, we get warmer, we reflect more sunlight. Clouds. We don't really know what clouds are doing. So I'm going to hark back to my past. When I was the age of most of you all, there was this famous singer named Joni Mitchell who used to sing about clouds. She's actually the one who said, pay paradise, put up a parking lot. Now I'm going to try to summon the spirit of Joni Mitchell. Everyone online say, Joni, Joni. Let's see if this works.
I really don't know clouds at all.
Okay, that's my wife, Shari, doing her Joni Mitchell. Thank you, Shari. And we don't know clouds at all. So here is a approach we take. Like the prior talk, we're using a reduced complexity climate model. In our model, we're doing attribution of when volcanoes go off, it cools. And so we've heard a lot about already today. We've heard a talk on AMOC, which was a great talk. We do ocean heat balance, sparing you equations. Here's Tim Canty, Laura McBride, Zeke Nichols, some of the collaborators we have. Take humans out. The warming's due to humans. You all know that. Here's the problem. We could live in a world where aerosols have masked very little global warming. If we live in that world, we get very small climate feedback. To fit the climate record very well, we go out at end of century. We're good if we could limit global warming to 3.4 watt per meter squared. We're good. In other words, we limit warming to 1.5 degrees. But we don't know if that's the world we live in. This is the AR5 best estimate of where we live in. Aerosols have masked a moderate amount of warming, in which case, even if we limit radiative forcing 3.4 watt per meter squared, we have stronger feedback. But we might live in this world where aerosols have masked a lot of global warming. I hope we don't live in that world, because if we live in that world, we can only fit the past climate record with really strong climate feedback. And in that case, we're in a world of hurt. And I have a lot of words down here that I'm not going to read in the interest of time, but glad the talk is being recorded. So what does my group do? We use our reduced complexity climate model to run hundreds of thousands of ensemble simulations of global mean surface temperature. Here I'm showing the colors are projected out to year 2100. Here are the various aerosol scenarios that we use. This axis is how much cooling aerosols have induced by 2019, the AR6 number. Here's climate feedback. And I only show results if we can fit the climate record well. We then weight our results by this curve, which is the AR6 best estimate of what the aerosols really offset. And notice for some of their estimates, we can't even fit the climate record well. This is a conundrum. We put this in our model and we project out to the end of century. Now, let me try to explain this plot. This is what we're trying to do now, is limit warming to 2 degrees, because sadly, we've kind of passed the 1.5 degree warming already. This is for 4.5 watt per meter squared warming by end of century. The blue colors here are how much will warm as a function of time, at least this much. So 100% in our model framework. Here's the upper limit. Our most optimal warming is in the middle. And this whole thing is driven by aerosols. The whole uncertainty is driven by aerosols. We run hundreds of thousands of ensembles and we look at the effect of aerosols. So in our model world, and here's the paper led by a Ph.D. now, who's a postdoc at Cornell. If we follow the 4.5 watt per meter squared scenario, we only have an 8% chance of staying below 2 degrees. We wouldn't want that if we're trying to achieve the Paris Climate Agreement. We turn CO2 over to get to 3.4 watt per meter squared radiative forcing, and this is CO2, and here's the watt per meter squared. We now have a 40% chance. In some sports, like baseball, if you hit bat 400, you're great, but this is climate, we like to do better. So let's go to basketball, free throw shooting, 85% free throw shooting, that's really good. If we can get on the 2.6 trajectory, we'll have an 85% chance of limiting warming to 2 degrees in this model framework, published. Great peer reviews of this paper. Thank you to the reviewers. And if we could somehow bend CO2 over, just bend it over to get all the way down here by end of century, we'd have a really good chance of limiting warming to 2 degrees. Now, of course, I'll never say 100% reality. There's this thing called committed warming. I have slides and back up to talk about. All right, so this is getting towards the end. In our book, published 10 years ago, we showed that we are on a trajectory between RCP 4.5 and RCP 8.5. So here's CO2 emissions as a function of time in the 8.5 and 4.5. And this is an agnostic projection of what we're going to do with population growth and energy demand, and just the track we're on, renewables growing slowly, nuclear after Fukushima not doing much. If we could put the world on a track to get not just electricity, but global energy 50% by 2060, we'd get ourselves on RCP 4.5, and that gives us about a 40% chance of limiting warming to 2 degrees. And I should add that today we get about only 23% of global energy from renewables and nuclear, and we get about 40% of global electricity. So we have a lot more growth to do. To really get serious about limiting global warming, we need to do one of 3 things. We either need to get off of fossil fuels, but as you all know, CO2 is still growing despite all the words. What we do in this graph is we carve out a big spot for carbon capture and sequestration. It would only happen meaningfully if there was a price on carbon that was kind of globally out there. Or the G word, which our prior speaker and a few other speakers have mentioned, geoengineering a climate. Okay, with that, I've tried to leave some time for questions. My last slide is a shout out to the future. I teach at the University of Maryland, College Park. This is our Ph.D. recipients, Joey, Akancha, Hannah, Natalia, Jairam, Henri, Abby, and Andy. And this is Andy Farago, whose work did a lot of the work I'm showing. I was at every one of these PhD defenses. It's my delight to teach the youngsters, these young minds, because they got to figure it out because my generation hasn't done so. Thank you, and I'll be happy to take questions.
Amazing. Thank you so much. And your generation has done a lot, and including teaching all of these amazing young people and many more. That was a super interesting talk. We'll start off with a question from Sydney, which was, we're talking about limiting warming to 2 degrees, but haven't some parts of the Earth already surpassed 2 degrees? What do you mean exactly?
Super. Great question, and thank you so much. I didn't really say these important words. Global mean surface temperature. We're looking at global mean surface temperature. The land warms faster than the ocean. As we heard from a prior speaker, Arctic amplification. The Arctic is way over 2 degrees warming. However, 2 degrees warming is the whole mantra of the Paris Climate Agreement. I mean, that's what, it's a measurable quantity, it's a definable quantity, quantifiable. And so that is a very important policy metric. But yes, impacts are felt differently at different places. The question that Claire asked our prior speaker hits at the heart of it. We warm differently at different places. And, what we're particularly worried about is that as we clean up aerosols, like the world's ship emissions of SO2 have gone down dramatically. That might be playing a strong role in 2023 and 2024 warming. And I will be meeting Sid about 14 hours from now, and I'll be talking about that in my walk with Sid, with Syl. Syl, my bad. Sorry, it's late. With Syl tomorrow.
It is very late, especially on the East Coast for you. Everyone make sure that you go and check out the interview then that Syl will have with Dr. Salawitch about on his walk tomorrow. That's going to get posted on our channel as well. So I had a question about these energy consumption projections that you were showing at the end, and was curious, how are those projections changing with this kind of rapid explosion of data centers, these very energy hungry LLMs that we're all using these days? Is that changing these energy consumption projections dramatically? Are we worried about that? I'm worried about that, but a little naive. Maybe you know more.
Great question. You hit the nail on the head. Yes. So one of the conundrums we've had in trying to grapple with this, and I should actually shout out to Germany, getting 60% of electricity from renewables. Shout out to California, 67%. California is going to ban fossil fuel cars, we think, in 2035. But demand is growing faster than anybody had projected in 2017 because of the data hungry AI centers. So, yep, we're in a bind.
Alrighty. Well, thank you so much, and you have a good night. before we bring on our next speaker, I want to just welcome anyone who is just joining us and thank everyone who has stuck with us. We are in hour 10 now, so thank you so much for sticking around. We are here today to learn, get excited by, and come out and support weather and climate science in the United States. So if you have loved what you have heard about from all of our amazing speakers so far, we have a request for you. We want you to make your voice heard to your congressional representatives. Let them know how important, exciting, and beautiful the science that you are hearing about today is, how much you want to continue to be supported. All of the work that our speakers have been showing has been work that is funded by US federal funding. The United States has built itself as a world leader in weather and climate science and many other disciplines of science through this really sustained federal funding that we have had the immense pleasure and fortune to have, and that our society has recognized the importance for over the past many decades. This has let us develop these amazing tools like the first computerized weather forecasts and the first climate models that were showing the impact of carbon dioxide emissions. We heard a bit earlier in the last hour from Sean about some of these really early predictions from these models about how CO2 would warm the troposphere, the layer that we live in, but cool the stratosphere aloft. These are just some of the amazing scientific feats that have been accomplished through the sustained funding. A lot of the research that we're hearing about here is happening in universities, places that are getting federal grants and contracts to do research to solve important problems that the government and scientists identify as being important for understanding what's happening in our Earth and making important informed policy decisions for the future. So again, if you have been compelled by this awesome work that you have seen, please go to wclivestream.com/act. We have instructions and tips there on how you can call and write to your representatives, let your voice be heard to support funding for weather and climate science. So without further ado, I would like to bring our next speaker to the stage. This is Dr. Ananyo Bhattacharya, who is currently a postdoctoral research fellow at the University of Michigan. And today he's going to tell us about some really cool work on the impact of lakes in weather forecasts. So we're switching gears, going to hear about something new. If you live in the Great Lakes region, tune in now because this talk is for you. And I'm super excited to hear about forecasting of winter storms, something we don't have to think about for a few more months, but it's good to learn about it in the summer.
Yeah, no, thank you so much, Claire, for this introduction. And just before I get started,
we are not hearing you yet.
Okay.
So we're gonna check your audio and maybe.
Can you hear me now? Is it better?
Is that me? Hey, chat, are you hearing our speaker right now? Okay, it's a me problem. Go ahead.
Okay, I'll get started in that case. No, yeah, so just before I get started, I just want to just give a heads up that, I am trained as a planetary scientist. So I didn't even start working with these numerical weather prediction models until last 1 year ago. So yeah, this is the work that I have been doing as a part of my postdoctoral research at UFM. And as you can see that, these models are not made overnight. The list of names, the staff, the engineers, the supercomputing resources, all of that together make it possible. And then some of it goes into operation. So without any further late, I'll just jump into the topic. So many of those people, if you're joining from the Midwest, then I guess you're aware about, our vast Great Lakes, which are comprising about 20% of, I think world's surface freshwater resources. And during the winter months, we have this severe problem when, there's a cold air outbreak, and then the air sort of like goes over warm water, and then that collects a lot of heat and moisture fluxes, which then travels to form these clouds and deposits a lot of snowfall on the shores, and they form sort of like rolling convection and banded cloud structures. Interestingly, like there are many satellite images of this phenomena happening over the lake. So, the downwind regions to these lakes get a lot more snowfall, and the lakes enhance actually this process. Not just that, it is known that the lake as well, the lake surface water temperature and the lake itself freezes during winters. And this freezing properties is actually quite dynamic in nature. It can change within a matter of few days. And therefore, the way these lakes give a feedback to the atmosphere becomes very important to capture if one really needs to predict what's going to happen, in the next 60 hours. So here I'm going to talk about my work, which is particularly focused on NOAA's Unified Forecast System. Again, it's a community-based Earth system modeling project, under the umbrella of NOAA, and it's a framework for multi-scale global and regional weather forecasting models. Particularly the phenomena of lake effect snowstorms, we are going to focus on short-term forecasts, which is like a few hours to, let's say, 2 to 3 days. So that's the time scale, on which we are looking at some of these things. And particularly, we are looking into the representation of lakes in NOAA's rapid refresh forecast system, which is, also a part of suite called short range weather application under UFS. So these tools provide us with a really modular structure to sort of, create both global and regional scale limited area models, and then test some of our findings using different lake models, and, how it changes during different winter storm conditions. So what our approach has been is that, we use FECOM, which is an established three-dimensional lake circulation model, and we couple the output of the FECOM model to UFS to understand, just by changing the lake conditions, let's say the freezing properties and the water temperature as it evolves over these storms, how much does it have an impact on the snowfall forecast? So why is this such a big deal? So it turns out that, historically, or I would say, many, like years back, there were, since the models were very simplified, the treatment of lakes were even more simplified. We had like single column lake models, which may or may not work based on these vast inland, like lakes, which are, if you go to the shorelines of these lakes, they will appear as vast as the seas. So it's very important that, like the complexity of these lakes are taken into account into these models. So here's a snapshot of like the air temperature that we see from different models, and you can clearly spot differences over the Great Lakes region in between these models. Therefore, there is some sort of differences that we generally get depending on the type of lake model that we use. Therefore, this is something which must be brought to light, and has it demands some sort of consistency from the community. So in the recent years, there has been much more upgrade where new models or like existing ocean community models have been adapted to the Great Lakes region, like FECOM and BOM6. And they have been coupled in various capacities with the atmospheric models to sort of look at the regional climatology. And in our work, we are looking at the winter storm prediction. So the way we are doing it is that we focus on a high resolution, limited area domain, just focus on the Great Lakes region. So our domain is actually having like a 3-kilometer horizontal resolution. So maybe it's called high resolution weather forecasting. And the term for it I'm forgetting, but so basically we are using the Great Lakes operational forecast system, which is an established operational product, which is based on the FECOM lake model, and it has already been forced using some sort of atmospheric dynamics model. Particularly GLOFS uses the high resolution rapid refresh model, the HER model. So in a way, it is providing a consistent feedback back to the atmosphere. And hopefully we will see some positive changes in the couple of slides I'm going to show you from here. But yeah, just to throw some light on what RUFUS or Rapid Refresh Forecast System, its capabilities are, you can see the vast extended domains that NOAA's model can actually resolve. So, for my case, I'm just focusing on this domain, but when I go to conferences, when I meet other colleagues, they are definitely working on all different parts of this entire extended domain. And similarly, all the work that has been done to develop these kind of models can be applied to different parts of the world as well. Now, the particular way we are introducing the feedback of lakes is through the Earth System Modeling Framework. So it's like a generic architecture through which we are ingesting some of the FECOM lake data conditions. And then there's a physics dynamics coupling package called CCPP, and it sort of feeds back to the atmospheric dynamics solver. Now, there are certain schemes, or we call them like land atmosphere schemes, using which we calculate different sort of surface fluxes that goes and directly feeds into the atmospheric models. And especially it will affect the cloud formation and, like the surface heat fluxes, which, will happen due to the dynamic lake conditions. And particularly, we look at the initial and like boundary conditions from the rapid refresh model, which is like a 13-kilometer resolution forecast or analysis files, and then we regrade them on a 3-kilometer domain. So we are looking at selective cases where we find that it's much more easy to pick out how the lakes enhance the snowfall. So for my own research, I was looking at the recent winter cases, and this is sort of an example of like how the snowfall looks like. And as you can see, the downwind regions are very much affected. So this is what it looks like to sort of be in Midwest and like maybe watch a news channel, and then you see like, okay, this is the forecast, or this is something which has happened over the next weekend. And it's interesting to work on the other side of it, which is probably at some point of time will help the operational weather forecasting. So the dynamic lake coupling improves snowfall forecast. So one thing over here is that so this is like a snapshot of different like lake water temperatures. And something easy to pick out is that sometimes, as the event progresses, the lake water temperatures go cooler and cooler. Especially for Lake Erie, it is very easy to spot, so if I do like a static lake boundary condition versus a dynamic lake boundary condition, my water temperature diverges enough, and that affects my surface sort of like fluxes into the atmosphere. And so far, what we have seen is that if I compare it with the SNODAS data product, which is sort of like a state-of-the-art snowfall data product, just to see how well a dynamic lake improves, we find like about it improves the snowfall forecast by 2 to 13% so far, and it's very much dependent on case-by-case conditions. But what we are trying to root for is that we have the architecture right now, so it can be done in the future. And given that these lakes are evolving in nature, and we can capture the 3-dimensional spatial scales of some of these mixing processes, it becomes a very important resource for the entire community. Now, moving on, we are also trying to look at the sensitivity of these lake conditions, because it's very hard to figure out what the lake water temperatures during winter months. In fact, the observational product GLC, which comes out, it can actually be delayed by let's say over 10 days, because the lakes get pretty cloudy due to in the winters, and also like there could be genuine observation gaps over the lake regions. So we sort of try to do like idealized scenarios, and just by looking at let's say the differences in lake water temperatures, you can see that what can be this envelope of uncertainty in my 60-hour forecast, or 2 to 3-day forecast from now. So my work is sort of supporting, which might transition, if possible, into the operations, and is also aligned with some of the other developments going within the UFS model. So with that, I would like to summarize that, like we implemented and tested a dynamic lake coupling scheme for the Great Lakes region, one of the world's largest freshwater lake systems. yeah, and it provides, like hourly feedback of lake temperature and ice conditions. One good news is that we were able to merge it with the development branch. So this capability, it's open source, it's on GitHub. So if somebody has a supercomputer that can run UFS, they can definitely do this. Yeah, and with that, I think, I would like to open the room for questions.
Awesome. Thank you so much. There are a ton of questions in the chat. Understandably, people are very excited about lake effect snow. So let's start off. We have two kind of similar questions about how we should think about the Great Lakes. Are they really lakes, or should we think about them more as inland seas? Are they just big enough that we shouldn't count them as a lake per se? And kind of how comparable are they to other bodies of water, such as a river or in fact an inland sea on the snowfall?
Well, I might not have the exact answer to your question, but in terms of how important they are, like it impacts both states in like USA and, like provinces in Canada. So understanding, let's say, lake effect snowfall is one of the things. The other thing might be the water levels. They are also constantly changing, and it's quite dynamic in nature. And just, from what I know, people at University of Michigan or other parts of the Midwest have been studying this problem for quite a while. They call it a transboundary water resource, which is very interesting to think about because it serves as a very critical role. Yeah, but other than that, like these are really large lakes, and just by if you go around the shores of these lakes, you will just understand the scope of it, what you're dealing with. And even like 1 year ago, I was not aware of these things, but just by exposing myself to the weather forecasting enterprise, if I can say, like academia or maybe NSF NCAR, they provided me a lot of training to sort of understand, look back. And in fact, one of the funny things was that I ended up simulating a snowstorm where I myself was situated in Ann Arbor on one of those days. So it's an
That
interesting take on how big of a role they can play.
Yeah, that is so cool. It's definitely fun to get to see how our science connects to our actual lived experience of the weather in the places we live. I totally know what you mean when you're standing on the edge of one of these lakes. I used to live in Chicago, and you look out and you can't see the other side. It's pretty crazy. Um, I want to pop up this question from Sydney again, who wants to know, is lake effect snow a different consistency or quality to snow that where the water comes from other places?
Hmm.
How does it affect the actual snow that
How
falls?
does it affect the actual snow? That's a good question. I don't think I might be the right person, but in terms of can there be water from other places? Yes, definitely true. So it totally depends on how some of these events are. So let's say when I'm developing a new model, I can talk it from a modeler's perspective. Like I'm making modification to this new code that I made. I want to know how lakes sort of improve or changes things. So we particularly picked up cases where there are larger signatures of the lakes, but there are also these large scale forcings or maybe like cold air outbreaks where I think you would get a lot of moisture sources from the north, from Canadian side, and that is quite a huge amount of moisture, and it definitely amplifies by the time it reaches the Great Lakes region. And there are dedicated studies to sort of like look at the budget of how much amount of like a role does Great Lakes play. So I would say studies exist. So this is already being investigated. So if you just search out, and there's a gigantic infrastructure. People try to monitor stable water isotopes. They do numerical weather forecasting. So I cannot answer that in one single sentence, I'm afraid. But thank you so much for bringing it up.
Yeah, thank you. And thank you so much, Ananyo, for your great talk. I guess Sydney, I can jump in with a little bit of an answer to your question because I myself study clouds. One of the things that we know is that the water, once it evaporates into the air, it's quite agnostic of its source. The only thing that can really trace where that water has come from is exactly what you just mentioned about the isotopes. So we can look at the isotopic composition of the water as a tracer of where it was evaporated from. And that is a very cool technique. But in terms of the quality of the snow that falls, that's really determined by the local thermodynamic conditions, the temperature, primarily that air parcel is experiencing as it moves along as the snow crystals are forming in the cloud. So it doesn't have so much to do as where the water came from, but what temperature it is when the snow was forming in the atmosphere. So, okay, we're gonna move on. Thank you so much, Ananyo, and
Thank you
have
so
a
much,
great
Claire.
night. We are coming up on the end of hour 10. This is going to be our last talk and my last talk hosting. Thank you so much for everyone who has stuck with us, and for anyone who is new, welcome. This is the Weather and Climate live stream. We're here sharing weather and climate science with all of you, our viewers, to share our passion, our excitement, and the amazing feats and knowledge that we have learned through our research, and how it benefits our whole society. So the United States has been a world leader in weather and climate research for many decades, and this is in very large part due to the sustained support and funding from the US federal government. This funding is currently at risk. The administration had proposed substantial budget cuts to all of our scientific agencies. We've heard about the NSF, which supports NCAR, which we've heard a lot about. We've heard about NOAA. In this past talk, we were hearing about a lot of resources that are developed by NOAA, and there were many NOAA collaborators on that work that was shared. We've heard about NASA, of course, that is responsible for launching, operating, maintaining our amazing satellites that are making measurements of the Earth, as well as other agencies like the Department of Energy that does a lot of important work in the weather and climate space. All of these agencies' budgets have been proposed to be slashed, decimated, cut in by very large amounts, up to 50%. And this would be very devastating for our weather and climate science enterprise, for the continuation of the models, the tools, the resources that you have seen being used, but also for the pipeline of scientists that are being trained to continue doing this work over the next decades. So if you've been inspired by the awesome science that you've heard, please call or write to your representatives, make your voice heard. You can go to wclivestream.com/act to get more information and learn about how to make that contact to your reps. So our next speaker, I will welcome to the stage, is Brianna. Brianna, welcome. Brianna is a early career climate scientist, and she has a super exciting talk title for today about the muddy coastal Arctic. The Arctic is a super fun place. I've had the privilege to start studying it myself in the past few months, and I can't wait to hear about the coastal muddy Arctic. Please take it away.
Yeah, thank you, Claire. Thank you for the introduction. And I also just want to thank all of the organizers for putting on this very important and powerful event. So my name is Brianna. I recently graduated with my Ph.D. from the Department of Atmospheric and Oceanic Sciences at University of Colorado Boulder. And so I'm in that weird in-between period of ending a Ph.D. and starting a postdoc. So I'm kind of in limbo right now, but I wanted to share a little bit of my dissertation research with you all, called the Muddy Coastal Arctic. So we've had a lot of weather and climate talks, and I'm just going to pivot us back to the ocean for a little bit, but in the context of climate change. So still relevant. So hopefully people are joining us from all over the US, maybe even all over the world. Feel free to put in the chat where you're coming from. I personally am tuning in from Boulder, Colorado, But for the purposes of the next 10 to 12 minutes, we will be focusing on the Alaskan Beaufort Sea Shelf, which is located up in northern Alaska in the Arctic. And a really cool feature of this region is seasonal sea ice coverage. So I'm going to play a movie of satellite images, but I just want to orient us. We are looking at the same area that I was just showing, and you can kind of see the coastline, but it's a little hard to see because of all these clouds. So we have land over here and ocean over here, and then the false color is showing you the sea ice concentration. So for example, a purple box has about 25% ice coverage, and then our reds and whites are higher sea ice coverage, and we're starting in August, but I will let this movie play. So again, land over here, ocean over here. You can see this region is really cloudy, and then when we're in the summer months, the sea ice is further away from shore, and we have a lot of open ocean or open water near the coastline. But then as we start to get more into the winter, the sea ice will form closer to shore and kind of move closer to land. It also gets dark because we are in the Arctic, and so there is a portion of the year when it is completely dark for several months. And you can imagine that combined with the cloudiness makes it very difficult to get satellite observations for this region. But now that we're deep in winter, we see the ocean is pretty much fully ice covered, and the sea ice comes all the way up to the land. And then as we get more towards the end of winter, daylight comes back, and we can see it's really cloudy and it's really snowy on land, and we still have the sea ice. And so this impacts a lot of the ocean dynamics. Like you can imagine, not really any sunlight can reach the water column, and then a lot of waves are dampened. And then as we start to get into the spring and summer, the sea ice retreats or melts and starts moving away from shore, and then is still present out in the deeper ocean, but we return back to those open water conditions closer to land. So we know that sea ice is a really important factor in these regions for the ocean, as well as for the climate and the weather. And then we also know that the Arctic is getting warmer, and it's predicted to continue warming. So there are these really cool things that I think a few people have referenced so far called the IPCC reports, or Intergovernmental Panel on Climate Change. And this is essentially where a bunch of scientists from around the globe come together and look at the state of the science on climate change in different aspects, and then combine it all into a report to just kind of say like where we're at with things research-wise. So I'm going to reference a summary for policymakers, which I think is a very valuable tool that writes things in very accessible language. But I put the QR code here to the website if you want to just explore these reports a little bit more, because I think they're super cool and a little bit depressing, of course. But I'm going to pull a few things from these reports. The first is looking at the observed temperature change in response to 1 degree Celsius of global warming. So here I have a map of the Earth, and the color is showing you the temperature change in different regions. And I want to bring your attention to the Arctic. And you can see that we have some of the deepest reds in this region, meaning it's already had some of the largest increases in temperature on the Earth so far. And then they also looked at projections in temperature change under different amounts of global warming. So in the bottom left, you can see the simulated temperature change under 1.5 degrees Celsius global warming, and then 2 degrees Celsius in the middle, and 4 degrees Celsius on the right. And again, I want to bring your attention to the Arctic, to these northern latitudes, where you can see we have our deepest reds, and therefore the Arctic is projected to warm pretty much more than anywhere else on Earth. And you can imagine this will have implications for the sea ice in this region, and then the ocean dynamics and the weather, and so on and so forth. So coming back to our Alaskan Beaufort Sea Shelf, we know that rapid changes are taking place in response to warming temperatures, and these include stronger waves in these regions. It also includes increased river discharge. So you can kind of see in the satellite image that we have some small rivers in this region that deliver sediment and nutrients and fresh water to the coastal ocean. Also, a lot of this land is permafrost, which I think a few people have talked about, including Kara. And you can see that as this permafrost starts to thaw on land, it forms these little lakes that show up as these dark spots on satellite images. And then we have increased permafrost bluff erosion. So a lot of the coastline up here is these permafrost cliffs or bluffs. And as water temperatures get warmer and waves get stronger, they carve away at the base of those bluffs and cause them to collapse onto the coast. And then as they melt, they deliver fresh water and nutrients and sediment to the coastal ocean. So all of these changes are impacting the coastal sediment dynamics and the seasonal sea ice formation, which is the focus of my research. And you might be wondering, why do I care about sediment in the ocean? And that is a very valid question. So it impacts a whole bunch of things, and one of those is marine photosynthesis. So you can imagine if you have a lot of sediment suspended in the water column, it will block sunlight from organisms trying to perform photosynthesis, like kelp and phytoplankton. And we care about kelp and phytoplankton because they form the basis of the marine food web, and phytoplankton are also responsible for a lot of the oxygen that we breathe, so they are great for us. And carbon sequestration. So carbon can stick to mud particles, and then if this mud gets buried on the seabed, it can essentially store that carbon or sequester that carbon so that it doesn't get released back into the ocean or the atmosphere, kind of drawing down carbon and limiting the greenhouse effect. So also important in the context of climate change. And then for sea ice, this also impacts a whole bunch of things, including coastal navigation. And this is especially important for the local communities in northern Alaska who depend on sea access. And then global climate. So having a cold region at the North Pole really drives a lot of the ocean and atmospheric circulation on Earth. So really quickly going to give a little intro and conclusions, results from my research. It's going to be a little bit of whiplash. I apologize, but I'm happy to answer any questions afterwards. But the objectives of my research have pretty much been to simulate and analyze present-day Arctic coastal sediment dynamics. So we can understand present-day dynamics to better understand how they might look under future Arctic conditions, and then to investigate how different model choices impact modeled sea ice formation to better constrain uncertainty in sea ice, because it is so important for the climate system. So sediment, when I talk about this, I'm talking about like the mud and the sand and the pebbles that are in the ocean. And waves and currents in the ocean can suspend and move this sediment around the ocean, which will impact things like light attenuation and photosynthesis. And then sea ice. So sea ice formation in the ocean depends on water temperature, and water temperature depends on mixing. But there are different ways that we can calculate mixing in numerical models. So some of my research also looks at how different model choices impact your sea ice conditions. So I've kind of alluded to this, but my research centers around numerical modeling. So I'm essentially taking this region in northern Alaska, the Beaufort Sea Shelf, and recreating it in model world. A little bit of jargon: numerical ocean models are computer models that use a large number of mathematical equations describing physical phenomena to simulate ocean dynamics. And they're really powerful because we can like tweak one little process in the model and see how the rest of the ocean responds. So they help us kind of tease out different relationships between different processes, which is especially important when you're trying to look at how things might respond in response to changes in Arctic conditions. So I'm just going to throw some really quick results at you guys and kind of talk over this movie while it plays. So here I'm showing some model results with the background shading being suspended sediment concentrations, and then the arrows being sediment fluxes. So showing once that sediment is suspended in the water column, where is it going on the shelf? And then each of these dots are the different rivers in our domain. And you can see that we have the highest suspended sediment concentrations near shore, where we have these really dark browns. So you can imagine if you're like kelp or phytoplankton in these dark brown regions of the ocean, it's going to be pretty hard to perform photosynthesis. And that's especially important to understand under future Arctic conditions to see how that will change these processes in this region. And then some quick sea ice results. We also see that modeling choices can impact the timing of sea ice formation. So here I have a time series where the x-axis is the model day, and the y-axis is the sea ice concentration. And then each colored line corresponds to a different model simulation that used a different model choice. And then these vertical dashed lines are showing you when each model reached 15% ice coverage, which is a threshold we use to determine whether or not the water is considered ice-free. And you can see that just by changing how the model does a certain process, we get a spread of about 1 day in sea ice formation. And so that can have a lot of implications for like how much light is available during that day, and like wave activity, and a whole bunch of cascading effects. So we're still kind of placing this in the context of other sources of uncertainty in sea ice and models, but this is just some preliminary research showing that some modeling choices do have an impact on this. And then I just really briefly wanted to talk about this research in the context of current events. So numerous people and institutions have made my research possible, including various funding sources such as the National Science Foundation and a Department of Energy fellowship under the Biological and Environmental Research Program, and then funds from my university. And then I've had numerous collaborators help a lot on all of this research, spanning universities across the country, as well as the National Center for Atmospheric Research, and then undergraduate participants in the Atmospheric and Oceanic Sciences Data Science Research Experience for Undergrads, or RU, at CU Boulder, which I helped organize for the past 5 years, but we did unfortunately get canceled right before our last year, which was very disheartening. But I just think this research is really important and really valuable and inspiring, and I hope that it can continue in the future and maybe even grow, because a little optimism never hurt anybody. So with that, I'll leave you with just a quick summary, and thank you for listening and supporting the Weather and Climate live stream. And I'm happy to take questions if there's time.
Amazing. Thank you so much, Brianna. We have time for questions, and you've gotten some really good science questions in the chat here. So I'll pull up the first one from our loyal viewer, Fish, who wants to know, is the increased river discharge causing more algal blooms?
That is a good question. I personally have not looked at that. I would think yes, potentially, because of, like you're saying, like there's more nutrient delivery. However, there is a paper by Bonsall and Duncan that looked at kelp primary production, and it saw that having less sea ice and having stronger waves suspended more sediment and kind of blocked photosynthesis because of the increased like activity in the ocean. So like you might be getting more nutrients, but if the waves are really strong and it's suspending a lot of sediment, it could make it hard to do photosynthesis. So I think it's not super straightforward, but I'm guessing that like first principle, that is probably something that could contribute to more, algal blooms. Really good question. I have not looked into it, but that's my best guess.
Awesome. Thank you. And then we have another question, which this person knows what they're talking about because they want to know if sediments impact the alkalinity. So maybe you want to take a stab at telling the rest of our viewers and me, what is alkalinity?
Okay, I have not thought about alkalinity in a hot second, but it is definitely has to do with hydrogen ions potentially. I honestly am more on the physical oceanography side than the chemical or biological. So I do not want to give fake information, but I don't think so, but it probably depends on what nutrients are associated with these sediments. I think about them really as just like mud, and sand, but not like a lot of the chemical side. But yeah, so that's a good question.
Good question. Okay, Dreamin9Tree, please bring your question back. We will have more chemical oceanographers on the stream. There are some people out there who love alkalinity and they would love to answer that question for you. We have one more question for you, Brianna, which is, do ship channels influence the stirring of sediment reach that far, and is that considered a factor?
Yeah, that's a really good question. So yes, the bathymetry data set I used to make my model domain back in the day, many years ago, did have this like weird shape in it, and I smoothed it because you have to smooth a little bit so the model doesn't crash, but it did not go away, and then I learned that it is a shipping channel. So yes, that is an influence. And another really important thing is sea ice can actually scrape the seabed a lot, or create like water will flow through the sea ice and then make little funnels that create divots in the sediment. So sea ice also does a lot of wonky stuff to the sediment in this region. But shipping channels is another thing that might increase as shipping increases in the Arctic. So very good question.
That is super cool. I've never thought about sea ice helping stir up the ocean.
Yes.
That's so fun. I think we are coming up at the very end of hour 10. Thank you so much, Brianna. And you have a good night.
Thank you too, Claire.
This is also, we love your earrings, by the way.
Thank you. I had to match your cloud again, so you inspired me.
Yes. So as we come up to the end of hour 10, we've just switched over to hour 11, and that means this is the end of my time as host. Your next host is going to be McKenzie Larson, and she is a Ph.D. candidate at the University of Colorado, Boulder. So loving all of our Boulder folks out here right now. McKenzie, please take it away, and we'll try to do a little high five. We got
This
it.
side, or-
No, that side, yeah.
Awesome. Thank you so much, Claire. I've really
Bye,
enjoyed
everyone.
I've been enjoying the past 2 hours. It's been a lot of fun, and I want to thank all the organizers for all of the work that's gone into organizing this whole live stream. There's a lot that goes on behind the scenes, so big round of applause for everyone there. So hi everyone, welcome to hour 11 of the Weather and Climate live stream. My name is McKenzie Larson. I'm a 5th year PhD candidate at the University of Colorado Boulder, Go Buffs. I'm just like Brianna, who just talked. I'm in the Department of Atmospheric and Oceanic Sciences, and some of my research focuses on Colorado downslope windstorms. So I'm really excited and looking forward to spending the next 2 hours with all of you here as your host. But before we start, I want to remind everyone why we are here. And that is because as history has shown, and what we've just been talking about the past 10 or so hours, US scientists have been world leaders in weather and climate prediction research. We have some of the first computerized weather forecasts. We have complex models of the weather and climate, as well as a huge observation network of weather data, including satellites, airborne measurements from planes. We take measurements on boats, as well as floats, and much more. And all of this amazing research and scientific advancement is thanks to you, the public, because our taxpayer dollars is what allows for this US federal funding of our research and is really essential in our field. However, currently the administration's proposed budget for the fiscal year in 2027 is jeopardizing this research and the science that conduct our science. There are currently cuts to the National Science Foundation, NSF, as well as NASA's Earth Science budgets that are proposed cuts that go pretty much in half. And, a big question I have, as many of us have others talking on this live stream as well, is how can we train the next generation of young scientists to better inform our weather forecasts, as well as our climate understanding if this happens? For example, my research of extreme downslope windstorms in Colorado is federally funded by a graduate research fellowship, which I'm extremely thankful for. So we've already seen some negative impacts from funding cuts, such as short staff weather forecast offices, some shrinking and shuttering of climate labs. As Brianna also just mentioned, in our department, we had a research experience for undergraduates, or REU program, that was funded by the National Science Foundation. And about a few weeks before it was supposed to happen, it was terminated. So we were really sad to not have those summer students working with us on some climate and ocean research. So as we kind of talk about why we're all here, please make sure you visit our website, wclivestream.com/call, to contact your representatives as well as senators to help protect our weather and climate research. So our next speaker I'm really excited about is Haley Staudmyer, who is a climate scientist and PhD candidate at the University of California in Irvine, who's going to be talking to us about the impacts of extreme heat on daily life. And just as a reminder, all of our speakers' views are their own, and they are not representing their employers or any other institution. So take it away, Haley.
Hi, McKenzie. Can you hear me okay?
Yes, I can. Perfect.
Okay, awesome. Hi, everyone. As McKenzie said, my name is Haley Staudmyer. I'm super excited to be rocking this late night talk with you guys. I am in my dog pajamas because if I'm going to give a talk at 11 p.m., that's how you're going to get me. So anywho, I would love to talk to you about my interdisciplinary research on how extreme heat impacts daily life. Hopefully something a little different from what you've seen over the past 10 hours. So this is a person who has volunteered to get in a box. This is a sealed heat chamber. What is going to happen to this person is that she's going to have a thermometer inside of her. This thermometer can either go down her throat or up her butt, or she can swallow a thermometer. that thermometer is going to read her core body temperature, and then we're going to crank that heat up. She's in this sealed box. We're going to just roast her alive. So that air temperature is going to go up and up. But miraculously, her body temperature is going to remain constant for quite some time. Our bodies need to remain in homeostasis, right? They want to remain at that 98.6 degrees Fahrenheit. That's how we stay healthy. So you've got all these tricks up your sleeve, and that, if she swallowed that thermometer, that's the temperature that's reading constant. Even though the environmental temperature is going up and up, our bodies are just amazing. But there is only so much they can do. At some point, it's going to get too hot, and that internal thermometer of hers will show her body temperature, her core body temp, start to rise. So what is that temperature where there's that inflection point? That's not the point where she immediately drops dead. She's not going to immediately pass out. It just means that if she can't get out of the situation, she's going to be in trouble. Her organs might start to fail. So we take this temperature, let's just call it temperature X for right now. And so I have friends, I don't do this. I don't torture people, and this is all voluntary, and she's getting paid to do this. But basically, my friends, my collaborators, get this information. They figure out what is this temperature that it is too hot for her to safely be in there. And then I look into our climate models, these climate models that are taxpayer funded, not just in the United States, but in many places around the globe. And I look in these climate models and I say, well, here's the temperature. The average temperature is going to rise over time. So when do we get to the temperature where it's too hot to do anything for our bodies to compensate for us? So that's the question that my research tries to answer. How hot is too hot for humans, and when will that happen? But the answer is not quite so simple as looking for temperature, because humidity also plays a big role. You are also experiencing elevated humidity in the heat chamber, and your body is going to sweat. That's one of the main ways we cool down. Think about when you get out of the shower. Maybe you took a really hot shower, but even though it was really hot and it's very humid in that room, you're still freezing when you get out of the shower. You're like, I need that towel right now. Why is that? It's because as your sweat evaporates, it's going to take heat with it. And so as that sweat evaporates, just like when you get out of a pool and you feel cold because that water evaporates, you feel much cooler. That's great. That's why we sweat. But as it gets more and more humid, there's no more room in the air for that water vapor to evaporate, or for that water to evaporate into water vapor. So as a result, more humid conditions are more dangerous. So when I look in my climate models, I can't just look at temperature. I have to look at humidity. And it doesn't stop there too. Spot the difference between these two heat chambers. We've got someone over here who's walking, and he's going to be generating his own internal heat while he's exercising. That puts him in a slightly more dangerous position than if he were sitting. But he's also young, and he sweats a lot. Did you know that as you get older, all of your sweat glands will degrade? You'll stop producing as much sweat. And as a result, our elderly are more vulnerable to heat-related illness. So think about that. Let's say we had no climate change whatsoever. The average age of a person on the earth is also getting older because we have amazing scientists who help keep people alive. So the average person gets older. Even if we had no climate change, we would have more and more people vulnerable to heat and experiencing worsening impacts from heat. So we have these two totally different causes of worsening heat impacts over time. So this is what I look at in my research, and I do so using an amazing new tool, which can take, have you ever looked at your phone and you look at the temperature to see how hot it is? We talked about how humidity also matters. So maybe you scroll down a bit and then you look at heat index, which is rolling these two things together. That tells you it feels like 100, even if it's really only 90 because your sweat's not evaporating. But what it feels like to me is not what it feels like to my grandma, right? Because we sweat differently, our bodies are different. So what if we could add in physiology to this equation? What if we could consider someone's ability to sweat, their height, their weight, and even the clothes they're wearing? So I use a tool that can take all of this information, not just the environment, but also the physiology, and put out the level of activity that it is safe for someone of that physiology to do in those temperatures. We call this model the heat limb model. You don't need to know what it stands for. So effectively, think of it this way. Here I'm going to show you a graph where blue is low intensity physical activity and red is very heavy physical activity. We'll have air temperature on the x-axis, and we'll have relative humidity on the y-axis. So over here is cooler, over here is hotter, lower is drier, and farther up is more humid. And so as you can see, this graph is telling you the level of physical activity that will still be compensable, where your body can remain stable in its core temperature at a certain temperature and humidity for a healthy young 18 to 40-year-old adult in shaded conditions. You can see that if it's less hot and dry, you get these nice red colors. That's good. That means you can do more intense physical activity and still be safe. But if it's very humid and more hot, then only a small amount of physical activity is safely compensable before your body temperature starts to rise. So let's take a look at a particular MET value. We measure the physical activity in a unit called METs. Don't worry about it. Basically, think about a moderate level of physical activity that's equivalent to harvesting crops. Like you're trying out there, you're definitely doing some amount of physical activity, but this is not the most intense physical activity. Okay, how much of the average year will be uncompensable for this moderate physical activity in the future? That's a question that I ask in my research. So I'll show you another graph where on the x-axis, you have the global average warming. So you've heard of the Paris Climate Agreement, how we want to keep our global average temperature rise below 2 degrees Celsius. So that's right here. And we have the better outcomes and we have the worst outcomes depending on how we do. And then on the y-axis, we'll have the percent of the year at 2 degrees of warming. Oh, you know what? I'm sorry, I should just say percent of the year. I'm sorry, that's a typo. I gotta fix that. Okay, so percent of the year. And then we'll also have different latitude bands in different colors, as well as our global average in black. Basically, what we see is that the percent of year is going to go up with more warming. So this 0.7, this is like the 1980 to 2010 period. That's what we've experienced before. Compare that to the 1.5 degree world. It's worse, but it's not quite that worse. But then as you get into this 2 degree warmer world, especially people in the tropics will experience a much greater fraction of the year where they're not going to be able to do the physical activity they need to survive, to harvest crops, to go exercise. And people who live in the tropics already modulate their activity. They don't work during the hottest hours of the day to stay safe because they already experienced this, but it's going to get even worse and it's going to get harder and harder to avoid that heat. And of course, the more we allow the climate to change, the worse these impacts are going to get. So the amount of time of the year that it will be unsafe for even a healthy young adult to do this moderate level of physical activity is going to increase with global warming. So the more warming, the less time for physical activity that will be safe. And this is a greater portion of the year for older adults. All of this graph is for young adults, but it's more of the year if you're old. And the elderly are maybe not harvesting crops, but they do, of course, need to go out and get exercise, right? So that's just a taste of what I do. I want to talk to you just a little bit about why federal weather and climate funding is so important. Here's a graph of weather fatalities in 2024 across all the different weather extremes that you've probably heard about with heat. In the middle here, let's see where heat clocks in. And wow, it kind of blows some of these other ones out of the water. You might think, lightning and hurricane would kill a lot of people, but in fact, heat is a silent killer. You just don't hear about it because on the news, they can't show, oceans of, blown out buildings and things like that. It's not pretty to look at or exciting, but it's a real killer. The good news is that all of these deaths are preventable. Really, not just heat, but any of these deaths, right? The more that we understand about what's coming down the pipe and the more we prepare, then we can save pretty much all of these lives. So the good news is that the majority of Americans, according to our best, most recent research, believe that our government should be doing more to address global warming. And in fact, sometimes it doesn't feel like this, but about 70% of Americans do think that global warming is happening. So if we're all on board that this is happening, and we can get more people on board that we really should be doing more about this, then funding is one of the best ways possible that we can keep doing research and be prepared for what's coming down the pipe. My research is done, it's made possible with the National Science Foundation and the Department of Education. I personally have been very impacted by NSF cuts. A fellowship that I was funded on through the NSF got canceled by DOGE, and then I had my own funding in jeopardy, but I also had friends who were post-baccalaureate scholars. These are 22-year-olds who had just finished undergrad, and they were in a one-year program post-undergrad, and they weren't going to get a paycheck. I mean, their jobs just, evaporated, and they weren't going to be able to pay rent. I mean, it was a really dire situation, and to watch them go through that was really painful. There was a lawsuit, and that funding did get restored, so my friends ended up being okay. But the jeopardy that these funding cuts have put people in, not everyone is so lucky. I'll put it to you that way. Additionally, just that RU program that McKenzie was talking about at UC Boulder, I did an internship like that when I was an undergrad, and I fully attribute that I'm where I am today because of a similar program that I went through. Those are critical experiences for undergraduates, and we will never have future scientists if we don't keep funding programs like that. I could go on and on about how important this all is to me, but please know that you all who pay taxes have changed my life, and I do nothing but hope to serve the American public and keep people safe with every day of work that I do. So thank you so much for having me on.
Awesome, Haley. Thank you so much, and for a very amazing talk, very touching as well. I really like how you talked about, how important thinking about the heat is with physical activity, and how it's not often talked about in the news as much. It reminded me of, if anyone's watched the new season of The Pit, where it's like July 4th, they kind of bring light to a lot of how heat can be a bit of a silent killer. So we have a lot of great questions for you here today. Our first one's going to come from Sydney Lindquist. Early question in your talk: if humidity is at 100%, do breezes cause more harm or not make any difference?
If humidity is at 100%, then if you get a breeze, then hopefully it's circulating air that is slightly cooler towards you. Generally speaking, though, humidity is very rarely at exactly 100% unless it's actively raining, in which case, if it's not at 100%, then breezes are going to help evaporate that water a little faster. But I suppose if, you don't want the breeze to just be blowing the water off of your skin where it's not really evaporating. Great question. I think that generally speaking, if humidity is at 100%, then a breeze won't be quite as helpful.
Okay, awesome. I think we have time to squeeze in one more question. One person asked, Lila says, that seems to be about 50% of the year in the middle of your presentation. If we're talking about harvesting crops, wouldn't that be a large portion of both the growing season and harvest season?
Yeah, that's a great question. I would love to dig in further to that. My research has mostly been on a global scale because that's just been the scope of it. But in future work that I'm just about to start, I'll be zooming in on California specifically to understand how heat is going to impact our ability to do physical activity during more specific times of the year. It's definitely going to get worse. It's perhaps going to force us to harvest our crops at different times, maybe waking up much earlier or staying up later after the sun goes down in order to do that safely. I should mention also that my calculations are assuming full shade, which certainly not all workers have, but as a scientist, we try to be as conservative as possible so as not to, so people don't accuse us of making things seem worse than they actually are.
Awesome. Well, thank you so much for your talk. You have a few more questions if you want to pop into the YouTube chat
Yeah,
to answer
absolutely
those.
will.
But thank you so much for your time and for sharing your science.
Thank you.
Yeah. All right. Next, before our next speaker goes, I'm just going to again remind everyone why we're here. And that is because U.S. scientists have been leaders in the weather and climate science and prediction realm. We have developed complex models of the weather and climate, as well as have developed a very large observation network ranging from satellites, airplanes, all the way down to the sea, using boats and floats and whatnot. And all of this amazing research and scientific advancement is thanks to all of you, the public, where we use our taxpayer dollars here to help support U.S. federal funding that gives us the essential funding we need to support this science. And so one organization that you've heard about over the past 10 or so hours here during this live stream that is at the heart of the weather and climate science is the National Center for Atmospheric National Center for Atmospheric Research, also known as NCAR. So some of the weather and climate models that we all depend on for our day-to-day lives are developed and maintained at NCAR. If you're clicking onto your weather app on your phone, many layers behind those forecasts are these weather models that have been developed at this amazing organization. I personally love NCAR. I spent a summer there as a student visitor right after I got my undergraduate degree to help further dive into Colorado downslope windstorms, which you can hear me talk about tomorrow night at 10:40 Eastern time in the evening. And the time that I spent at NCAR and the collaborators that I met there have really shaped my career. And I absolutely would not be where I am today without my experience at NCAR and the wonderful people that work there. So we've already seen some negative impacts from funding cuts associated with weather and climate science, such as short-staffed weather forecast offices, shrinking of climate labs in academia, as well as some summer internships for undergraduates that have been cut as well that I talked about and Brianna did in this past session as well. So we encourage you to please visit our website, wclivestream.com/call to contact your representatives and senators to protect weather and climate research. Our next speaker is going to be David Ho, who is a professor at the University of Hawaii at Manoa, who's going to be talking about if the ocean can take up more carbon dioxide. And just as a reminder to everyone, all of our speakers' views are their own and they're not representing their employers or any other institution. So welcome, David. The floor is yours. And thank you so much for being here.
Yeah, well, thanks for having me and thanks for hosting. And thank you to the organizers for putting this together. And I should start by saying that, I'm pretty late in my career now, and I wouldn't be where I am without federal funding from my NASA graduate research fellowship when I was a PhD student to the funding that I've gotten along the way as a scientist from NSF, from NOAA, from NASA, from the US Geological Survey and the National Park Service, as well as the USDA Forest Service. So it's all because of the taxpayers that I'm here. But today I'm going to talk about whether we can get the ocean to take up more atmospheric CO2. Okay, and so basically what I'm talking about is climate intervention that people call carbon dioxide removal. And it's sort of obvious what it is, which is that we want to have some way to remove more CO2 from the atmosphere. And it's important when we talk about these things, I think, to emphasize that, we should focus. The focus has definitely need to be on eliminating carbon emissions, decarbonizing our entire economy, right? Stop burning fossil fuels. But at the same time, if we really care about CDR, carbon dioxide removal, then we need to fund it as much as possible. And the only source of funding for this kind of stuff is governments, because governments are the ones that have the money. Okay, so if we can keep those two things in mind, then we're good. So I want to say something about this figure. What this shows is the amount of CO2 we put into the atmosphere, the total amount that's in the atmosphere, and then the resulting global warming. And you see this linear relationship. And this is very convenient, right? This is called the transient climate response to emissions. But because there's this nice linear relationship, we know that if we want to keep global warming below 1.5, we can put a certain amount of CO2 into the atmosphere. If we want to keep it below 2, we can put a little more. But it gives us this carbon budget to work with, right? And unfortunately, so here's a figure showing time, and we're somewhere here. And this is emissions from our energy and industrial processes. So it doesn't include land use and land use change. But we're putting in something like, including land use change, over 40 billion tons of CO2 into the atmosphere every year. And if we want to keep global warming below 1.5 degrees, we have to be at 20 billion tons of CO2 every year by the year 2030, which is only in 4 years, right? And what this graph is showing is that each of these color bars is how much CO2 emissions dropped during COVID, when basically the whole world shut down. And if we did that every single year until 2030, we're going to miss that target by a lot, right? So we're at the point where reducing emissions is not enough. We need carbon dioxide removal, okay? And there are methods that are based in the terrestrial biosphere or technological methods on land, but what I'm going to focus on is the ocean. And people look at the ocean because of a few reasons. The ocean already takes up a lot of CO2. It's basically removing about 30% in the last 10 years. It removes about 30% of our annual CO2 emissions. And the ocean is the largest active carbon reservoir on the planet. It's so much bigger than the atmosphere, right? And the other thing is that the ocean is a big contactor. It has a very large surface for exchange with the atmosphere. And this is a view that most people aren't used to, but I'm in Hawaii and Hawaii is right here. So we're used to seeing this view. So in terms of these marine carbon dioxide removal techniques, there are a whole bunch of them that have been proposed, and I won't have time to get into them, but they can basically be broken down into biotic techniques that rely on photosynthesis to increase the CO2 uptake in the surface ocean, or abiotic techniques that tries to manipulate the ocean chemistry to achieve the same result. And the thing to know about marine carbon dioxide removal is that it's a two-step process. Any of those techniques that I showed earlier rely on first doing something to draw down the CO2 in the surface ocean, but that's not carbon removal yet, right? That doesn't do anything to the atmosphere. Carbon removal happens when that new state of the ocean equilibrates with the atmosphere. And in one scenario, the water that we've done the manipulation to stays in contact with the atmosphere and it takes up additional CO2. And that's great. In another scenario, the water subducts and doesn't see the atmosphere and it does nothing for climate, right? So it's important to figure out what happens. And the thing is that this happens over months to years. So it's difficult to track in the ocean, basically. So as Earth and environmental scientists, there are a few things that we can help with. One is something called MRV, monitoring, reporting, and verification. And that's basically checking how much CO2 has actually been removed from the atmosphere. But the other is environmental impacts. People are very concerned that if we do this to the ocean, there are adverse impacts. So MRV is very difficult. Monitoring marine carbon dioxide removal is really difficult because, well, the ocean is huge, right? So we do an intervention locally, but that signal spreads to an entire ocean basin, and that there's just no practical way to measure that. And then, like I said before, the ocean already takes up more than 10 billion tons of CO2 every year, just from natural gas exchange with the atmosphere. So there's this huge noise, if you call it that, on top of whatever small signal that we try to impose on it by getting it to take up additional CO2. And then the other thing is that it's impossible to measure a counterfactual, right? We need to know what would have happened if we didn't do the intervention. And so this necessarily means that we need a model to do this, right? And then there are still things that we don't understand about the ocean that makes it hard. So I mentioned that we need models before. So here's an example. There's a technique called ocean alkalinity enhancement, and that involves adding some chemicals to the water to get it to take up more CO2. And so we did a study where we broke the ocean up into these little polygons, and each of them we model what would happen if we put alkalinity in there. And I don't have time to go through the results, but if people are interested in exploring this, we worked with a nonprofit called Carbon Plan to visualize this. So you can look at each of these polygons to see, is this a good place to do this kind of intervention? So this kind of modeling could be useful for MRV, but we all know that models are full of bugs, right? And the question is, do they affect the results? So, to be able to trust the model, we wanted to satisfy a few criterias. One is, can it predict environmental variables that are important for the process, like the carbonate system measurements like dissolved inorganic carbon, pH, CO2, and so on, nutrient, salinity, oxygen, chlorophyll, etc. And it's got to perform well against observations that we can make. And then also, it can capture the relationship between things that it can predict, like nutrient versus carbonate chemistry. Lastly, I put this in red, which is, and it's because that's the thing that I'm currently working on, is that the models have reliable equations and parameterizations in them. And I'll just say quickly that when we run models, we usually run multiple models because no single model outperforms the multi-model mean. And it's also a good way to get at the uncertainties. So I'll just give you an example of parameterization. So gas exchange determines how quickly gases are exchanged between the atmosphere and the ocean. And usually these are parameterized by wind speed. So down here is wind speed. This is something called gas transfer velocity. And so there are these relationships that are used in global ocean models and climate models to predict how quickly the ocean takes up CO2. But it turns out in the coastal ocean, this is work that was done by a PhD student of mine that was funded by the National Science Foundation. It turns out that in the coastal ocean, it's very different than the open ocean, but the coastal ocean is where we are going to do these interventions. So it's really important to find out what happens in the coastal ocean. And right now we don't know, right? And so I actually just got back from a research cruise last week that was funded by NOAA at a body of water that's between the US and Canada. So this is the Olympic Peninsula in Washington State, and this is Vancouver Island. So we wanted to find out the same thing there, is how does the relationship between wind speed and gas exchange, how does it look like there versus some other place in the world? So I will end there. I'll just say that, there's a lot of work to be done, before we can know whether marine carbon dioxide removal is a viable climate intervention technique. And a lot of this requires government funding, not just in the hard sciences, but also in the social sciences, right? We need to know what people are okay with and the economics of it and so on. So it's really important that an organization like the National Science Foundation continues to fund social science in addition to the hard sciences. Thank you.
Awesome. Thank you so much, David, for that great and engaging talk. We've had some quizzing in the chat about the ocean being known as a carbon sink. Lots of folks concerned about ocean acidification. I guess one question I maybe have is, when we think about ocean acidification, a lot of us are also thinking about coral bleaching and things like that. Do you know if there's a way for, if you took some carbon or out of the ocean and had less ocean acidification, is it possible for coral to maybe come back to life after that? Might be a little bit out of your wheelhouse, but just a curiosity question.
Yeah, so I'm not a coral biologist, so I would defer that to somebody who knows. But I'll just say that adding alkalinity to the ocean increases the pH, right? So it counters ocean acidification in that sense. Carbonate chemistry is sort of difficult to explain, but sometimes people talk about the buffering capacity of the ocean, and that has to do with the amount of alkalinity that's in the ocean that allows the ocean to take up way more carbon than fresh water, for instance.
Awesome. Yeah,
Yes.
that's a great way to break that down for everybody. Awesome. Thank you. Another question. So you talked about some NOAA-funded field work you had just been on. What is some kind of day-to-day? What does the day-to-day of that look like when you're out kind of in the field looking at some of this?
Yeah, so for people that haven't been on a research cruise, basically your life is very regimented and simplified, right? Like you don't have to go shopping for groceries. You basically wake up in your workplace and you take shifts, like very defined shifts. And yeah, so it's like life, normal life, but much simpler, where you don't have the distractions. It's just you work, you sleep, you eat.
Yeah. Cool. Awesome. We have a little bit of a less serious question, a little more fun. Someone asked to explain the background, your little image background of some molecules in a box or escaping a box.
Yeah, so those are CO2 molecules. Depending on whether you're an optimist or a pessimist, they're either going into the box or coming out of the box.
Cool. Awesome. Let me see if we have any other questions. Otherwise, I have one. You mentioned a lot about modeling and specifically parameterizations of processes that can't be resolved in the model. And I was wondering if you could kind of break down what a parameterization kind of is to everyone.
Yeah, so I talked about gas exchange. Gas exchange is controlled by the amount of turbulence in the water, and basically at the interface, it's molecular diffusion, but you have to bring the water up to the surface to be exchanged. And so we parameterize it with wind speed because it's hard to measure turbulence in the surface water, but wind speed is so widely measured, right? We measure them from ships, from land, from satellites. So that's a parameterization, even though we know that wind speed isn't the thing that's controlling gas exchange. It does a good job of scaling with the amount of turbulence in the water and to an extent bubbles. So, yeah.
Yeah, that was a great explanation. Thank you so much for that. And with that, let's all thank David for his great talk as we continue on our 11th hour of the live stream. So thank you so much, everyone. Sound off in the chat. And so next, as we move on, we're just going to talk about why we are here again as we go to our transition to our next speaker. But if you're just joining or if you've been here, hi everyone, I'm McKenzie. I'm going to be your host for the next 2 hours or about an hour and 20 minutes more. And I'm really looking forward to it. We've had some great talks so far in this session. And so I just want to remind everyone why we are here. Also, you can see my cat in the background. Everyone was very excited about cats earlier this evening, but I think a lot of people have gone to bed. But I want to talk about how the US, our scientists here have been world leaders in weather and climate prediction research. We have some of the first computerized weather forecasts were developed here, as well as some complex models of the weather and climate. We also have a very vast observation network that ranges from space with satellites to airborne measurements, surface-based measurements, on land, as well as on boats, and even floats off in the ocean. And so all of this amazing research that's done here in the US is thanks to all of you, the public, because our taxpayer dollars is what funds our US federal funding, which is essential for our atmospheric research. And so, however, currently, I'm going to talk about a little bit the current proposal by the Office of Management and Budget, or the OMB, and how it would drastically change how federal research is funded. And just one example of that is when scientists are writing proposals and applying for funding, which is how we all get paid, or how faculty can have graduate students. Each program now needs to currently align with the administration's political priorities rather than the scientific need, which is now a historical shift since the original funding method that was put in place after World War II. And we've already seen negative impacts from these funding cuts, such as short-staffed weather forecast offices, as well as shrinking of weather and climate labs in academia and beyond, as well as, even research experience for undergraduate or RU programs that host summer interns in different departments across the US, including one in my department at the University of Colorado Boulder that was terminated just a few weeks before we were supposed to host a bunch of undergraduate students for a really fun summer of research. So we really do encourage you to visit our website, wclivestream.com, and to access all of our links on there, as well as share those with friends, family, everyone on your socials. We're encouraging you to contact your representatives and senators to protect our weather and climate research that's so amazing in our country. So our next speaker is going to be Jonah Bloch-Johnson, who is an assistant professor at Tufts. And we're going to be talking about NCAR letters and eventually some best clouds. And I just want to remind everyone that our speakers' views are their own and not representing their employers or any other institution. And with that, take it away, Jonah. I cannot hear you currently. Minor technical difficulties. Okay, I will stand here. Oh, come back. No, I still cannot hear you, but I don't. Yes, Phoebe is still saying me here. Claire might pop in, who was our host last segment. The last segment is one of the organizers. See in the chat, we got some love for Argo floats. We do love some Argo floats. Lots of fun going on there. Hi, Claire.
Hi, can
Welcome
you hear
back.
me now?
Yeah, I can hear you.
Okay. We are going to wait until Jonah comes back, but in this next segment, Jonah and I are going to be talking about your favorite topic, my favorite topic, clouds. And we have some fun, interactive things to do with all of you who are watching. So please stay on, get ready to type into the chat because we're going to be finding out what our collective favorite cloud is during this next segment. So before we get to that, we have an amazing video from Syl if you guys haven't heard, Syl is walking right now all the way from New York City to Washington, D.C. He is bringing all of the letters that you are submitting. If you want to send us a letter to share with your congressional representatives, go to wclivestream.com/write, and you can write your own letter to Congress. Syl will be delivering those letters to Congress on Wednesday, but he is taking the long road to get there. He has been walking for the past 10 days or so. He's got 2 more days left. He's somewhere in Maryland now, I think, but he's taken a bunch of amazing videos interviewing scientists along his route, as well as some really cool videos like the one we're about to show you, different fun atmospheric science facts. So let's play this video for all of you now.
Hello. Okay, let's try that again. Welcome to day 8 of walking 250 miles from New York City down to DC in support of weather and climate research. I wanted to share today a bit about the research I do, and what better place to do it than in the beautiful Chesapeake Bay, which we're standing in right now. So if you look out into the waters, you can see these choppy waves that are beautiful, but also play an important role in the weather and climate. As the waves break, tiny droplets are flung up into the sky containing bacteria, sea salt, and other particles. These particles both facilitating cloud formation and also directly interacting with light. Part of my research is to take data about these particles collected by satellite and use that data to help evaluate how good our forecast models are doing at representing them. With better representation of aerosols in these forecast models, we can be more certain about the types of forecasts we give regarding different emission scenarios to policymakers. So that's a bit about what I do, but if you have any questions, please let me know, and see y'all at day 9.
Okay, that was so fun. I love all of the content that Syl has been making. Let's check in with Jonah. Jonah is still not with us. That is okay. We are, I see already getting started in the chat with some of our favorite clouds. Please keep adding them. We're going to do a March Madness style bracket in a minute here when Jonah comes back. But in the meantime, drop your questions in the chat for me. I'm going to answer any burning cloud questions you have right now, live. Put them in the chat.
I have a question for you. What do you think is the least known cloud type?
No one asked this yet, but I'll share with you what my favorite cloud is. So if any of you remember, though I don't expect you to, last year I gave away the answer during my talk on the live stream. My favorite type of cloud is called a stratocumulus cloud. These clouds are kind of super boring to look at when you see them in the sky. They're the very, very flat clouds. They're very common if you live in Southern California, then you see them a lot. They're the clouds that we like to call May gray, June gloom clouds out here. Chat, are you hearing me right now? Or are we still having technical difficulties?
Can you hear me, Claire?
Hi, folks.
Oh, hi,
Can you hear me
Jonah.
now?
I can hear you,
Mackenzie,
yeah.
you can hear me?
Yes,
Okay,
I
maybe
can hear
Claire's
you.
the only. Okay, great.
Yeah.
Okay, well, thanks
Welcome.
everyone at home. We're having 2:47 in the morning technical issues, but the good news is we can in fact begin to ask you about what is the best cloud. So we have in the style of a bit of a March Madness situation, a bracket. Now, obviously, there are many, many, many types of clouds out there. And maybe Claire can hear us now?
I'm back.
Yeah. Can you hear us?
I can hear you.
Great. I can hear you. Okay, we're all good. So, welcome to this. We have these 8 clouds. So obviously, there are many different options out there This was selected in a very rigorous manner by me just thinking about what would be fun to consider. And we're just going to go through and consider some of these matchups. And what we could use in the chat is we're going to consider each of these matchups one by one, and we're gonna ask you to vote, and maybe we can talk a little bit about some of these clouds and what we think about them. So let's start with the first matchup. We've got cumulus versus lenticular, and McKenzie and Claire, I'm curious your thoughts on some of these. So I thought that in some sense, cumulus cloud is kind of like your classic cloud here. You know, clouds form because air. Oh, there we go. Is that the cloud again? This is the famous cloud again from Claire.
Cloud again is back. Cloud again is a cumulus cloud.
So there you go. You imagine a cloud. It's probably a cumulus cloud, sitting daydreaming, considering how they form. And you know, clouds form because you have air with water as a gas in it, and as that air cools, water likes to stick together, and so the water starts to condense out into liquid or solid form. In cumulus clouds, usually you have air that is rising, and once you get high enough in the atmosphere, the air gets cold enough that you start to condense out. We have a little bit of a movie showing some of this. So here's see these rising plumes of air, and they start to form these puffy cumulus clouds. They usually have flat bottoms because there is a place in the atmosphere where the temperature gets cold enough that you can start to condense out some of this water. McKenzie, Claire, do you have other thoughts on cumulus clouds? Any feelings about them?
Cumulus are the clouds that you see when it's a beautiful day outside. They are the nice puffy clouds that you see usually when it's still nice and sunny.
Yeah, cumulus clouds are what I think of just when I think of the word cloud. Cloud emoji, I'm thinking about cumulus.
There we go. Okay,
The cloud emoji is very accurate because it also has a flat bottom.
Mm-hmm.
Awesome. So there we go. It's a very iconic cloud. I think we can all agree on this. But then I see already there's a lot of love in the chat for lenticular clouds. In this case, over a mountain, these are clouds that form because of a disturbance of some sort in a flow of air that pushes wind up into a place where it's colder, and so you get this sort of continual entry of new air that condenses out water and then exiting, and the water kind of evaporates away. Here we have a film from 1929 showing a lenticular cloud over Mount Fuji. And so if you think about it, you're looking at a cloud that's almost 100 years old.
That's pretty incredible, Jonah. Where did you find this video?
I first saw it in there's a movie, The Cloud People, that was made by some folks over at the Max Planck Institute about their trip to Barbados that started with some of this footage. Masanao Abe, the filmmaker, has done a lot of interesting films about clouds. What do we think about lenticular clouds?
Aliens.
Aliens,
That's a
absolutely.
good comment in the chat. They are the alien cloud.
I see a lot of joy, a lot of positivity around those. Okay, we might not get through the whole bracket this segment, but luckily there's more time later on. Let's see what else what do we think between cumulus and lenticular? I see lenticular S tier. I think before there was a lot of love for lenticular. Yeah, hat cloud, good. I think that about sums it up. Okay, so we've got lenticular. Let's just at least do one more pairing. Let's talk about cirrus cloud. Cumulus is definitely underrated. One of you folks want to talk a little bit about cirrus? I feel like I don't want to hog all the cloud fun.
I think Claire is the cloud expert. I think you should go.
Okay.
Yeah.
I'll go for it. So to catch the people up who are just jumping back on, we are having a runoff of the best type of cloud. So we're going through one by one. We're telling you a little bit about each one, and then you can vote in the chat which is your favorite of the pairing. So up right now is cirrus clouds. Cirrus clouds are clouds that occur very, very high up in the atmosphere. They're made entirely of ice crystals. So that's pretty cool. Cumulus clouds, maybe we didn't say, but they're usually composed of liquid droplets, but cirrus clouds are frozen clouds. They tend to get very stretched out and wispy because the air up at that altitude is moving super quickly. Cirrus clouds are super beautiful. Some people say they look like a horse's tail or something like that. It's a good analogy that's made. Yeah, I see that getting some love in the chat. What else about cirrus clouds? We had a shout out early on in the live stream in Jen K's talk. Jen was showing the work that she did as a grad student, so a little bit ago, but she studied cirrus clouds during her PhD, so that's kind of cool. I got my start and my love for clouds studying cirrus clouds, so they have a special place in my heart as well. What is cirrus up against in this bracket? Ooh, stratus clouds. Okay, who wants to talk about stratus clouds?
So stratus clouds are interesting because some of these clouds are formed because air is moving into, is maybe being pushed or raised to some place where it gets colder, but stratus often forms in place. You have air that maybe radiates away some of its energy, or maybe it moves over a surface that's cooler and so cools down, but you just get this big layer of cloud, often very close to the surface. And in fact, fog is basically stratus cloud that is at the surface. So this is typically a nice big old layer of cloud droplets of water, and sometimes people compare it to pea soup. You can sometimes see big old pools of stratus clouds in valleys, especially in the Bay in California. What does the chat think about cirrus versus stratus? Kind of these two very different styles of cloud.
We're looking very one-sided here in the chat. Everyone is loving a cirrus cloud.
Okay, I think that, and maybe should we do one more? Or should we pause here before the hour? What do folks think?
Well, Jenna, I think we have to at least get to my favorite type of cloud.
Okay.
Bonus points again in the chat if anyone knows what it is.
Well, we might have to. Well, let's
I'll have to give the grand reveal. My favorite type of cloud are stratocumulus clouds. Stratocumulus clouds, those ones down there, they are similar to stratus clouds. It's the first part of their Latin name. They're these big, flat, blankety clouds, but they're also kind of puffy on top, hence the cumulus part of their name. So it's a little bit of a combination. These clouds are very prevalent over our ocean, which means that they reflect a whole bunch of extra light back to space, extra sunlight that would have otherwise entered our ocean. That's why, as they were labeled on that previous slide, they're Earth's sunshade. So they're really good at cooling our planet. So we love them extra. Give us some stratocumulus propaganda. Why are they my favorite? Stratocumulus clouds are my favorite because I spent 5 years studying them during my PhD. My thesis is about stratocumulus clouds. They're also my favorite because I did my graduate studies in Southern California, where we have a lot of stratocumulus clouds. I actually happened to be back in Southern California for the live stream. I'm here at a conference, and I woke up this morning, or yesterday morning, because now it's the next day, but I woke up on Monday morning and there were stratocumulus clouds covering the sky, and it made me very happy to get to see them again. So that is why they are my favorite.
So maybe we should pause here, but it's been fun to get to share clouds with you folks. And we will continue the cloud bracket later in the stream.
All right.
We'll see you guys later.
All right. Thank you, Jonah and Claire. That was a lot of fun. A lot of good engagement going on in the chat. So we'll keep that up shortly and continue that bracket. Next, we're entering our 12th hour of the stream, as it just changed now up here. So that's very exciting. Everyone spam the chat with 12s. Very exciting. So everyone, welcome. My name is McKenzie Larson. If you're just now joining us for our 12th hour, I'm a fifth-year PhD candidate at the University of Colorado Boulder in the Department of Atmospheric and Oceanic Sciences, and I love researching Colorado downslope windstorms. So if you were just here for the bracket, when we have these really extreme windstorms in Colorado, we often see those lenticular or UFO clouds. So if you want to see some more cool graphics of those and how they form, check out my talk. I was going to say tomorrow night, but I guess it is tonight now, at 10:40 p.m. Eastern time. And I'll be talking about those. So I'm looking forward to spending the next hour with you as your host. Also want to thank on the background end our directors behind the scenes. We're going to say goodbye to Phoebe. So everyone say thank you so much, Phoebe, for all of your help. And now we're going to welcome Ash as our new director for the next 2 hours. And so I want to remind us all why we are all here. And that's because U.S. scientists have been world leaders in weather and climate prediction research. We have had the first computerized weather forecasts. We also have complex models of the weather and the climate. We also have a very vast observation network ranging from space with satellites, go a little lower with airplane measurements and field campaigns, all the way to the sea surface with boats, land surface with just observational sites, can even have floats in the ocean as well. And so all of this amazing research and scientific advancement is thanks to all of you, the public, because our taxpayer dollars here in the US allows for federal funding of this research that is so essential for many of us here on this live stream and us in our field. But however, currently the administration's proposed budget for the fiscal year 2027 is jeopardizing this research and the scientists that conduct our atmospheric and climate science. Currently, there are proposed cuts to the National Science Foundation, or NSF, as well as NASA's Earth Science budget. Their proposals are to cut that funding in half. And a big question that I have, as well as many of others, are, how can we train the next generation of young scientists to better inform our weather forecasts and climate understanding if this happens? So for example, my PhD research is fully federally funded by a graduate research fellowship that I'm extremely thankful for, and is what has turned me into the scientist I am today. So we've already seen negative impacts from funding cuts, contributing to short staff weather forecast office, shrinking of climate labs and other research labs, as well as summer internship programs being canceled as well. So we urge everyone to visit our website for the weather and climate live stream at wclivestream.com. You can do /call on that link to contact your representatives and senators to protect our weather and climate research. So here we are now at 3 a.m. Eastern Time, and our next speaker is going to be Bob Berwyn, who is a climate science and climate policy journalist that's going to be talking about connecting the dots and seeing if there are similar concerns about cuts to science in Europe. And just as a reminder to everyone, all of our speakers' views are their own and they are not representing their employers or any other institution. So we might be having a little bit of technical difficulties. So I'm going to check to see what's going on over in the chat. Lots of hype for hour 12. Let's see. Can anyone say in the chat how long you've been here? Have you been here since hour 1? Very exciting. Lots of love for Phoebe. Phoebe's awesome. Popping me in and out of frame. Yes. You could take this time while we're figuring out some logistics in the background to visit our website, wclivestream.com, to write down those phone numbers of how to talk to your representatives, write them letters, send them emails. Okay, Fish got here around hour 4 to 6. Cool. Has there anyone came last year? I gave a talk last year, but I'm so excited to be here this year as a host, which is really fun. We have someone here since hour 3. Cool. Awesome. We might have Jonah pop back in. Let's see. Fish was here last year. Perfect. Awesome. Well, I just want to thank you all so much for supporting this live stream, for sharing it across social media, even just sending it to your friends and family. Every share, every like makes a big difference about spreading the message as to how, the current administration is making changes that impacts our weather and climate research here in this country. That's impacting a lot of us, especially younger scientists, that we have heard a lot about today in many of our various talks. And now we have Claire joining us.
Hello. I'm back. I thought that maybe you and I, McKenzie, could have a little bit of a chat while we work out some technical difficulties backstage with our next speaker. I wanted to know a bit more about you and your research. Can you tell our audience what it is that you study?
Yeah, so I kind of study a lot of things that I could talk about, but my main PhD focus is on Colorado Front Range weather. So in the state of Colorado Square, the northeast corner, we have a lot of complex mountain terrain right here. So I'm really interested in the interactions of our weather with the mountains, essentially. So I've looked at the big low pressure systems that move through here in the winter that bring us some of our big snowstorms and blizzards. I have used some machine learning. We talked about AI earlier. I've used some machine learning to kind of dive into the different flavors of those really large storms. What I'll be talking about tomorrow or today in my talk is our downslope windstorms they produce hurricane force winds where we all live here. So when we're talking about those fun UFO lenticular clouds, as pretty as they are, whenever I see those, I know that we're going to have some crazy winds that are going to probably take down some branches. We might have some energy cuts to try to reduce fire weather. So they're really important that we study those and forecast them better because they're still quite a bit misunderstood and they can be hard for weather models to simulate. And then I also had a wonderful opportunity to have an internship at the National Oceanic and Atmospheric Administration, or NOAA, here in Boulder, Colorado. And I've been working on some operational high-resolution model development, which has been something I've really found a true passion for that I would love to continue, which is why I would love for us to all continue funding this wonderful research that we all use every day when we're just looking at the weather.
That is super cool. I didn't know that lenticular clouds were a predecessor to these really severe windstorm events. That makes them a little bit less beautiful in my mind, but
they're really
but useful.
Pretty, very pretty in a picture snapshot. Yeah.
Yeah.
But yeah, you just have some air that's really trapped in there with the cloud kind of going through. But that means the layer at the surface has a lot of turbulence going on down there that we all get. So yeah, we had one in December of last year that I think got to 113 miles per hour measured at the NCAR Mesa lab, which is right against the mountains. So very, very strong winds. It's been interesting. Yeah, it's been quite
interesting. Very damaging.
Yeah. So yeah, I've enjoyed kind of studying them. And a lot of people in Boulder who've lived here since the 80s have noticed that the peak wind gusts seem to be decreasing. So currently my research is looking at how are these, future wind extremes changing along the Front Range? What are the mechanisms causing that? Is something that we're trying to answer to help everyone that's living here.
That is super cool. Yeah, and it seems really important for all of the impacts that it can have. You were talking about trees going down, power outages, but also ignition of wildfires, which is a really big problem in large parts of our country, but especially in the Front Range.
Yeah, some of the viewers might remember a fire that we had here in Colorado called the Marshall Fire. That was in December of 2021. It definitely made national coverage because when it happened, I was home in Florida and I saw it on TV and I was like, oh, I live there. But we had this really strong, persistent downslope windstorm for, probably like 6 to 8 hours, over 100-mile-per-hour winds and gusts. And a fire was ignited during it. And when the winds are that fast, there's really no stopping it. It's dangerous for the firefighters. And so there are about 1,000 homes destroyed. 2 lives were lost, quite sadly. So we're very concerned about winds and the connection to fire weather, especially now that our fire season is now kind of changing with our evolving climate, where now we don't really have a fire season anymore. It's kind of year round now. So it'll definitely be something to watch when the upcoming downslope windstorm season starts in October, especially because Colorado's in a pretty big drought right now as well. So
Definitely. I'll ask you a rather naive question, but when I was living in Southern California, we would have these events called Santa Ana winds. And is that just the name that we gave these downslope windstorms? And do you have a fun name for them in Boulder?
Yeah, so a lot of the winds get like localized names. So the Santa Ana winds are also downslope winds over in California. In Colorado, we have kind of like 2 flavors. Their like technical official name is called a Föhn wind. And we have kind of 2 flavors in Colorado. There's like a warm downslope windstorm that's usually kind of like before a cold front moves through. And that's known as a Chinook here. And then there's a colder version, which is a little less known once a cold front moves through. And that's called a Bora. So that's what we call them over here. Yeah. But there's these winds happen. They're pretty well studied over in the Alps, the Swiss Alps. And they term them as the Föhn winds, but they have some different flavors to them too. So they're all really dependent upon the local mountains and things like that. So it's quite interesting and a bit of a puzzle to kind of study these.
Yeah, definitely. And so the Santa Ana winds in California, they're also quite linked to wildfire challenges. And yeah, they were in large part responsible for the spread of the really big fires in LA last winter. Does that same sort of thing happen in the Alps, or is it too wet over there to have this fire problem?
Yeah, I haven't looked as much about fire season links with them, mostly on how I've been interested in how they've been modeling them and using these like large eddy simulations, and because they have like a lot of compute power over there and things like that. And I have not looked quite as much at that. Yeah.
Cool. Well, this is a fun comment from Fish about other downslope winds, like the ones in Antarctica, the katabatic winds. Are those the same sort of mechanisms, or is there something different going on?
They're not quite the same. The one in Antarctica, the katabatic winds, are more of this like gradual type gravity forced like downslope wind, whereas like here in Colorado and things like that, you have like a big mountain ridge, like a range, and there's a very steep descent going down. So you have this air that rises. You can have orographic precipitation or the cloud formation where you get like a rain shadow, things like that. And you get this dry air that descends and can speed up. So it's more like that. A little different, but yes, all downsloping winds.
Super cool. Well, it seems like, there's a lot of interest in the chat about wildfires, and totally understand why, because these are some of the most tangible climate impacts that we experience, especially if you live in one of these wildfire-prone areas, which, like you were saying, fire season is growing, but fire areas, places that experience wildfires are also growing. It's becoming a much bigger climate problem.
Yes. Well, also, as we've been talking about the importance of NCAR and how we don't want NCAR to be dismantled, there's a lot of fire research happening at NCAR. And it's all so important because it's all so complex. There are separate fire models that are developed specifically for that, and you can change, what the land surface looks like, or the fuel types of things as well. And it's a lot of complex interaction, especially when you're talking about winds and high turbulence. It's quite the modeling challenge. So it's especially important now as our fire weather regimes are changing, to continue supporting that research over at NCAR.
Yeah, definitely. NCAR does it all, right?
They do, and we love them. All right.
Definitely. So let's see what's going on with our speaker. We apologize, everyone, but there are some technical problems happening. Let's see. Oh, we got a great question here in the chat about fire management practices and controlled burns. This is not something that I know a ton about, so maybe, do you want to jump in on it?
I can try a little. I'm not a fire weather expert, but so the question is, have there been any discussion of something like controlled burns, or would that not work for whatever reason? So yes, these controlled burns are called prescribed burns, and we often have them more throughout the summer when we don't have like these big windstorms like here in Colorado. They're quite important to try to mitigate fire risk. But when these prescribed burns happen, they have to be in a very controlled environment almost. Like you have to be very confident with the weather forecast, which is also why it's really important we continue funding everyone who does this research. So that can help kind of cut out some of the fuel if there's a region that the local scientists believe can be an issue for fire in the future. You can have these prescribed burns and they can schedule them. And if all the weather conditions are right, they can burn a region, usually in coordination with like local firefighters, to try to put out some of that fuel so that it's less of a risk later. So prescribed burns are really great.
Yeah, that's a super important point. There's kind of these two aspects of the fire fuel source and the ignition source. And when we do prescribed burns, we're trying to treat the source of the fuel because we can't control what will ignite a fire. Oftentimes it's something like lightning, which it's just going to happen in our atmosphere. And if it strikes the ground and there's enough fuel there to burn, if it's dry enough, it's going to start a fire. But we can make that fire less damaging, less strong, less likely to get out of control and burn into populated areas if we reduce the fuel supply that it has ahead of time.
Yeah, absolutely. Very, very well said. Yeah, the other thing too, when you have a burned area or so, once you burn something, the region is called a burn scar now. And those can also be quite damaging. So when you have a fire and it's been really dry, but then all of a sudden you come into the summer months and you're going to get these big cumulus clouds, and you have really nice thunderstorms. When you rain over a burn scar, the ground can't really absorb the water as well, and it can't like catch on as many things. So that can lead to localized flooding as well. I think even like landslides, and so that's a whole other layer of that as well. So it's also important when there's thunderstorm warnings in the summer. The Weather Service forecasters, you can read their discussions online, and they'll have pointed regions of like interest of being like, okay, everyone be extra careful here. Do we need to have evacuations here if we're expecting a really strong storm over this region that's experienced a fire?
Yeah, that's a huge problem out in California for sure, especially in regions where these wildfires are occurring in very mountainous terrain, very steep terrain, very prone to landslides, which can oftentimes be more damaging to property and more fatal to people than the fires themselves. So definitely a huge concern, and another really important job of our weather forecasting service, of our National Weather Service, which is part of NOAA. Again, one of these things that we really rely on to keep ourselves, our property, our lives safe. And having funding cuts proposed to these agencies that are at their heart a public safety service for this country is very scary, and a big deal. That's why we're up here talking to you about the science, about the research, and about how it all gets done with your support, with your tax dollars. So I think we're ready for our next speaker. I'm going to pop off and get some sleep. It's great to see you, McKenzie. Good
Yes.
night, everyone.
Good night, Claire. Everyone, please thank Claire for all of her great work that's been done. All right, let's get on to our next talk. I'm just going to remind everyone again while we're here. I'm McKenzie. I'm your host. As we just talked, discussion with Claire about how important funding weather and climate research is for all of us in day-to-day lives when we might not even think about it. We know that the US scientists have been world leaders in weather and climate prediction over the past decades. We've had the first computerized weather forecasts. We are home to some of the complex models of the weather and the climate. We also have a wonderful observation network of satellite data, plane data, boats, and much more. And so all of this amazing research and scientific advancement is thanks to all of you, the public, because our taxpayer dollars here in the US are what allow for federal funding. And it's absolutely essential for our field. And one organization that we talked about, Claire and I just now, that is really at the heart of our weather and climate science is the National Center for Atmospheric Research, or NCAR. So some of the weather and climate models that we all depend on for our daily lives are developed and maintained at NCAR. You know, if you're just opening up your weather app and looking at your forecast that's shown on your phone, way in the back end, back there is likely a model that's been developed at NCAR that's providing the base forecast that you're seeing there. And I love NCAR. I spent a summer there after I graduated with my undergraduate degree that allowed me to help dive into more of the studies about Colorado downslope windstorm research, which I'm doing now and have a talk on at 10:40 p.m. Eastern tonight. And the time I had at NCAR with the folks that I met there and the collaborators that I'm now still working with today have absolutely shaped my career. Even though I'm just an early career scientist, I know that I would not be where I am today without NCAR. So I'm forever thankful for them. And we've already seen negative impacts from funding cuts. We've seen short-staffed weather forecast offices, which can lead to issues like we were just talking about fire weather. We've also seen shrinking and shuttering of research labs across the country, as well as some NSF-funded internship programs that have been terminated as well, which is really important for young scientists to find their way to what they want to do. So we encourage everyone to visit our website at wclivestream.com/call to contact your representatives and senators to protect weather and climate research. Without further ado, here in our 12th hour of the live stream, our next speaker is going to be Sanketa Kadam, who's an early career climate scientist and PhD student who's going to be talking about India's other monsoon problem. And I just want to remind everyone that all of our speakers' views are their own and they're not representing their employers or any other institution. So welcome, Sanketa, and we're so happy to have you here.
Hi, I'm so excited to be here today.
Awesome, thank you. Take it away.
Yeah, okay, so I'm going to talk about India's other monsoon problem, but here's a question to start with. When we think about monsoons in India, what comes to mind? It's usually heavy rainfall, maybe even flooding, streets underwater, now more so under climate change. And that's kind of the story that we always hear, but I actually wanted to flip that completely and talk about India's other monsoon. And then the major twist on all of that is that it's not about rainfall at all, it's about heat. And what actually happens when these little winter systems that we call the Western disturbances, one that they are very little known and not much studied, what happens when they just stop showing up. But let me build up to the why heat matters in spring season, which is what we're going to be focusing on mostly. Let me start with what is a monsoon, which I'm sure many of us know. It's the canonical reversal of winds that we see in the plots here, right? The winter, and I'm showing this as focused on India, but we see in the winter that they're away from India towards Arabian Sea, and then in the summer they're southwestern towards India, which bring rainfall and moisture, and this is the reversal of winds that we know monsoon as. And this whole system actually occurs globally, right? So here I'm showing you precipitation, which is the blue band. And so that's the maximum, the dark blue. And it moves seasonally is what we see. It moves to the north and it moves to the south. And this dark blue belt of rainfall is essentially what causes the summer monsoon and the winter monsoon in some parts of the world, right? And so what really drives the whole monsoon globally is this intertropical convergence zone that we just saw, which is this dark blue belt caused mostly by solar input. And it moves seasonally, causing, as you can see here in India, during the summer, you have monsoons, but in the southern hemisphere, we have, the other season of the winter monsoon, right? Like, so it moves around seasonally, essentially. But what I'm here to talk about actually is not the summer monsoon at all, which is the most, famous, more studied, more well-known. I'm actually here to talk about winter and spring monsoon, and it's a completely different system. There's actually two parts to this. The first is the retreating phase that we saw in the winter with the reversal of winds. So in the October, November, we see this India towards Arabian Sea sort of winds reversing, causing rainfall mostly to the southern tip of India. But the one I care about is the one that essentially starts from December all the way through March. And this is ruled by what I call the Western disturbances, or what we know in the literature as Western disturbances. And the paper by Dimri in about 2016, so he and his co-authors actually made the case that we should be labeling these two rainfall systems separately, one as the northeastern monsoon occurring in October and November, and then the December onwards as the actual Indian winter monsoon, which goes all the way into the spring. Now, Western disturbances, as you can see, bring rainfall to northern part of the India, cloudiness, but a lot of it over the Himalayas. They also form over the Mediterranean. So I'm going to talk a little bit about the actual system. So as you can see, they form here. Can you see my arrow actually? If I point? Okay, never mind. They form over the Mediterranean region and west of India, somewhere over Iran sometimes. And they are similar to extratropical storms. They, get embedded into the subtropical jet stream and then flow all the way to India from December to spring. Like I said, they bring snow, they bring much needed precipitation to Himalayas, they bring cloudiness, but they essentially act like an air conditioner for spring. So they keep your temperatures cooler, specifically surface temperatures cooler via cloudiness and rainfall, right? So why are they important? Why do we care about them, right? So they, like I said, keep surface temperatures cool, bring moisture from Arabian Sea, and also replenish Himalayan water and water systems. But why I care about them, especially bringing the heat wave lens into it, is what happens when they don't occur regularly. These systems, when they form over the Mediterranean and pass over India, every month they are cyclic. So about 6 or 8 of these on the regular in a month would pass over India. And of course, there are different features, right? Some of them are strong, some of them are not. Some of them go to the north sometimes, but on the regular, they come by in the spring over India about 6 to 8 times in a month, right? So what happens when they don't occur regularly? How are they linked to surface temperatures? What happens in their absence? What is that relationship, and how that relationship has changed under global warming? And this actually started, or my motivation for this started, is that it's not just academic. We had one of the worst heat waves that started in March and went all the way through April in 2022, which was the earliest we've ever had a heat wave in northern India. And this kind of got my attention also because it was unusually long. It was about 1.5 months. And it started in spring, and it actually landed right when wheat, which is one of the most important crops for Indian food security, was in its grain filling stage, we call it. It's like the growing stage of the crop. And wheat is extremely vulnerable to heat because it's a cold season crop. It's a winter crop. We plant them in November, December, and then harvest around April-ish, May, depending on the region. And so this heat wave not only had real health emergencies across North India because it was so long, it also, gave rise to a lot of debate whether the heat fed into India's wheat export ban, which occurred in that year, right after this heat wave ended. So, we feel it not only in hospitals, but also in harvest. And so it was a really important year for us to learn about spring heat waves and what actually happens or what gives rise to spring heat waves. So that is the map of where wheat is usually grown, which is also where North Indian heat wave hit the strongest. So I'm really going to quickly show you what I mean by its relationship with the surface temperature. So like I said, these systems, you can think of them as lows or cyclones, right? They form a wave. So there's a low, high, usually, and then they regularly pass over India. And so this is showing you a very typical sequence of Western disturbance, if you will. So what happens is usually when they pass over, you always have a cloud cover, and then they pass by, and then there's an absence. And in their absence, you'll have an anticyclone or a high, where you have clear sky conditions, subsidence, more incoming shortwave radiation, meaning that essentially your surface heats up. And then another Western disturbance comes by and it ends this, right? So you have more cloud cover and precipitation sometimes. So it wets the soil, it ends this heat accumulation, if you will. And that is kind of what happens on a regular sequence, right? And so our hypothesis is that if they don't regularly come in, and if there's a prolonged gap in their presence, you usually have this prolonged high that keeps building up, and this intense anticyclone means that there's more air subsidence, and that means that there's more surface heat accumulation, and then you have a very late relief by the time you have another Western disturbance come by, which is really late, and then you have this heat wave which accumulates at the surface. And so that is kind of what we found in our first paper, is that recently Western disturbances have been coming in less and less. They're also decreasing in their intensity, so they're much weaker when they form over the Mediterranean and they try to cross by. And this prolonged absence in the regular sequence is what helps the surface temperature heat build up and causes a heat wave, or one of the factors that helps in a prolonged heat wave during the spring season, which is supposed to be a cooler season. And so I really wanted to end with the projected activity or a future activity slide saying that this is fairly new research area and people have been actively working on understanding Western disturbances and their activity in the future. But this plot is essentially showing 3 different papers trying to understand what that means, the frequency of Western disturbances for different emission scenarios. The latest one, we see that they are decreasing in frequency. This means that the less and less WDs come into India during the spring season, the more intense heat waves we have or we might have in the future, along with obviously mean temperatures rising. And so I just wanted to end with that Western disturbances are cool and we should care about them because in absence of them, we have heat waves in the spring. And I think that was it. Questions?
Awesome. Thank you so much for your great talk.
Yeah.
It was really wonderful to kind of learn more about the different monsoon kind of aspects going on there. We currently don't have any questions in the chat. So I have some for you. I noticed in your last plot, you were showing some data from CMIP 5, which is a community model intercomparison project from the MCube lab to NCAR. I was wondering if you wanted to talk more about maybe your collaborations with NCAR and how that's kind of impacted your research or with model output you've been using.
I have been actually using CSM large ensembles a lot in my work recently. And like you mentioned, I feel like everyone has been through CSM or NCAR who's in our field and have had the opportunity to be there in person and learn so much from the community of people that are at NCAR. I also attended their CSM workshop last year, and it's just incredible how open data and everything is for anyone to use ever, and to keep that going is something we should be working towards. But it definitely, my entire second chapter of my thesis is based on like the CSM modelment and how well it does in actually replicating some of these dynamics in India and the spring heat wave.
Yeah, absolutely. Very, very well said. I agree with you that everyone's kind of gone through NCAR for something at some point. You mentioned like the community earth system large ensemble. I'm also using that for my research right now for my second chapter. So NCAR really is kind of at the heart. Maybe one final question to wrap up with. We have a question from Lila in the chat. Someone said, I know people have looked into weather modification before. Has anyone been looking into causing Western disturbances to help relieve heat waves?
I'm not really sure I understand. Has anyone been looking into causing Western to help relieve heat waves? Well, these, they do occur year long. They are kind of like cyclonic systems that occur year long, but they only are more intense and frequent in the winter season. So they're supposed to be only coming in hot, as you will, in the winter season is because they are embedded into the jet stream, and the jet stream is to the south in the winter season, and it's to the north in like summer and other seasons. So they're usually steered to the north and don't really come by India. So they only come across India in winter up to spring. So March is where we care about, is because they really keep or help keep spring temperatures cooler. So, they do really help relieve heat waves in spring. And so the fact that they're not coming in as much is what may be causing heat waves. That's what we found. But I don't think in other seasons it helps really much because they're to the north.
Yeah, that makes sense. I think we have one more question from Sydney, who's been very active in the chat. She asks, what makes India so vulnerable to heat in comparison to other regions? It seems like India is more susceptible to deadly heat waves than any other region, even in the tropics.
I don't know if it's the most susceptible compared to other regions in the tropics. You do have other countries facing really deadly heat waves too, but I think for India, different systems play a role, right? In summer, you have this massive monsoon system that impacts it so much. And because it's a global system, it's been like the most vulnerable due to climate change too. And so pre-monsoon, before monsoon occurs, before we have that relief, it's also just the tropics. It's just we have so much more solar activity and just accumulated heat. But I'm not really sure if it's more than other regions in the tropics. I feel like tropics in general are really going through it when it comes to heat waves.
Yeah, absolutely. Okay, awesome. Well, thank you for answering Sydney's question and for your amazing talk and for sharing your science and how important all of our research is. So we really appreciate it. Thank you and have a good day. I don't know what time it is for anyone anymore. So
thank you.
Yeah, thank you again. All right, we're going to move on now to our next talk, which I believe will be Bob. But before we do that, I'm just going to remind everyone why we are all here. This is my last 20 minutes with you all hosting until later this evening. But I'm looking forward to our next talk. I just want to remind everyone that we're here because U.S. scientists have been world leaders in weather and climate research. We've had the first computerized weather forecast. We have really complex models that are developed here, especially at NCAR that we've just talked about. We have a vast observation network, and all of this is made possible thanks to all of you, the public, because our taxpayer dollar is what allows for U.S. federal funding for this research. But currently, there's a proposal by the Office of Management and Budget, or the OMB, that could drastically change how this federal research is funded. One example is that when scientists are now writing proposals and applying for funding, to conduct research and to host graduate students, each program now needs to specifically align within the administration's political priorities rather than based on scientific need, which has been a bit of a shift. Because after World War II, there were kind of a specific protocol that was put in place for our scientific funding that is now being changed. So we've seen many negative impacts that we've already talked about today. So we encourage you to visit our website, wclivestream.com/call, to contact your representatives and senators to protect weather and climate research. And now, without further ado, our next speaker is Bob, who we're really excited to have after we had some technical difficulties earlier. Bob's a climate science and climate policy journalist at Inside Climate News. And he's going to be talking about connecting the dots to see if there are similar concerns about cuts to science in Europe. And just as a final reminder, all of our speakers' views are their own, and they are not representing their employers or any other institution. And with that, welcome, Bob. We're really excited to hear from you.
Yes, it's nice to be here. Thanks for your patience with my technical difficulties with the presentation like this, but I'm really glad to be here. And as you mentioned, I'm a climate science and climate policy reporter, and I'm based in Linz, Austria, which you can see on the screen there. In a frame that I took from a time lapse, which is a hobby of mine, which is photographing weather and climate related stuff. And I also use it for my work. And I use federally funded science nearly every day, and I've been using it for more than 20 years as an environmental reporter every single day. It's incredibly important and valuable, both professionally and personally too, because this sort of obsession with photographing weather goes back to my childhood and asking my dad 1,000 questions about why is there lightning? Why are there forests here but not there? Why do the seasons change? And of course, science answers all these questions and translates well into the type of reporting I do for Inside Climate News. So I usually start my day by taking a tour on windy.com or a website like that and just looking at the overall global climate picture. So again, the science, the resources that are available through satellites are amazing. And as I do that, I like to look at webcams of places that I visited or reported from. And not only that, I worry about, because I cover changing climate patterns, I worry about places that I visited, like this oak seedling area that I found a few years ago after a couple of wet years. And then after a few dry years, I'm wondering, wow, are they still thriving? I wanted to talk a little bit about how I translate some of the science and research into stories for readers in a way to make them, resonate and hopefully give people a little deeper understanding of how our Earth systems work. And so I look for new studies that are interesting, that relate to how parts of the Earth systems, forests, for example, are changing. And when I find a study that seems important, they're all important, but that seems really relatable and translatable, I start to reach out to the authors and I try to interview one or two of them. This is Alyssa Kohlberg at the ETH University in Zurich, and she recently did a very detailed study of leaf physiology and leaf response, individual leaf response in a sort of a controlled lab setting. And after speaking with her and her co-authors and several other scientists who study related things, I wrote a story about how forests may start to decline and die, starting with changes one leaf at a time. And that's sort of how the process works. And to explain it a little more, I want to go back to the US and take you to a place in California called Mono Lake. It's in the Eastern Sierra. It's a salt lake. And part of my path toward reporting on climate science started here at Mono Lake when I was an intern with the Mono Lake Committee in the early 1980s. And the reason I wanted to share the story that I wrote about this place is because it's just such a great example of how science can really make a difference. The Mono Lake Committee was founded by scientists who were passionate about the ecosystems there, about the birds that were in trouble because of changes to the ecosystems from, at the time, the main concern were water diversions. And then over the last 40 years, climate was added on top of that. And I had just finished studying political science. Even though my interest in nature was really great, I decided to do that. And I got to Mono Lake and spent a lot of time with amazing scientists who were studying this ecosystem. And it was just a great experience to be out in the field with scientists who were looking at brine flies and observing spadefoot toads in the desert at night. And as interns there, we helped band gulls and spent nights out on these tiny islands out in Mono Lake. And it just really shaped my worldview. It became much more relational rather than transactional. I felt part of what was going on instead of distant from it. So I went back there in 2019, about 40 years later, to take a look and to see what had happened. And because of this initiative that was started by scientists, there's a huge ecosystem restoration project going on in the Mono Basin. Some of the degradation was reversed. The threat from climate change continues. But there is a mandated ecosystem restoration target and millions of dollars being spent each year to rebuild streams, and it's all completely science-based. These are a couple of the founders of the Mono Lake Committee: David Gaines, who was a biologist and ornithologist, and Dave Shuford, who you can see there banding a gull, and who I was able to interview again when I went back to write the story in 2019. So I think I'm probably getting close to the end of my time, but I'm not sure. I don't see a message in the chat or anything. So I'll just go through a couple of the rest of the slides and once again highlight how incredibly valuable the U.S. science enterprise is, and to what I do and to what all my colleagues do, and all other climate and environmental journalists that I know and that I work with. Here's just a beautiful restoration scene at Mono Lake. And I use these resources to try and tell stories and take pictures and make people care and make people understand these things. I think basic eco-literacy is hugely important. And if you don't understand how the world works to begin with, it's hard to understand how it's changing. And again, the science that we have available to us very publicly really goes a long, long way toward doing that. So thanks to all the scientists that preceded and are following me in this live stream. And I think I can end there now, if that's okay. And I'm happy to take questions. And you mentioned initially, oh, that's right, I was going to talk a little bit about Europe. It's difficult to make an apples to apples comparison because political systems are different. In general, the situation doesn't seem as serious here, although there was just, where I live in Austria last week, a big university-wide protest about cuts to the entire university system that were seen as a threat to science and research, and people raised similar concerns about sort of a missing generation. You know, just when you close the door, even for a couple of years, it just puts a chokehold on the pipeline of academic and science work. All right.
Awesome. Thank you so much, Bob. That was a really, really great talk. A nice kind of different from the style of talks that we've been hearing earlier today. So we all really
I listened to when I got up for quite a while. I saw David Ho, who I really like and who I've met, and I realized it would be quite different. I hope that was okay. But
absolutely. I think it's really great. we're really happy that you were able to talk to us about everything today. And we actually do have quite a few questions for you that we'll get going for the next 6 minutes. Lila asks, how do you balance not coming off as alarmist when speaking about climate with getting the average person, I don't know where it went. Oh yeah, to take climate change seriously?
Well, I think I use science in all my, in all my discussions with friends, with acquaintances, in my reporting. And so I don't see anything that is scientifically founded as being alarmist in the sense of, overreacting. I also try to tell people that there are solutions. We know what to do. So we don't have to panic. We just have to sort of do the right thing.
Absolutely, yeah. Kind of a follow-up question to that Lila had was, are there any tips on, how to talk to your friends and relatives about climate change without being just crazy, which is definitely something, you and I have experienced here in the US, and talking to some of those relatives. Do you have any advice for that?
Yeah. I try to ask people how they've experienced things themselves and try to encourage them to trust their own senses and their own observations rather than saying, this is what I see, and wagging my finger. There are a few people that other people I try to focus on the economic aspects of it. And, I recall a discussion a few years ago with friends who commute a lot about encouraging them towards an electric car, sort of before this latest really big wave started, and tried to connect that with other things in their lives. And I try to stay positive. Again, I don't try to preach doom and the end of the world. I tell people, hey, yeah, things are changing really fast, but again, we know what to do about it, and we can act calmly and rationally and use all this incredible information that we have from science, and not just physical sciences, but social sciences. And this question relates to that. That's why I'm bringing it up. And as I've covered climate for 20 years, in the last 2 or 3 years, I'd say I've probably started talking to different types of social scientists at least 20 or 30% of the time, whereas before that I focused on glaciologists and forest scientists, because the human part of it seems to be ever more important. So keeping calm and not alarming people and not coming off as crazy is really important. That's the bottom line.
Yeah, good discussion. Yeah, it's also, these can be tough conversations to have with people. You can get a little uncomfortable, but it's definitely important to have them, for sure.
Yeah.
I think we have time for one more question. This one comes from Fish, who's been very, very active in the chat. How difficult do you think it'd be for us in the rest of the world to step up and fill in for the USA if America stops funding research? It's a big question.
It's a good question. I was wondering actually if there was going to be somebody in the live stream who was going to talk about the overall funding in the context of everything else that we spend money on in the world, and how small that piece really is. I don't have specific numbers at my fingertips, but a while back I reported about concerns, and I'm sure people have talked about this in ocean observations, and what it would take for other countries to step up and replace these monitoring devices that we need to understand the oceans. And I wish, if I'd known this question was coming, I would have pulled up some of those numbers. All I can say is it's not that much in the scheme of things compared to military budgets, compared to subsidies for fossil fuel developments, compared to a lot of other things. And it's more a question of political will. I don't think it's really a money issue, and that may just be my opinion. But I have looked at those numbers because it always amazes me when we talk about, $10 million, and I'm pulling that number out of the air to keep the ocean buoy system operating. And yeah, it sounds like a lot, but when you look at the cost of one, I'm just going to say it, one military device, and compare the two things, I don't think it's a question of money. So I think the rest of the world could step up. You can't just replace a whole system like the US science system by just all of a sudden stepping up, by all of a sudden. Yeah, it wouldn't just pop up, but other countries would have to say, and I think the EU is doing this to some level, hey, we need to continue our investments and if possible, strengthen them so that we have more distributed science globally, which is probably a good thing in the long run if it can be achieved.
Yeah, very, very complicated, intricate system going on, but yeah, good answer. Yeah. So with that, we're in our 13th hour of the live stream, so it's time to go on to our next speaker. But thank you so much again, Bob, for giving us a really great talk from a different perspective and for going through those technical difficulties. So we appreciate you and your patience.
Thank you very much.
Yeah.
It was really great. Yeah.
Awesome. Thank you. Awesome. Well, have a great day. Now it is time for me to pass on the hosting duties. We're going to welcome Jacob here. Hello, Jacob. Do you want to introduce yourself? Oh, 1 minute. Let's see. Making sure we're looking good. All right. Well, everyone, spam the chat with 13s. We have made it. Thank you all for sticking around. Good few of us on here. It's really great. We have a lot of folks in the background as well, too. All different time zones. We have Ash, who's our director currently in the background, who's in France, doing some research abroad right now for this month. We also have Jonah, who you have all met earlier, who's one of the organizers as well, is in the background here. Jacob, who's our next host, is having a few difficulties. So I'm going to introduce our next speaker. But first, I'm going to remind everyone while we are here, you know the deal. So I'm McKenzie. I'm a graduate student. I'm going to host you for this last talk here. But we're going to talk about how the U.S. scientists have been world leaders in weather and climate prediction, and currently our funding is at risk with our current federal funding situation and the administration proposed budget cuts. Here in the U.S., we've had the first computerized weather forecasts. We have developed complex models of the weather and the climate, especially at the National Center for Atmospheric Research, or NCAR. We have a very vast observation network ranging from space with satellites to airplanes to boats to observational networks just on the ground. And all of this amazing research and science advancements is thanks to all of you, the public. And that is because your taxpayer dollars are what allow for the US to have federal funding to fund this research in atmospheric science. But however, currently the administration's proposed budget for the upcoming fiscal year in 2027 is currently jeopardizing this research that our scientists could conduct. Currently, there is a proposed cut to the National Science Foundation, or NSF, and NASA's Earth Science budgets. The proposed cut is to cut those in half. And a big question many of us have, especially myself, as still a graduate student, we're asking ourselves, how can we train the next generation of young scientists to better inform our weather forecasts and climate understanding if this happens? For example, I focus on Colorado downslope windstorms, which is federally funded by a graduate fellowship that I'm extremely thankful for, and it gives me the flexibility and freedom to study what I'm really passionate about. And so we've already seen some negative impacts from these funding cuts, such as short-staffed weather forecast offices and shrinking research labs. So we really encourage all of you to visit our website at wclivestream.com/call to contact your representatives and senators to protect our climate research. All right, our next speaker that I'm really excited to introduce to kick off our 13th hour is Sophie Abramian, who is a postdoc research scientist at Columbia University, who is going to talk to us about storms wandering in the latent space. And before that, I just want to remind everyone that all of our speakers' views are their own, and they're not representing their employers or any other institution. And with that, Sophie, thank you so much for being here, and we're really excited to hear your talk.
Thank you so much, McKenzie, for the presentation, and thank you so much for the invitation. I'm super happy to present today to the Weather and Climate Livestream. So as you said, I'm a postdoc at Columbia University, but my research is funded across different institutions, first from the Department of Energy through a project about water extreme. I'm also based at Columbia University and interact a lot with people at New York University. And I am part of this institute, the LEAP, that try to gather tools from the machine learning and AI community and try to apply this to climate data and climate science. And this institute is funded by the NSF. So today I would like to present my current research that I entitled Storms Wandering in the Latent Space. So as you'll see, I'm studying mesoscale convective system, big storm that are responsible for main heavy precipitation in the tropics. So here we're looking at a simulation actually over the tropics, and each dot is a different storm, a different system that has been tracked by an algorithm. And using these tools, we can look at the storm during their whole life cycle. And in a previous study, what we did is that we tried to link the early stage features of storm and their maximal size, their maximal extension when they get the most intense. And what we demonstrate is that most of the information is at the beginning of their life cycle. So it kind of helped the forecasting, the nowcasting to determine what will be the heavy precipitation and the natural hazard that will be the consequence of this storm. But another thing that we've observed in this data is that sometimes a similar environment would produce distributed outcome, very different storms. And so we don't have a deterministic and a perfect tool to predict what will be the future of the storm. Instead, we need to look at the storm in another way, in a way that they are stochastic realization of the weather. And we know that there are other physical processes behind that allows us to better understand what will be the response of the storm. So in this project, my idea and our main concern is that given a fixed external condition, what is the possible range of the dynamical evolution of storm, and how can we characterize this? So to answer this question, I stepped back a little bit and used idealized simulation setup. So what I do is that I reproduce little atmosphere, but numerically. So I impose a low-level wind shear, and I let the convection, so the storm, develop. So this is a simulation. What we see is that with this shear that will constrain the convection to form pretty big storms, usually squall lines, we see that the clouds develop and then will eventually dissipate. And what we can see is that even though the constraint is fixed, the system will grow and then dissipate and then rebirth in another way. Sometimes we won't see anything for a couple of hours. And so we ran the simulation for like 30 days and see how the response in clouds change. And as I said before, what we want is really to characterize this variability. And the problem is that we can't really characterize a storm by just looking at them like that with our ice balls. The idea is that we need to monitor the vertical mass flux. So it's a technical word to say that we want to know how much air is pushed in the air and to what extent it will form a cloud and storm. And so to do this, we usually look at the cloud using this diagram. So I won't get into the details, but the idea is that you look how much air goes in the air or gets down, and to sort it through some energy level. And so if we look again at the simulation, we can see that it's the same time step. So we can look at the temporal evolution of the storm here using this simplified diagram that gather all the information about the mass flux. So based on this time series, we want to answer two scientific questions. So first, what are the different convective states for this constrained environment? And another thing is that how do systems transition from one state to another? But the problem is that even though we've simplified the way that we are looking at storms over there, it is still quite noisy and high dimensional. So we can't easily spot distinct modes or transition in this raw dynamic. So this is why we also leverage the Koopman framework. And in 2 words, the Koopman framework theory says that when you have a dynamical system that is described by a vector xt in very high dimension, and that this system is evolving in a non-linearly way with the function t, it will be hard to characterize the dynamic. So instead, the Koopman framework would suggest that we will transform the way that we are looking at the system. We will project this representation of the system using a function f that we call unobservable, and then we will choose this projection, this function, so that the evolution in time in this higher dimensional projected space to be more simple. So we can write it like this, so that when we concatenate the projection and the function that push forwards in time the system, we will have a linear evolution. So in other words, the challenge in this Koopman is not to understand directly the function that pushes forward the system in time, but instead to find a relevant observable that make the evolution simple and as simple as linear. And in 2 words, it happens that to find this right observable, to find this right function, it is eigenvector problem, a proper modes problem. And these observable are actually the modes of the Koopman operator that is formally defined as this. So in the past, people would handcrafted this function to find the best projection that will let the evolution linearly. But now we can use machine learning to learn this function and to make it easier. And how do we do that is we are using the concept of a latent space. A latent space is a reduced space that gather all the information of the system at the beginning, and that can be derived using an autoencoder, and that can be further constrained to meet and fit the requirement that we want. So in practice, I also will be quick on that, but we're using an autoencoded architecture. And in the latent space, we also further constrain the evolution to be linear. So we basically have 2 main loss, so the autoencoder loss and a Koopman loss. Another thing that we did is that instead of having a deterministic linear evolution in the latent space, we shifted to get a more stochastic evolution. So so to do this, we kind of partition the latent space and try to derive a transition matrix between different states in the latent space where the system can go. And then we have a probability of going from one state to another, rather than being sure that in the latent space the system will go in one direction only. So this is the technical part where we get the architecture of a model and the different term of the loss. And then we train this model and in order to understand and answer these two questions. So what are the different convective states for a given shear? So now I will not look at the clouds directly, but I will look at them through the latent space. And we can use a principal component analysis to understand how the latent space is structured. And so here we can see all the points. So one point is just one time step of our simulation. Oops, sorry. And we see that we have most of the points that are in this region. I don't know if you can see my mouse. But then we also know that for each point in the latent space, we have an associated cluster and an associated partition. And so we want to understand what is the physical interpretation of each cluster. Are there different storms? Are there different states through which, when we combine them, we will produce different storms? And so to interpret them, what I did is that for each time step, I said, okay, what is the mean precipitation over the whole domain? And what we see is that the mean precipitation is mainly correlated with the first axis of principal component analysis, meaning that all the instantaneous cloud snapshot would be sorted by their precipitation. Another aspect that I've looked is the organization index, saying that to what extent clouds are clustered together or they kind of are spread and evolve in a kind of popcorn way. And so here we see that the second axis of variability of the PCA is strongly correlated to the level of organization. And so based on these two components, the precipitation, which is kind of related to the life cycle of the system, and the other one that is the organization, we kind of interpret each cluster with different physical meaning. So the cluster yellow, the cluster 2, would be more associated with like the initiation of convection. The cluster 5 would be associated with developed convection with some rain area, but in a more unorganized way, a more popcorn way. The cluster 6 is the development of clouds, but in an organized way when clouds are clustered. And for instance, the cluster 3 would be also a part where clouds completely dissipate. And so how do we go from this state partition to storms? So in other words, how do the system transition from one state to another? And as an output of the model, we have a transition matrix. And we can look at random walk through this matrix. What we see is that the matrix is very sparse. So it means that there are some reduced number of admissible transition. And the other part is that it's strongly diagonal. So it means that the system also has a tendency of persisting in the states. And there are some mathematical derivation to get the different paths, but we can also play with this transition matrix and saying that if we start from the cluster yellow, the cluster 2, we can see that we have a chance to go to the cluster 6 with 3%. And from 6, we have a chance to go back to the cluster 2 with 9%. So we see that we have a first oscillation from initiation to organized system that will be fed. Another thing that we can do from cluster 2 is going to cluster 5, the green cluster. And from 5, we can go to the cluster 3, and from 3 to 5, and then to 2 again. So another thing is that some storms would have a different path and would produce different precipitation. And this study kind of quantify and characterize this. So if you also look at the time series of the system that we have, we really observe this kind of path that is not just an artifact of the matrix. And for instance, the very first video that I showed you really showed the development of a quite organized system under this environment. So to conclude, our objective was to characterize the diversity of convective evolution pathways under a fixed environmental forcing. And we were using a data-driven stochastic framework to do that. So we derive a 9-dimensional latent space to identify different clusters. We see that this latent space is physically structured by precipitation and organization, and that organized and disorganized storm, even under the same environmental forcing, would develop in distinct pathways. And this is also another thing that I haven't shown there, but we can also question and see to what extent we can really apply this Markov chain framework for convection, and it works well. This is it for me. Thank you so much for listening to me, and I'm happy to take any question.
Awesome. Great. Thank you for that great talk. That's really great. We have a couple questions that we'll go through, and then we'll introduce our next host. Mary has two questions, actually. Can you use the Koopman framework theory for all environments?
Yeah, great question. The Koopman framework is actually can be used to different environment, and this is actually the next step of our project. The idea is that you look at different forcing, different environment, and see to what extent the transition will change, and to what extent also the projection will remain the same. And a very incremental project would be just to get the same environment, the same shear structure, but then to increase the shear intensity and to see to what extent we promote one sort of storm rather than another one. So yeah, it's a good point, and it is meant to be applied to different environments.
Okay, awesome. That's really cool that it's adaptable. It's really great. Last question is also from Mary. Asks, what was the model prior to the development of Koopman framework theory?
The prior is to have data that are long enough, diverse enough, so that you kind of reach the ergodicity hypothesis, meaning that you have the temporal and the spatial derivative are the same. So the system has to visit all the states it can goes in order to apply the Koopman framework, because otherwise it would be biased. So the Koopman framework is really related to the ergodicity theory.
Okay, awesome, great answer. I think that's all that we have for that. Thank you so much, Sophie, for that really great talk. We all really enjoyed it, so thank you very much. So now for our next talk in hour 13 of live stream, I'm actually going to pass off the hosting duties to Jacob, who I think will appear here. Are we good on sound now?
Yeah, brilliant.
Yeah, do you want to introduce yourself?
Yeah, thank you for guiding us through the night so far. Yeah, my name is Jacob, and I'll be hosting the next 2 hours, 1.5 hours or so. And yeah, I'm as well a PhD candidate or PhD researcher, however you want to call it, at the Spanish National Research Council. And I'm also heavily using NCAR resources, and that's why I was keen to join this stream as well. Yes, that's mostly for me, I guess. Yeah, I'll be guiding, I think, hour 13 and hour 14, if I'm not mistaken. And first, I'd like to highlight again why we are here. So we've already done basically 12.5 hours or so. Probably not everyone has been here. Maybe now some are waking up because it's slowly becoming morning in the US as well. And before we go to some discussion of some letters that were written by scientists in the public to NCAR, or to Congress, and that are like physically transported there, part of them at least. So I like to highlight that the weather and climate forecast is very important for our daily life, which I think has become very clear for the last hours, and also that US scientists have been leaders in that field and are still to this point for the many years that and what I'd particularly like to highlight, because it comes a bit from my background, I guess, is that the diversity of people that actually are able to work at NCAR and the kind of diversity of backgrounds they can bring to this massive institute is really unique worldwide, not only in the US, I'd say. And for instance, what has been highlighted is the first numerical weather forecast in, I think, 1950, as well as the first computer models of the effects of CO2 and such things, as well as measurements and these big networks of buoys, of balloons, of many different things that are just not possible by one single university or any single research institute, but really needs such a large national institute. And this excellence really arises from public funding, which is essential to enable such non-political, such really purely scientific for the public good research. And as you've already heard, this funding and this research is under threat currently due to already staff shortages at weather stations, but as well as shrinking and cuts in funding to climate labs and other things. So this is even more highlighted by the the US administration's proposed budget for the fiscal year of 2027. So, which basically wants to cut the National Science Foundation's budget, as well as another Earth Sciences budget in half, and basically not only eliminates many of the research, but also kind of gets rid of all the expertise. I think that's been highlighted for the GFDL part some hours ago, I think last evening for me, that really they got rid of a lot of that expertise that accumulated over all those years. So that is really something that is not easily or quickly to replace. So it's really an important thing to do. And beyond that, since I'm also an early career scientist, these foundational programs for young scientists are really important at any time, because that's how the next generation learns. And for that, you really need these big institutions. And beyond these budget cuts, what I've already kind of hinted at a bit, the administration is trying to effectively dismantle this big NCAR institute, which we're going to hear a bit more later on, but also heard from Professor Jennifer Kay in the very beginning about what NCAR is and how it's connected to UCAR and all these complicated acronyms that really do a lot of good that is maybe not known by everyone in the public. So we really urge you, are hoping that you help to defend weather and climate science as a essentially public good, not only in the US, but it's really a global aspect to defend and to care for. So we hope that you use the link that is shown here in the live stream, the wclivestream.com/act, to contact your members of Congress and really tell them that you care about these institutions, because they matter for our daily life, and tell them basically to fully fund not only NCAR, but NOAA, NASA, NSF, and all these other agencies that really are only there for the public good and for nothing else. So the decisions are made right now in the House and the Senate, and we've already heard about some judge rulings some hours ago, but there's still important work to be done, and you can really make your voice count in the next hours and days to come. So, and last but not least, I'd like to highlight that all the speakers' views are their own, and they don't speak for any institute, but really for themselves, which really shows how people care about what is happening. So with that, I'd like to kind of introduce a bit different slot now. So the next two speakers, or people who will discuss, will be Jennifer Kay, a professor at the University of Colorado Boulder, which we've already heard from before, and Jonah Bloch-Johnson, professor at Tufts University, and they will be sharing, I believe, some of the letters that people, and especially scientists and whole research departments essentially, have written about NCAR. And that, take it away.
Thank you so much, Jacob. Can folks hear me all right?
Yeah, it's great.
That was a great introduction, and absolutely, I think, you know, this year one of the big reasons that we're here is NCAR. You know, among the funding cuts, among the OMB rules, you know, what's happened with NCAR is really, I think, galvanizing for all of us. I just wanted to share. I know it's, you know, here it's 4:29 in the morning. Syl, who's, you know, been walking from New York City to Washington, D.C., actually continued his walk into the night. I can just share this video really quickly that was just taken by Miriam, where you can see this is him at the end. This was just taken like an hour ago or less. He's unstoppable. I just wanted to share that little spirit of energy that's going on out there. But yeah, you know, I think what happened with what's going on with NCAR, that threat NCAR has been facing is, I mean, it was so unimaginable. I think when we all heard about it, or because many of us were at the AGU fall meeting when this was all announced. I think that Jen, you were, we talked at quite a bit at AGU, and I don't know if you remember the moment. Do you remember when first hearing about it?
Yeah, I mean, I was just out to dinner with some friends, and somebody said, "Oh, I think there's a article in the newspaper that says NCAR will be destroyed." And I was like, "Well, what is the newspaper? You know, I don't know. This just sounds like a rumor. This can't really be true." And then within 24 hours, everyone was like, "Wow, they've been planning this, and it's just an attack." And there's no logic, there's no scientific reasoning behind it. It just seems kind of hard. Like, what do you understand what this institution does and how important it is to so many people, to our country, to our national defense, to our economy? I mean, it's just like crazy to say to a reporter, and that for that to be the way that you share that you're destroying this institution that's been around for 60 years. Like, through many different politicians, many different governments, there's been long support for this and long benefit from it. So yeah, it's hard, and still hard now.
Absolutely. And so I think it would be great to share some of the responses. You know, this was first announced as just I think it was just a tweet, right? Was the first thing that came out, something like this from someone in government. But then the NSF put out this Dear Colleague letter soliciting plans to saying, you know, if you're some entity, if you're a university or in private industry, you know, how do you want to carve this thing up, pretty much? You know, how do you want to make use of this thing? And so, you know, as part of a Dear Colleagues letter, you have to solicit public comment. And so many people wrote in, and the NSF announced they weren't going to share the letters that people were writing to them. And so we here at the Livestream decided to put together this site, which I'm just going to put up. This is, if people are curious about this, it's at oops. This is the website that we're looking at here, wclivestream.com/save-NCAR. And there are many letters here. You can see dozens of letters from individuals, from universities, from different organizations, from many people who worked at NCAR in the past or at NSF. And we thought that it might be nice to take a moment to read some of these letters because people really put a lot of thought into them. And we're going to start in particular with a letter from maybe a surprising group, the American Academy of Actuaries. So I'm going to load this up on the screen. Give me just one sec.
And Jonah, you're still collecting letters, right? Like if people still have them. I mean, we heard there were close to 1,000 letters submitted, and we have a subset of them, 56. And so, if you have a letter that you submitted, or, we could also put additional letters, I guess, up there. I don't know. That's for you all to call. But I think part of demonstrating the value of NCAR is kind of stating its value in plain language and from multiple angles. And that's what these letters do.
Absolutely. And I want to also say that as part of the walk that we're doing, so we have, if you have letters that people have submitted on to the NSF for NCAR, we will post it on our page, but we also are soliciting letters to Congress. And I don't want to be too confusing because I know we're saying people are calling the representatives, but this is another opportunity. If you go to wclivestream.com, all of this is explained and made clear. But if you have thoughts on NCAR, because really it seems like this is maybe our best chance to really protect NCAR, is to make it something that is in legislation, make it something that Congress is doing, because it's clear that some of these agencies are moving towards maybe a more aggressive set of choices around how they want to issue their funding. So we really need the protection that could come from legislation from Congress. But let's take a look at one of these letters. And I figure maybe Jen, should we just alternate paragraphs? Do you want to take the beginning?
Sure, yeah. So this is a letter from the American Academy of Actuaries, and it's written to the acting director of the National Science Foundation. So the acting director, dear Acting Director Stone, on behalf of the American Academy of Actuaries, we appreciate the opportunity to comment on the announced plan to dismantle the National Center for Atmospheric Research, or NCAR. Public reporting indicates the National Science Foundation will break up NCAR and relocate vital activities, in quotes, a course of action that, if implemented, would remove a cornerstone of the nation's open scientific infrastructure for tracking and understanding weather and climate risk.
NCAR's continuity is not only a scientific necessity, but an economic one. NCAR's shutdown would eliminate rigorously curated, public and scientifically grounded resources that the American insurance industry relies on to understand systemic climate risk and safeguard consumers. Actuaries utilize NCAR's datasets and community climate modeling frameworks to benchmark and validate catastrophe model outputs to support pricing, reserving, and capital adequacy analyses that underpin the financial soundness of insurance markets. You might not expect that this connection is there, but here it is. These resources are also relied upon internationally by insurers, reinsurers, and catastrophe model developers to analyze extreme climate-driven risk scenarios across regions and inform cross-border capital allocation decisions. Given the global interconnectedness of insurance and reinsurance markets, disruption to NCAR's infrastructure would propagate well beyond US borders. We urge actions to maintain the continuity of NCAR's datasets, models, and guidance so the insurance ecosystem can continue to price and capitalize responsibly, which is necessary for a healthy insurance marketplace.
So NCAR has long supplied the foundational capabilities that enable catastrophe modeling and climate-informed pricing and reserving in the property and casualty insurance sector. Any disruption to its operations would materially degrade these capabilities, heighten uncertainty in risk assessments, and undermine the stability and affordability of U.S. coverage for U.S. consumers. Without the critical information NCAR provides, insurers would be critically challenged when accurately pricing and offering coverage, leading to significant affordability and availability challenges nationwide.
Actuaries apply professional judgment based on available and well-tested data and models to evaluate low-frequency, high-severity events, as well as long-term trends that affect insurance markets and consumers. NCAR's work supports the actuarial profession's ability to assess and manage financial risk by offering credible, consistent, and well-documented information. NCAR's publicly available datasets, community climate models, and scientific guidance have historically provided a common, transparent foundation for these analyses across insurers, regulators, and other stakeholders. The following considerations describe why disruption or loss of NCAR's resources would introduce additional challenges for financial risk analysis and decision-making.
So for catastrophe modeling, developing accurate models and assumptions for insurance and financial security requires that actuaries use reliable and relevant data. NCAR's data sets covering atmospheric dynamics, climate variability, and extreme event frequency are particularly foundational to the catastrophe models used in property and casualty insurance. So I'm assuming that's like home insurance and life insurance.
Without that, yeah.
Without these resources, the insurance industry faces increased uncertainty and greater challenges in accurately assessing and pricing risk. And I just want to say, you know, uncertainty usually translates to higher prices because people don't want to take that uncertainty. So they just increase the prices to reflect that uncertainty.
So, trend analysis and long-term assumptions. Actuaries incorporate historical and projected climate trends into pricing and reserving assumptions for insurance contracts and capital adequacy assessments. It's really interesting to me how the insurance industry, it seems to be one of the few industries to really take climate change seriously. But if someone has if anyone's going to have a long time horizon, I suppose it's the insurance and reinsurance industries. NCAR's research enables actuaries to evaluate changes in hurricane intensity, certainly, wildfire spread, as we've heard in some earlier talks, and precipitation patterns, factors that materially affect loss costs and risk margins. Discontinuation of NCAR's work compromises the ability to set assumptions that accurately reflect emerging markets.
So correlation and systemic risk assessment. Climate-related risks often occur together across regions and insurance lines, amplifying the potential for widespread losses. NCAR's integrated climate models help insurers anticipate these interconnected risks and extreme scenarios, enabling stronger financial resilience and more stable coverage for consumers. Without these tools, the industry risks underestimating total exposure, which could lead to inadequate capital reserves and higher volatility in pricing and insurance availability.
Now, this is one I think is really interesting for, I think, some stuff that I remember talking to Jen about before. Public access and market stability. NCAR's open data framework promotes transparency and consistency across insurers, regulators, and policymakers, reducing information asymmetry and supporting fair pricing for consumers. The fact that NCAR is a community resource is, it's not just that they build these models, it's not just that they do all the scientific research that then, maybe makes it into some papers that you have to be an expert in to go and dig your way through. I feel like NCAR produces all of this, these tools that they then try really hard to make easily accessible to people, to make to make well documented, to serve as a meeting place for people, for people who are trying to do analysis and do science in this very sort of inviting way. And it's really amazing to me to just realize until I read this letter, or I'll could read in a second, but I didn't realize what a big role NCAR was playing for this entire industry.
It doesn't surprise me. I mean, I have an economics degree undergrad. I actually worked as an economic consultant for a year. And, these kinds of resources that are public and vetted and trusted and put everyone in a common framework, that's just essential for economic stability. And so I imagine even though the actuaries wrote, there could be other industries too that are using this. And it really suggests, if you privatize things, if you change things and you don't have kind of a stable, dependable, publicly available voice, it kind of pulls the rug out of any kind of economic stability around certain markets. And that's really scary, actually.
Yeah, it's very scary.
And I think even like what was highlighted yesterday in the AMS panel, that such things as where do you deliver your parcel from? Do you deliver it from Chicago or do you go from San Francisco? Such things, like even such day-to-day kind of things that happen every day, they are essentially linked to these models and to their forecasts, essentially.
That's a really good point. Yeah, it's amazing what you can do when you have these sort of consistent and reliable resources, and the disruption would be, market instability does not sound good.
From days to decades. And also, there's always going to be some market instability, but this is something that's well in our control. It's not expensive in the relative budget. And so it just seems like a no-brainer to keep it and keep the stability. So
yeah, let's see what else that is. I think we're getting through this.
Yeah, we delved into commentary here. Thanks for joining. That's great.
Yeah, absolutely. If you want to participate too, you're very welcome to. Do you want to take turns with us, Jacob? Would you be up for that?
That's fine. I can do that. Sure.
Sure. Okay. Well, I'll finish this paragraph and then maybe Jacob, you can go. Without NCAR, reliance on proprietary or fragmented data sources may increase volatility in insurance markets and reduce confidence in actuarial projections. With less availability of data and uncertainties about risk exposure, fewer companies may choose to enter or remain in markets, leading to availability challenges for customers.
NCAR and non-governmental innovation. NCAR has been an active participant in the creation of industry university cooperative research centers sponsored by the National Oceanic and Atmospheric Administration. So that's essentially NOAA, if I'm not mistaken. And the National Science Foundation, which is NSF, we've been talking about the whole time. These centers bring together academic researchers and industry data users to develop innovative products, enabling the insurance and reinsurance industry to better assess climate-related risks. Without NCAR, the centers will experience data gaps and diminished modeling capacity and expertise, which I think was also highlighted some time ago, perhaps also in the AMS panel. I think I'm taking a lot out of that by all this expertise of years kind of working at this institution, just kind of leaving, not just people leaving, and you can't just rehire them, but the expertise leave with them and their experience, really. And this would likely result in fewer innovations and less useful tools for assessing climate-related risks.
In addition to these concerns, it is important to underscore the fundamental economic relationship between uncertainty, price, and availability in insurance markets. In all financial arrangements, uncertainty carries a positive cost. Just as equities command higher expected returns than bonds, greater uncertainty in forecasting insurance losses increases the risk load or margin required for insurers to offer coverage. When the scientific foundation for understanding natural hazard risk is weakened, insurers must assume a wider loss distribution, and higher tail risk, which translates directly into higher premiums for consumers. Beyond price, the availability of insurance depends on insurance confidence in their ability to understand and manage risk.
As uncertainty grows, some insurers will reduce exposure or withdraw from high-risk areas altogether. Eliminating or degrading key sources of climate and weather information also makes it harder for communities, developers, and policymakers to determine the appropriate level of resilient construction and land use planning investments that are essential to ensuring long-term availability and affordability of insurance coverage.
We strongly encourage the NSF reconsider its plan to dismantle NCAR, as doing so is very likely to negatively impact the industry, insurance coverage, and outcomes for the American public.
If you have any questions or would like to discuss these comments further, please contact Will Benke, the Academy's Policy Project Manager, Risk Management and Financial Reporting. And this letter has been signed by the leadership of the American Academy of Actuaries. So the 2 vice presidents for Risk Management and Financial Reporting, Practice Council for Casualty Practice Council, and then the chairperson, who is the research committee from the American Academy of Actuaries. So yeah, this letter really underscores the importance, for someone in the US, probably in the world, trying to buy a house and to get insurance on it. Or, if you're not buying a house, maybe you're renting a house or renting an apartment, but whoever owns that apartment still needs insurance on it. And if they pay more for their insurance, they'll probably pass those costs along to you. So yeah, this positive price, they had some very kind of economic words to say the prices are going to go up. Yeah, I think that was basically the bottom line there. Was that your take too, guys?
Yeah, and I think one aspect is the open access part, which is, I think, a bit underappreciated, because many big groups or big institutes that develop such a massive model, such as the CSM model, like their community Earth system model, where the name really says all, I guess, which is not only open access, but I think even the development stages can be accessed. So you can clearly see why these decisions to develop it in the way that is developed are done, and it's really transparent to the public. If I'm not mistaken, it's even available on GitHub if anyone is interested, which is quite neat, I think.
I see we actually have a question. Maybe we can put this up from Sneelinquist. Can you volunteer with NCAR? That's a good question. Jen, do you know if someone can volunteer with NCAR?
Yeah, I guess it depends on the capacity. I would say one way you could volunteer your time is, by calling Congress right now and asking them to put protection for NCAR into law, and volunteering your time to become more informed about NCAR, which clearly this question asker, Sydney Lindquist, A243, has already done. I think locally, we typically have opportunities, but they're more in kind of the public outreach and education parts of NCAR. So, for example, NCAR hosts every fall something called Super Science Saturday, where a bunch of kids from all over Colorado, I guess from anywhere, if they wanted to come, if they wanted to fly in for Super Science Saturday, they could. But it's like a full day of talking about science to kind of kids, and they put on a show and have a bunch of demonstrations and things. And that, requires a lot of volunteers. So I personally have volunteered for that before. In terms of science, there's a lot of opportunities to get engaged in community modeling. So, that you wouldn't get paid for that. So, for example, if I came with a new idea for how to represent rain in the atmosphere, I might be funded by another entity, like I could be funded by a National Science Foundation grant or Department of Energy. But if I come and I have this idea, I would have to do some volunteer work to get it into the NCAR community models. NCAR doesn't pay people in the community to put their information into the models. Most people do it because they want their information to be part of the broader ecosystem to survive past that. So sorry, that was kind of a long-winded answer, and I don't know if I really got at it. Yeah.
Yeah, I think maybe like to go back to this outreach part. I think especially the outreach part is quite important also to get young people excited about atmospheric science and about research. It's essentially when you go outside as a kid, that's the first thing you see. You see the clouds, you see the sky, you're curious why they work the way they work. You may want to see, I don't know, why they have the structure, which maybe as a kid you first assume is some kind of animal or you see something in there. But even from the start, I think like you immediately get excited and interested in this kind of stuff. So I think these big institutes, they can really pull off such a I forgot the name, but this Science Saturday or what it was called, or Super Saturday or so. I think like these big institutes, they can really like make this these open door days or outreach activities.
Well, I think those all sound like some great opportunities. So thanks for that question. I think we can also, I think it would be great to at least look at one other letter that I feel like looks at NCAR, but from a very different perspective. But coincidentally, so I think we saw that at the end, Jen, you read that the person you should write to at the Academy of Actuaries is this Will Benke. And this is a letter from someone named Richard Benke. I don't know if they're related at all. This could just be a coincidence. But you'll see here, maybe, Jen, do you want to start this one? And
yeah, you make it a little bit bigger. Sorry.
Yeah, let me make it a little bigger. Sorry, no worries. How's that?
That's great. So here we go. Dear NSF, I worked at NSF for over 40 years. The last 30 years, I was head of geospace and spent 2 years as interim director of atmospheric and geospace science. I know NCAR and its importance and capabilities well. Simply put, NCAR is critical to the advancement of both atmospheric and geospace science. The center employs many of the world's best scientists in their field who, working together in impressive groups, are responsible for key weather and space weather research advances. NCAR also provides the leading edge facilities, such as, and a couple of aircraft are named here, the Solar Telescope and a highly regarded supercomputer. Provides these leading edge facilities not only to NCAR scientists, but to the entire atmospheric and space science community. These facilities underpin and make possible future breakthroughs in understanding and predicting hazardous and dangerous weather and space weather impacts.
I mean, maybe just, I don't know if we have had any space weather talks in the weather and climate live stream. Maybe people can correct me if I'm wrong about that, but that is actually also a whole other can of worms to be aware of. Is this something that either of you have any experience working with or thinking about?
I mean, I'm definitely aware of NCAR's work in this area and how critical it is, for example, for GPS and for navigation, just because if there's going to be some sort of storm that affects those assets, that can be a huge disruption, back to the package Jacob was talking about and how it was traveling. And, if we don't have the weather both in the lower part of the atmosphere and the upper part of the atmosphere, your package is not going to arrive to you.
Yeah, I think at least what I know from the especially NCAR and Wacom models, and these models, they have quite high model tops, meaning like they go quite high up in altitude. So you can really go to the upper atmosphere or like the high atmosphere, depending on who you're talking to, I guess. But that's what not many models have, I think, and it's quite unique in that way.
Would you like to keep going with the letter, Jen?
Oh yeah, I was wondering if someone else wanted. I just read 2 paragraphs. I got excited. I was like ready to read what came next to the letter, so I forgot that we were alternating. So maybe I'll pass the baton.
Jacob, you want to keep going?
It's similar, right? The role of NCAR plays in training and mentoring the next generation of scientists cannot be overstated. I truly know hundreds of atmospheric and space scientists, and almost every single one of them has spent time learning, teaching, and doing research at NCAR. Should I take the next one, or?
Sure, go ahead.
Yeah, okay. Maybe one thing to mention before. I think that's what I've been looking through these letters a bit beforehand, and I found it really fascinating how many people, not necessarily still working in the US, but who, like what this letter basically says, have gone through NCAR and NSF and all these institutions to learn to get basically a large part of their education and this expertise, and take it then to different institutions and then collaborate again with NCAR to bring this kind of back. So it's not that it's lost, it's just it's kind of it just grows basically and expands, and it's quite cool, I think.
And it brings, and then people will, people come, and next generations of students know that this is the center that they can be connected to. I think it's very short-sighted to think only of the scientists, local to. But anyway, sorry. Please continue.
Yeah. Finally, it is important to keep NCAR's various scientific components together and in close proximity. Many scientific discoveries and advancements have come about at the intersection of scientific fields and through the informal interactions of scientists from seemingly disparate field of study. And yeah, I would fully agree with that point.
Absolutely.
Are you going to take the last one, or should?
I'll take the last one. Sure. NCAR has always. Thank you. NCAR has always been a well-run organization, consistently getting high marks in NSF reviews. So it's a little bit, maybe that's some inside baseball for them. I'm not sure. The scientific advances it has achieved, the quality of the empowering facilities it maintains and makes available, and its importance in scientific education at all levels makes NCAR a center that is the envy of scientists from around the globe. It is a true gem. What problem is NSF trying to fix? So I think, and then at the very end here, we have Richard Benke. So I thought that was a very powerful letter, and shows maybe another perspective on just the value to us as scientists. But thank you folks for reading. Maybe Jacob, we should give you some space to do I think we've come up on another hour, so maybe we'll. Do you wanna bring us into hour 14?
Yeah, it's been so fast. I didn't notice that it was already hour 14. Yeah, thanks for reminding me. All right, yeah. So yeah, then as you already said, we're starting hour 14 now. So my last hour, and perhaps I guess like 20 to 40 minutes, the sun will also rise in the US East Coast. So I'm not mistaken. If the sky is good, who knows? But you will know if you know the weather forecast, I guess. It's a nice bridge to that, I don't know. Yeah, and we have some talks for that hour as well later on. But first, I'd like to remind you like why we're here. So as we've already highlighted, I guess, through these letters a bit, and we will be doing so for the next many hours, that weather and climate forecasts and modeling and all these institutions are very important. and that US scientists and US institutes and institutions have really been at the forefront of this field and are really important for the taxpayer, for anyone really on the globe, if you want so. And for instance, one thing that I'd like to highlight, I don't know if it has been highlighted before, is since I've been working recently mostly concerning stratospheric aerosols and these kind of aspects, where we also use the Rackham model, so the community Earth system model version of including the higher parts of the atmosphere, and that is developed and maintained at NCAR essentially, which also really has implications for understanding ozone, not only the ozone hole, which was already many years ago and already received a Nobel Prize, so it is recognized globally by the highest kind of scientific awards one can achieve. But also how climate change and all these other aspects will change ozone and such aspects. And as you've already heard, this investment and this kind of currently present expertise, but somewhat diminished through the decisions that have been made and funding cuts, is under threat. So there's shortages at these different weather stations that are already hurting the forecast. For instance, if you live on the East Coast, I believe the forecasts tend to be quite a lot better because there's so many stations across all the land, and you can really track all these weather systems and weather phenomena beforehand. And you really know what is happening to the best of our knowledge, at least in our current understanding. And also these big climate labs, be it NCAR or GFDL or NASA GIS, or these federally funded institutes, are shrinking and are really under threat. So what is even worse now is that the currently discussed US administration's proposed budget for the fiscal year of 2027, so the upcoming year, is now being considered by Congress, and this could have even worse implications, meaning cutting the National Science Foundation, so NSF, and now the Earth Sciences budget in half effectively, and also eliminating basically the entire NOAA research arm. So this is basically also part of the institute where Manabe or other people have done their foundational research on climate modeling and really understanding weather and climate. And especially important for the future generations and for the years to come is that these foundational programs for young scientists are also under threat, which is, I think, an important point to note as well. And beyond these budget cuts, what we've been discussing a bit for the last half hour or so, is that NCAR, this big National Center for Atmospheric Research, is under threat to be dismantled by the administration. And this is really, as we've just seen in the letter, a gem internationally as well as nationally for everything that is happening. And so we urge you basically to help defend this public good of weather and climate science and keep it as a public good for everyone and every citizen and every taxpayer, essentially. So how you can do that, as you can see at the bottom of the screen, you can use the link in the video or the live stream description, or which is shown on the screen, to contact your representatives. So this wclivestream.com/act, and tell them to fully fund all these institutes, meaning NOAA, NASA, NSF, and other agencies that you may know, or even smaller local institutes, and really to protect NCAR to keep doing this important work. And this is really a timely matter. So these decisions are being made right now, so in the House and Senate. So it is really now the time to act. And I think it's always like, if you don't step up at that time, then what are you doing? So this is really like, if you want to step up, the time is now, basically. And last but not least, I'd like to highlight again that all the speaker views, or everyone that is speaking on the stream, basically, that their views are their own and they don't represent the institute that they are affiliated with, or any other institute. But this also shows that people are dedicated to this cause, and they offer their free time and their night, their sleep, essentially, to be on this live stream and to support this course. And yes, I think that's all I wanted to say at this point. And
that's great, Jacob. Thank you so much.
Thank you.
I wanted to highlight, in the midst of these letters, you might wonder, why are they doing this? Why get rid of NCAR? And there's, I think, a lot of speculation at the time if this was motivated by Colorado or other sorts of things. There's currently a lawsuit that UCAR has filed against the NSF to try to stop this dismantling. And we got the good news this morning that there's been a temporary stay as they consider how to proceed. But we shouldn't pretend that the danger is in any way gone. This is just a momentary thing. And maybe to drive that home, there's this document they uncovered as part of the lawsuit that I just want to share here from the OMB that really kind of explains directly. They say it here, what we're taking action against. And I thought maybe we could each do a bullet point here. So here, is this, can people see that? What we're taking action against, I'll start with this. NCAR has funded a lot of research on climate change caused by humans, including significant work at the Climate and Global Dynamics Laboratory, which studies climate variability, long-term climate change, and the role of human activities in global warming. This work directly supports international agreements like the Paris Accord, which this administration does not support. And so what I find really, I think in a lot of sort of public comment, there's a lot of statements around this is a hoax or this isn't real or something like this. And here in this legal document, there's nothing to suggest that that's what's felt or what's seen. It's talking about climate change caused by humans. It's talking about research into trying to understand this. And you'd think that that is something that would concern the public and be something that a government would want to help its public with. But it's drawing attention to the fact that this can be used to justify a policy that the administration does not like. And that seems like such a strange reasoning around whether or not you should try to understand something, whether or not you should be doing science about something. So I was really struck by that. Does someone want to read the next paragraph?
I just want to comment quickly that, there's two things Jonah's mentioned here. The first is kind of the policy, which is well in the domain of the government. And the second is the science, which is in the domain of scientists. And we have a complex interaction, of course, between science and policy. But science provides information, and it's just one seat at the table, and often a seat that doesn't get a lot of attention. But when you completely remove that seat from the table, as is suggested here, it's basically saying you want to make decisions in the absence of information, in the absence of data, in the absence of science. And so I think that's personally concerning. Yeah.
I very much agree with that. Yeah, to be clear, when we write papers about climate change, or when people at NCAR write about research these things, these are not policy prescriptions, or these are pieces of information that can help in any sort of decision about how you proceed, whether you go along with an international agreement or not. But it's not, it's very strange. Here it's already trying to draw inference from the science to a policy. It's all very odd, but our role is just to provide information that can be helpful for governments, for you, the general public, in making decisions around the world that you live in. But the decisions are yours. So
I'll read the next bullet. The Atmospheric Chemistry Observations and Modeling Lab investigates greenhouse gases and other chemical processes related to climate change. which informs regulations on emissions that the administration does not support. Again, the scientists who operate in this lab are not policy oriented. They're completing science investigations, and actually they go well beyond greenhouse gases. I mean, chemistry in the atmosphere involves a lot of things. So yeah, it's yeah. Anyways, okay, I'll stop.
Yeah, the Earth System Predictability Across Timescales program and the System for Integrated Modeling of the Atmosphere both do work related to climate change, contrary to the administration policy. These activities will be redirected to focus on weather and space weather that have direct and beneficial impacts on the nation, which I think what we've heard before from some speakers is that some speakers really struggle to separate weather and climate because they are so interconnected. And yeah, that's maybe a point to make here.
That's right. When you try to use your understanding of the weather to help the nation, that's okay. But if you average the weather and try to figure out how that, then don't do any statistics. That's when you can get into trouble. And NCAR also has long-running DEI initiatives like the UCAR NCAR Equity and Inclusion Program. It just feels like there's this attempt to. I think this is DA programs are common in universities and in science, and it just feels like in general there's this effort here to take NCAR and draw all of these ways in which the politicization of this process feels very very strange to me. Maybe we should read one more letter from former NCAR directors. Does that sound like a good plan?
I think maybe as a last point, I feel like if I read all these statements, mainly if I wouldn't read the last sentence, I would say that those are all good statements, like things that should be done if you're a scientist and if you're a research institute. That's kind of their duty, I guess. And if you leave out the last couple of words, the meaning becomes very different.
Yeah.
So.
Yeah. Okay. Well, let me bring up that. And Jacob, did you say that you worked at NCAR, or that you use a lot of NCAR?
No, I work with people at NCAR, and I use their WACA model, and I develop part of their NCAR, like in the WACA model essentially. But yeah.
And maybe can you talk again a little bit about what does WACM stand for? Do you remember this, or what is WACM again?
I would
I'm sorry,
say,
don't want to put you on the spot.
as far as I know, so the W stands for whole it's something like whole atmosphere chemistry climate model or something like that. I would imagine, but I feel like they're throwing about many acronyms all the time that don't always make sense. But which I think is quite a good name for such a model, as I said, that goes quite high up in the atmosphere, which many models really don't, because it's quite difficult. As soon as you go far away from the ground, observations are more difficult, and it's less known to some just by physical distance, I guess. I mean, measurements at the ground are difficult as well, but for different reasons. But only this distance, and only that you have to essentially go very high in the atmospheres that are very cold at the point, very different, very uninhabitable regions of the atmosphere, essentially. I think that's why it also took so long to essentially measure higher up in the atmosphere with those balloon measurements or such things. And yeah, that's quite unique, as I said, I'd say. That's why we are essentially using their model, because it's one of the most transparent and best usable models for that.
So this is some of the work done there is so unique and so widely used and so essential. I hope that yeah, it's just so shocking to imagine not having this. We have here this letter now from former directors of NCAR, and maybe we will just go through this again. Do we want to? Maybe I'll start this one. We can. So here we go. So here's the response. In our individual capacities as former directors of the NSF National Center for Atmospheric Research, serving consecutively from 1986, when I was born, to 2018, we write with a profound sense of urgency regarding the recent communications concerning the center's future. While we recognize that institutions must periodically evolve, we must be clear, any path that leads to the fragmentation or dismantling of NSF-NCAR is fundamentally not in the nation's interest.
Yeah, I'll take the next one. As a strategically integrated scientific ecosystem, NSF-NCAR's collective value far exceeds its individual components. Beyond academic research, the center serves as a vital pillar of the nation's public safety and economic infrastructure. By bridging the gap between fundamental research and operational application, NSF-NCAR generates immense economic value for the nation, providing the foundational intelligence that protects commerce, reduces disaster-related losses, and optimizes weather-sensitive industries like energy, insurance, and logistics, as we've heard before in the letter that we first read, I think.
Its technical leadership includes developing wind shear detection systems that revolutionized aviation safety and pioneering GPS drop zones, which have improved hurricane track forecasts. NSF-NCAR's solar research, including the suite of custom-designed ground-based instruments that provide unprecedented observations of the solar corona, support NOAA's requirements to improve space weather prediction, strengthening the nation's ability to protect the power grid and satellite operations. These efforts, along with sophisticated fire behavior modeling and advances in storm scale forecasting, provide the early warnings essential for navigating extreme weather events.
This synergy of innovation also directly fuels NSF-NCAR's Earth system modeling, enabling a seamless prediction framework that provides intelligence across timescales, from hourly alerts to decadal projections. It is imperative that the United States remains at the leading edge of this predictive science. This is particularly critical as the President has signaled a clear mandate for the U.S. to regain the global lead in numerical weather prediction. The NSF-NCAR-NOAA partnership is the primary engine for this ambition, notably the new prediction model recently announced for future NOAA operations. The Model for Prediction Across Scales, or MPAS, features NSF-NCAR science and technology at its core, fragmenting the center now would dismantle the very infrastructure required to achieve this national priority.
By advancing aviation safety, emergency management, and agriculture productivity, the center provides essential services beyond the scope of individual universities or the private sector to maintain. The proposal to redistribute NSF-NCAR's core functions threatens the very heart of American atmospheric science. The center serves as the essential hub where university researchers, federal agencies, and international partners converge to solve problems too vast for any single institution. This role as a community convener is a key component of the center's mandate, providing a neutral, stable ground for collaboration that has never been more necessary.
To dissolve this center of gravity is to sever the collaborative ties and the interdisciplinary workforce that produces this life-saving environmental intelligence. Furthermore, as artificial intelligence redefines the future of science, NSF-NCAR is uniquely positioned to mobilize the nation's best academic minds to rapidly advance AI-based forecasting for extreme events, a task requiring a level of coordination and workforce development that no other organization can replicate.
Also concerning is the irreparable damage such a dismantling would inflict on the future of the American scientific workforce. And this is something we've been talking about and came up in Richard's letter too. NSF-NCAR has long served as a premier training ground for the next generation of researchers. I certainly myself took the CESM tutorial there, the first experiences I had running a climate model, and helped me with a lot of my research down the line. By providing graduate students and early career faculty with access to world-class supercomputing and models, specialized instrumentation, and a mentorship network that spans the globe, NSF-NCAR ensures a robust pipeline of talent into our universities, agencies, and the private sector. If these pathways are disrupted, we risk a lost generation of scientists. At a time when our international competitors are significantly investing in science, fragmenting NSF-NCAR would be a signal that the United States is withdrawing from scientific leadership in the atmospheric and related sciences.
The impact of NSF-NCAR is truly nationwide, serving as an indispensable force multiplier for a scientific community that spans all 50 states and territories. Because most academic departments lack the multi-decadal funding and interdisciplinary expertise required to maintain global community models or operate sophisticated instrumentation and research aircraft, NSF-NCAR provides these big science tools as an irreplaceable shared public good. From improving the accuracy of hurricane forecasts for the Gulf and Atlantic coasts to advancing wildfire and smoke-impacted modeling essential for the Western US, the Center's research addresses our most pressing regional threats. In the Midwest and Plains, NSF-NCAR-led studies on deep convective clouds and storms underpin the agricultural economy, while its hydrological research provides the foundation for the U.S. National Water Model, NWM. Operated by NOAA, so what we've mentioned before, this National Oceanic and Atmospheric Administration also. I'm very bad with these acronyms, I'm sorry. The NWM has expanded the nation's flood forecasting from 4,000 locations to over 2.7 million river reaches coast to coast, ensuring that even the most remote communities have access to life-saving water intelligence. Dismantling this integrated ecosystem would not only fragment the university community, but would leave every state less prepared for the environmental challenges of the future. And I think one point here that is quite important, which I don't know if it has been raised so often, is that since it's a public institution, it really serves everyone, and it doesn't focus on cities or more populated areas, but it's really a nationwide aspect, which I think is quite important.
Yes.
Yeah, all 50 states and well beyond those borders, because as we know, the atmosphere doesn't really respect borders. Yeah.
That's right. If we won't have time, I think, today, but people should check out, if they just want an example of this, you could look at the Alaska letter, has all of these examples of specific things that NCAR helps with related to permafrost and all of, every single state has its own unique challenges, and every corner of the world has its own unique challenges, and NCAR's resources touch all of these different aspects. It's really quite something.
Yeah. You all can hear me okay?
Yes.
Yeah. Okay, good. Sorry for being muted, although it was mentioned that maybe that was meant for effect. So anyways, it's all good. Okay, so we'll finish this letter from the former NCAR directors who served, let's get the years right. So from the year Jonah was born.
1986 to 2018. So that's, I guess 32 years of people working at this institution, just directing this institution.
Yeah, and we learned yesterday that NCAR was founded in 1960, and UCAR right before it. So that's what I think we have spent over 60 years comes from the beginning of NCAR and UCAR. So we have spent over 60 years building a global pillar of excellence that underpins our national capability to understand a changing atmosphere. The primary mandate of the center is the broad spectrum of atmospheric and weather science that keeps our nation safe. To fragment this capacity now would be a historic strategic error that cedes American leadership at a moment of peak environmental risk.
We therefore urge the Foundation to reconsider any path that leads to the weakening of this national treasure and instead double down on NSF and proven mission to convene the community and enable the discovery that keeps our nation safe and competitive. We stand united in our commitment to NSF NCAR's mission and are ready to engage in a rigorous defense of the integrated model that has served the United States, its universities, and the global scientific community so well for over 6 decades. And so here, this letter is signed again by former presidents. So we have Rick Anthys, Eric Barron, Mara Hagan, Jim Hurl, Timothy Killeen, Robert Safran, and Roger Wakimoto.
So, I think that, I think probably everyone listening to this, hearing this, if you didn't already understand and feel the importance of NCAR, I mean, every time I read one of these letters, I feel like there's something new I discover or learn about that NCAR does, and the value of it. And what we read from the OMB makes clear that there's an axe to grind. There's a feeling of this can be used to justify policies that this administration does not support. So I think it makes this in conjunction with the new set of OMB rules that are being proposed that really shift scientific funding away from sort of a merit-based, peer review-based model to one of a sort of a political appointee-directed model. NCAR could really use protection from Congress. And I think in the immediate aftermath of the announcement when we were at AGU, it seemed like that was a possibility. There was an attempt to have an amendment to the appropriations bill from the Colorado delegation that was rejected in part by there was a senator who spoke about, well, it's not Congress's job to choose which laboratories or which scientific projects get funding, but it's this seems like a case where you have this very wonderfully helpful institution, this thing that so many Americans and people around the world benefit so much from, and it's a chance to protect it. And so but Congress, I think, won't do this unless we really let them know that this is something that we want. There needs to be a pressure coming from and support coming from you, the viewers, from the people who are who care about NCAR. So that's at least my perspective. I don't know how Jen or Jacob, your thoughts on this, but
I think Congress was in a bind when this came about, and I wouldn't lean into what any one member says. I mean, there's a whole body there and a whole number of people that we need to engage with, which is why it's so important that everyone watching this call and we really show the value across all of these different representatives. Congress has been very supportive of science. I personally wrote to Senator Grassley from Iowa, and he was very supportive in his personal letter back to me for NCAR. And so I think that that's just really reassuring, and we just need to make sure that we continue to not make it a he said, she said with OMB, because their perspective is not one that's shared broadly, even with Republican senators from Iowa. So just be really careful.
Yeah, maybe like what I don't know. I always like to highlight this aspect is, I think what Jen has hinted to before, is that it doesn't really matter if you care about the atmosphere or not, you will be affected by it. Like it's not really a choice. So that's why it's really important that it affects everyone. So that's why I think it is, since it affects everyone, it's kind of in the public hand in any case. So it makes a lot of sense to also provide it with public funding.
Makes sense. Makes sense. Well, it's been a great chance to get to dive in a bit to what is going on, or excuse me, to some of these responses to NCAR, and I wanted to. Have people been able to hear? Have people been able to hear Jen all right? We're getting some reports that maybe some people haven't been able to hear her. Folks in the chat, have people been able to hear Jen okay?
Cool. We're getting some yeses that they can hear.
Okay. Okay, that's great.
Thank you for being part of our sound check.
Yeah, thanks, folks, and thank you. It's now I'm here on the East Coast, and now the sun is starting to come out. I can see light dawning, and maybe a little
just
bit of time.
telling some personal stories. I'll just say that, many of the people who are the former directors of NCAR have really stepped up. And there's been some health issues that some of the folks who've been leading the NCAR and UCAR effort have faced. And so, Eric Barron has taken over as the UCAR leadership. And Jim Hurl, he had some health difficulties. He's fine. But he was writing letters and emails to try to make this letter in particular part of the publicly released website that the Weather and Climate Livestream put together, hours after he was out of a surgery. So these people care deeply about this institution, and they've seen it. They've had a front row seat to what it can do and its capabilities. And so I think we're really fortunate to have such passionate leaders and such passionate people who care about these institutions. And so if you're one of those people who's super passionate about these institutions, I think calling, really shows calling your representatives and asking them to put protection for NCAR into law really shows, if we can get that protection through Congress and also through the legal system, I think that we're going to do a lot better to save this institution that's so important for our country.
Yeah. Perhaps with this, I can slowly go to our next speaker before, or at least after, kind of introducing why we've come here. So first, thank you a lot for the last, an hour or so of discussion and reading out these letters. It's been really interesting and fascinating. And yes, as you said, so many different aspects. And yeah, so thank you again. I think we'll be seeing more of you most likely, but yeah, thank you for now.
Thank you so much, Jacob.
Thanks. Great. So yeah, as I've been saying before, now we're in hour 14, so hour 15 is coming up, more or less, in half an hour, 20 minutes or so. And I'd just like to really quickly, before our next speaker, remind you why we're here. So we've seen all these letters for the last hour or so, and this discussion and different statements online, etc. And you can also go to the website and see more if you're more interested in that. But yeah, as you probably know by now, or realized by now if you haven't done so before, weather and climate research are very important and are really important for the public and for everyone if they want or not. And as the US has been one of the leaders in this field, and this is really highlighted by these different people writing and caring about these institutes even after they basically already left these institutes, but still being involved in writing letters, giving advice to the future generation, really caring about these aspects. So as I've already highlighted before, the US scientists have done the first kind of successful numerical weather forecasts in the already 1950s or so, and have developed the first computer models of CO2 pollution, essentially warming the planet, etc. And not only Earth, but also on other planets from which we can also learn, which really shows kind of the broad variety of things that have been done and are still being done. And this really real excellence, you have to call it, is currently under threat, and this investment in these expertise in the future generations is under threat by these already existing staff shortages at weather stations and other observational instruments and institutes that essentially hurt the forecast and hurt the insurance industries and the different people living in different aspects, like in different regions of the country, and even being in agriculture in every aspect, really. And this will ultimately then go back to the taxpayer at the end. So these kind of shrinking labs that are kind of affected by these cuts really stem from the already kind of discussed cuts, but now really like proposed budgets for the next fiscal year of 2027 that is currently considered by Congress, which includes essentially cuts to the National Science Foundation and now the Earth Science budget, essentially cutting it in half, as well as eliminating NOAA, so the National Oceanic and Atmospheric Administration's research arm. So where many research has been, like a lot of research has been done on CO2 and all these aspects, and they still have important weather and climate models that are operational there and are important for forecast every day. As well as these foundational programs for young scientists that may end if this is approved as it is. And beyond these cuts, what we've been discussing as well, the administration is also trying to dismantle NCAR, so this National Center of Atmospheric Research, about which we've been hearing from its former directors or presidents just before. And this will really, if it comes into effect, hurt the capabilities of forecasting and understanding our atmosphere, which is essentially where we live. So we should be quite keen on protecting it. So we urge you to help us defend this essential field and this public good of weather and climate science, to use this link that is shown at the bottom of the screen right now and is also in the video description, this wclivestream.com/act, and really contact your representative and tell them that to fully fund NOAA, NASA, NSF, and all the other institutions that do this essential research. And there are, as I believe, some guides on how to do this. And if you have more questions, I think anyone involved in the stream and beyond is very happy to help you with that. So these decisions are being made right now. So it's really right now the time to act. And if you want to do something, now is the time. So if you've been thinking, if you want to support science, and especially science that will affect everyone in the US and also beyond, then now is the time to act and to make your voice count. And last but not least, before introducing our next speaker, I'd like to highlight that, or emphasize that all our speakers' views are their own, as well as everyone appearing on this live stream. They don't speak on behalf of their affiliated institute. It's more to identify who it is, especially for similar names, etc. So without further ado, I'd like to introduce and bring to the stage our next speaker, who is Robert Pincus, who's an atmospheric physicist and a research professor at the Lamont Doherty Earth Observatory, which is part of Columbia University, and I believe just outside New York City. And he'll be talking about his talk on A Million Shades of Gray. So without further ado, take it away.
All right, folks can hear me?
Yeah, perfectly. Thank you.
All right, Brooklyn in the house. Let me hear you say yeah. All right, I can't hear you. Maybe you could type yeah in the chat or something.
Yeah, I can hear you.
You can hear me. All right. Right. My name is Robert Pincus. I'm going to talk about work that I did with Sean Cohen, who spoke about 5 hours ago. What Sean told you about was something completely different. He's a very talented young guy who's in danger of not being able to proceed in science because of lack of funding. So I want to talk to you about why it rains more on warmer planets and less on cool planets, including over history on our own planet. So this image here, the kind that you're familiar with, encompasses all of weather and climate. It's brought to you by light, and I might use the term radiation. I mean electromagnetic radiation, but it's light. The image is constructed from reflected sunlight, of course, but beyond that, all the weather that you see and all the climate that you see, the clouds, the circulations, the way the air is moving, arises because of a few simple principles. The atmosphere is a thin shell of gas on this rotating rocky sphere. More sunlight arrives at the equator than arrives at the poles. And the temperature and the composition of Earth's atmosphere are such that water can condense to form clouds. So clouds are the most obvious feature in an image like this because the rest of the atmosphere is mostly transparent to sunlight, at least at the wavelengths that we can see, the colors that we can see. But if we look in the infrared, where the source of light isn't the sun, but rather the surface of the planet and the atmosphere itself, things are less black and white. Colder objects emit less light than a warmer object does. So when you look at clouds, when you look at the planet in the infrared, the clouds look black because they're mostly cold. That's especially true of the high clouds, the dots you see throughout the tropics. And we'll talk about the other colors in the next couple of minutes. So Earth's atmosphere is enormously complicated. Well, the atmosphere itself is not enormously complicated. It's mostly made up of nitrogen and oxygen, but these molecules don't interact with light. You can ask me why in the chat, or you can come to take a class with me. The gases that do interact with infrared light are called greenhouse gases because they're like the pane of glass on a greenhouse. They are transparent to sunlight, but they absorb this earth shine, this light that is emitted by the earth and the atmosphere. And the strength of that interaction depends on the color of the light, and that's the horizontal axis on this figure. The wavelength, here we use a different number that the dorks like called a wave number, because it depends on the way the molecules are constructed. You know, CO2 has 2 oxygens here and a carbon in the middle, and to absorb light, it has to bend in a certain way, that kind of thing. Understanding that relationship between molecular structure and the spectrum, the wavelength spectrum of light, was a triumph of quantum mechanics. It's almost 100 years old by now. That gray line that's across where it's 1 shows you where absorption starts to be really noticeable. And the colors along the bottom here, wait, can you guys see? Well, we won't bother. Yeah, the colors, all these guys down here, they're different gases, methane, industrial chemicals like chlorofluorocarbons. But most of these contributions are small. And let me see if I can do this right. The 2 big dogs are carbon dioxide here at 15 microns. So for folks in the US, that's 6/10,000ths of an inch. And the big one is water vapor. Water vapor is Earth's main greenhouse gas. It's the reason already that the planet isn't just an ice-covered ball. One thing you might notice about this figure is that the scale of the image isn't linear, but it's proportional. So every set of ticks over here is a factor of 100. So if you look from the most opaque part of the water vapor spectrum to the least opaque, that's a factor of 1 million, right? So it's in some places the atmosphere is very, very opaque, and in some places it's essentially completely transparent. So if pitch is to sound as color is to light, you'd need, if you had a piano that covered this range of difference, it'd be 13 feet long, 4.5 meters long. And that huge range of opacity turns out to be key to understanding why and how much it rains. So let's see why that is. Let's take this figure and scoot him up here, and let's add a couple more. Ugh. As you may have guessed, the total opacity of the atmosphere, the total of all those colored lines, is this line in the center row here, in the middle row here. And this basically looks like whichever is thicker of water vapor or carbon dioxide. The energy leaving the atmosphere and going to outer space, that's this line here. It depends on the color too, but it's influenced by these long, broad lines. And these are the lines that would be emitted by solid objects at either the surface temperature, which is the hottest temperature in the atmosphere, or the temperature at the top of the weather layer, which is the coldest atmosphere, or coldest temperature in the atmosphere. And because warm objects emit more, that's why this curve is higher than this curve, but they also shift towards shorter wavelengths or bluer colors roughly, although none of this is anything like blue. The same way that like, you know, something which is hot might not glow at all if it's room temperature, and it might be a little bit red if it's pretty hot, and it might be white hot, super hot. So you see the color shift as well as the sort of total amount of energy that's going up. This place here, where you can see as much light as if the sun were, as if the atmosphere were transparent, that's what we call the water vapor window, because water vapor up here is completely transparent. Okay, this is and what you see here is because carbon dioxide is so very, very opaque, you see only the very coldest temperatures. But what happens in between, oh yeah, maybe let me say it like this. I'm going to change from here, which shows you the energy, to here, which shows you, if you turn that relationship around and you ask, given this amount of energy, what is the temperature that is associated with its emission? So if I had a black body here, what temperature would it have to be to produce this amount of energy going out? And what you see is that all the different temperatures in the atmosphere are being emitted from. So here's the surface emission, here's the top of the atmosphere emission, and all the other temperatures are being emitted from. So that means every temperature is being emitted from, and every pressure, every height in the atmosphere is being emitted from. And that emission means that the atmosphere is losing energy all the way. It's getting cooler all the time from its top to its bottom. And that cooling is key to understanding rain. So you remember the water cycle from elementary school? I still remember the song my kids learned there. And so the energy from the sun comes down and it warms the surface of the earth. And that adds water vapor. It evaporates the water vapor, and the water vapor goes up into the sky. Some of it produces clouds. Some of those clouds rain and drop the water back down to the earth. And if you're a physicist like me, you're like, well, wait, you kept track of the water, but where does that energy go? Because you have to, because the water in the atmosphere stays between the earth and the atmosphere, and the energy has to stay between the earth and the atmosphere too. So if it takes energy to evaporate the water from the ocean, when that rain condenses, that must also mean that we are wheat. Oh yeah, good. It must also mean that that energy is being left behind in the atmosphere. And if you just kept adding energy to the atmosphere would warm up. And so the energy that is left behind by the rain is exactly the energy that's being lost by the emission from the atmosphere. So in other words, the heating by the rain is balanced by the cooling from the light emission. Okay. So there's another piece, but I think I won't talk about that. All right. So what happens then if the temperature of the earth changes? So the temperature profile, the way that temperature varies with height through the atmosphere, is controlled pretty well by mixing and by sort of basic thermodynamics. This is fundamental physics. The top is set by the temperature of the tropopause. That's the top of the weather layer. That's actually, that temperature is actually controlled by water vapor too, but that's a whole other talk. So when you make the surface warmer, basically it's like if you start at the top and it's always the same temperature and you make the surface warmer, it's just like making the atmosphere a little bit deeper if you measure it in temperature units. So the amount of water that's available in the atmosphere. So by making the atmosphere warmer, you make it deeper in temperature units. How much water is there in that atmosphere? Well, the amount of water that's available depends strongly on the local temperature. And that's because basically the water can condense. So as the temperature of the ocean water goes up or the lake water goes up, it's easier for molecules to escape. So the maximum amount of water that's possible gets larger as the surface temperature goes up. If you just think about adding up all the water in the atmosphere. So you might think, oh, precipitation increases with just as fast as all that water vapor does. And this figure's from the scientific literature. It's from last year's Blorbo, actually, Isaac Held, a paper about 20 years ago. And what he shows you in looking at the difference between the left-hand figure and the right-hand figure is that water only the rain falling out of the sky only increases by about a third as fast as the total water in the sky. So if the water mass isn't controlling how much it rains with temperature, it's got to be that energy component, right? And so so you think, well, that's cool. A warmer atmosphere, that'll cool more because warmer atmospheres, or warmer objects give off more energy. And a moister atmosphere also ought to be more opaque because water vapor is opaque. And so if you add more water vapor, the atmosphere will get darker. It turns out the atmosphere is a little bit more subtle. The answer is actually a little bit more subtle than that, because at colors where water vapor in the atmosphere is already opaque, emission from the atmosphere itself doesn't change very much as you change the surface temperature. So I made a little drawing here. I changed the surface temperature by 5 degrees twice, from just above freezing to 5 Kelvin above that, and then again to another 5 Kelvin to about Earth's average surface temperature today. And I made these atmospheres just as I was describing to you. The temperature structure is very simple. The relative humidity, the amount of water vapor relative to how much is possible, stays the same all the way through the depth of the atmosphere. And what you see is in the thick parts, the places where the atmosphere is very opaque, the temperature that you infer, this so-called brightness temperature that you associate with the outgoing energy, changes by only about 20% of the change in the surface temperature. So here, the amount of energy is changing by 5 degrees Kelvin. But that's the surface talking, that's not the atmosphere, right? And so here, why isn't this changing? Well, it's not changing where the atmosphere is thick, because the emission is controlled not only by, well, I guess maybe to say it like this, because temperature controls two things. It controls the amount of emission on the one hand, but it controls the amount of water on the other hand. And so every time you look down from the top of the atmosphere and you start to accumulate water, and you get to the amount of water that makes the atmosphere thick, that height is always about the same as measured in temperature. And if the height is always the same as measured in temperature, it means the emission is always the same. Okay. So where the temperature changes most, that emitting temperature changes most, is here, along the edges of the water vapor window. And so what's happening when you change the surface temperature is that you add more water vapor, and some range of colors goes from being more or less transparent to being more or less opaque. Okay. And so it's the area, exactly this area that changes, that controls the amount of extra cooling you get as the surface temperature warms. And the extra cooling you get is what allows more rain to fall out of the sky. And so that means you can figure out, actually with pencil and paper, how much more it rains as you increase the amount of surface, as you increase the surface temperature. It's basically a line that is drawn here, and you ask how much extra opacity there is in the atmosphere in the spectral sense as you increase the surface temperature. So it's 5 o'clock in the morning here, and so I might not be at my most coherent, but this is sort of what I wanted to tell you. So the question that we've been asking ourselves for 20 or 30 years is why the planet rains more, why the atmosphere rains more as the planet gets warmer. And the answer turns out to be that it doesn't exactly, or not directly. More rain falls out of atmospheres that have more water in them. It's not because there's more water mass, but because the water allows the atmosphere to emit more light back to space. And that light, that changing of the light emission happens in at very particular colors that are really at the edges of the water vapor window. So we have this phrase we use sometimes, the water vapor window closes. As one example, like on Venus, the water vapor window is completely closed because they've got 90 times the atmosphere we do. And because these kinds of, this insight is based so much on just the physical properties of water vapor, how much water vapor is available at a given surface temperature, and what its spectroscopy is. That's the relationship between absorption and color. Because it's based on these very simple principles, we have great confidence that when we think about the future, or when we go back in time and try to understand paleoclimate, that this phenomenon is completely robust, and it's not, for example, just a result from some complicated numerical model. Sean and I would be delighted if you'd read our paper. I can leave that there. I can answer any questions that folks have.
Great, thank you. That was really, really nice. I always like it that these talks.
Oh, wait, now I can't hear you.
Ah, sorry.
Wait, I gotta hear you.
All right, no worries.
Great, thank you. That was really, really nice. I always like it that these talks. Oh, wait, now I can't hear you. Ah, sorry. Wait, I gotta hear you. All right, no worries.
I think now it has some delay. Right?
I have a delay.
Okay, I think you have to. Do you hear me now?
Jacob, if you, yeah, all right.
Can you hear me now, or is it?
I still can't hear you,
right.
Jacob. Do you want to type stuff in the chat for me?
Yeah. I'll just kind of forward this question maybe in the chat that came up in the.
Yeah, that's fine. Oh, swirls in the, oh yeah, I meant to say this. So people were asking, yes, what you're seeing there, the way I made that map was by putting in different colors that are sensitive to water vapor. So if you look back at that map, I could go back if you want. If you look back at that map, what you see is that the deep clouds are associated with these green colors. That's because the atmosphere's super moist there. That's why the tall clouds are there. And here is where the air is descending. The air has to go up and then it has to come back down. And the air is descending. And so that's where the air is drier because all the water's been wrung out of it and it's coming down. So that's where the swirls are from. That's all water vapor. It's air currents, yeah, but it's air currents, some of which are wet and some of which are dry.
Great, thank you. That was really fascinating, but for the sake of time, we sadly have to move on, I think. But thank you very much, especially at this very early hour. I know it's like 6 a.m. or so, right? All right, thank you. So that is the end of the, I believe, 14th hour or so. So now I will kind of give over the hosting duty to our next host for the next 2 hours, which will be Vanessa San. And yeah, I'll just let you introduce yourself and, well, yeah, give it to you.
Yeah, thank you so much. Hi, everybody. Thank you for joining us in the 15th hour of the Weather and Climate live stream. We only have 35-ish hours more to go. My name is Vanessa Sun. I'm a PhD student in atmospheric sciences, and I research improving air quality. And I'm so excited to be here with you all, learning about the great work of some weather and climate scientists. And this hour of weather and climate science is going to be pretty fantastic. We have a great lineup of speakers for this hour and quite a bit of a mix of different geoscience fields throughout the sessions that I'm going to be hosting for today. So I'm kind of excited for that. But first, we want to remind you why we're here on your screens and doing this stream. The United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, the first computer models of the climate impacts of carbon pollution. And alongside these computational tools, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle. This miracle was made possible by decades of US taxpayer funding and by a merit-based system in which scientists have judged the best projects to receive funding. But all of this is now at risk. The administration is changing the rules so that political appointees, not by peer review, determines what gets funded, and political interests are already being used to justify the planned dismantling of the National Center for Atmospheric Research, NCAR, in Boulder, Colorado. And the administration's proposed budget for the 2027 fiscal year are now being considered by Congress, which would gut weather and climate science across research across the federal government and end foundational programs for young scientists. And I've personally used some NCAR climate model data in my master's thesis at MIT. And I had the opportunity to visit NCAR before I moved across the country to my current PhD program. And there were a lot of scientists that I met there that were really encouraging of my own research career. And it really set me up to feel confident going into my PhD. And so they told me all about these programs that they offer that I could participate in as a graduate student. And to my knowledge, NCAR is still attempting to run some of these formative programs for scientists like me into this summer and currently, and for also other scientists that you'll be seeing on the stream. And NCAR is a world-renowned laboratory which engages in weather and climate science research in this country, and their work is useful for people around the world, and it heavily depends on crucial federal funding. But because NCAR's climate research doesn't align with the administration's political priorities, it's at risk for being defunded. But it doesn't have to be this way. If you like what you see here, then we ask for you to please use the link below to contact your representatives and tell them to defend weather and climate science, to fully fund NOAA, NASA, the National Science Foundation, and other agencies that make this work possible. And to protect NCAR as well. So the Senate, the House and the Senate are making these decisions right now. Now is the time to make your voice heard. So with that, we have our next speaker. As a reminder, all of our speakers' views are their own, and they're not representing their employers or any other institution. So let's hear it for Owen Silvera, who's going to be talking about some sediments.
Hey, thank you very much. So the original title for my talk was Looking Down at Sediments, but just for reference, I finished my qualifying exams like 2 weeks ago, so If you know what those are, they're pretty big. And so I have been doing a lot of reflecting afterwards. And so I wanted to tell a little bit more of a personal story, especially because as a biogeochemist, the climate is related to what I do, but it's often a degree of freedom removed from what I'm actually talking about in my research. But it will definitely tie in today. And so what I typically, if you think of like environmental science or just science in general as experimenting, observing, and modeling things, kind of stick right around the middle a little bit. Definitely more on the experiment and observe side, just for reference. So, okay, so my first kind of part of my journey with NSF began in 2019, where I was an REU student at Moat Marine Lab, and I was looking at the effect of ocean acidification on clams. And this was a really important opportunity as an early career scientist to kind of present my research at a conference, and that was the Ocean Science Meeting in 2020, where I was funded by the ASLO Multicultural Program because I'm a Bahamian immigrant to America, to go and present that research. And I got to meet a lot of cool people, a lot of scientists whose works I've been reading. And one thing I want to emphasize is just that as the NSFRU, I was kind of leading this team at the time, but these are all other interns who are also funded on separate or on by separate grants in order to come and help me do my research and then present it. So there's a big teams that come together to like show to make the figures that you see and the stories that are impactful for the, I guess, the future of the world. And so then my next foray was like my undergraduate thesis. And what I wanted to emphasize here, this wasn't funded by NSF, but you can see that there's a lot of infrastructure that goes into experiments. And the reason that I wanted to emphasize this is because, you know, starting out in science, I wasn't really sure. I wasn't sure where the money went to. When you hear like a scientist gets like a $1 million grant, like what is that money actually going to? It's going to people. These are my own handwritten notes from that experiment that was published a couple of years ago. But all these tanks cost money, the lights cost money, and what I was doing is I was growing seagrass, as you can see here, and then I experimented with glyphosate herbicide to see how it affects seagrass die-off. And so this took about 2 years to grow the seagrass, and it was just my own labor. This wasn't an NSF funded project or even a funded project. I was working at a wastewater treatment plant where they had just a spare surplus of money in order to have me do this, but I was doing other work to help support me in this research project. So a lot of effort and time went into this. And so then after that, I had a little bit of a period between my undergraduate and master's program where I was funded by Sea Grant in order to become. I was an oyster farmer, essentially an aquaculturist, and so this was really hard work. And I was working at Treasure Coast Shellfish, if you're ever in Sebastian, Florida, and at the time, you know, I was couch surfing. At the time, I was couch surfing just because I was in this weird period between my master's and undergraduate program. And so I was doing a 1 hour commute to a farming job. So I had to be there for 7 a.m. So it's really hard work, but there were still some good times that I was having. You can see from this video. Yeah, so this was a really cool time period in between my undergraduate and master's program where I was just trying something new and just trying to like honestly, I just didn't have a master's program lined up, so I needed to apply. But this was really interesting. And so then when I started my master's program, there's so much I could talk about. This was at Harbor Branch Oceanographic Institute in Fort Pierce, Florida. I got to do research cruises in the Gulf of Mexico at the time. And you can see here, there's a lot of scientific equipment. There's large teams that aren't shown here. There's my master's advisor setting up some complicated technology that I'll talk a little bit about later. But then the one thing I wanted to point out in relation to today's talk was how Sakura really helped me out. So like I said, at this time period, I was kind of couch surfing. My master's wasn't really paying me a lot of money. And in 2022, I won the Sakura data challenge where basically I was looking at nutrients. So this is phosphate and trying to model nutrient flow in from the Lake Okeechobee to the essentially to the Atlantic Ocean. And so that's what I did as the project. But the reason why, and it helped me, it was just $4,000, but it was literally enough to allow me to move, so I didn't have to commute an hour each day to the lab. This one project was pretty impactful. And then a couple years later, there was famously a proposed 75% cut to IUS, who's the overhead of Socorro. That's the Socorro is the Southeast Coastal Ocean Observatory Regional Association, I think. But anyways, there was a 75% cut to its parent organization, and I can imagine that when you start to have cuts like that, and I don't think it passed, but when you start, because the data challenge has since been funded, when you start to have cuts like that, programs like this, which allowed me to have a much more comfortable life, one where I could actually flourish as a scientist, those type of scholarships can probably be defunded. So then to continue the story, I go from FAU to start my PhD at Georgia Tech, where I am now in Atlanta. And here's my cat along the way from Florida to Atlanta. And so what I study is sediment ocean nutrient cycling. And as many scientists and hopefully people are aware, just everyday people, the atmospheric carbon dioxide is increasing over time. And this exchanges with the water column of the ocean, where you can have photosynthesis, just like plants that uptake that carbon dioxide. And then that can remove it, because otherwise that carbon dioxide can acidify the water, which is more nuanced points. But yeah, the thing that I focus mostly on is respiration, because I look at sediments. And so what my group focuses on is how respiration leads to these fluxes, as we call them, of carbon, alkalinity, and nutrients. And so that's kind of what we do in my lab. And how we do this, this is from a NOAA-funded project a couple years ago. This was a PBS documentary that we had put out that kind of shows the science behind what we're doing. And it's not, there's no volume, or yeah, there's no sound. So this is our benthic lander. Essentially, divers in this case are lowering it down to the seafloor in a blue hole. That's my advisor, Martial Taifer. And so they're going to lower it down, and there's a chamber on the bottom, as we'll see in a second. And when that chamber forms a contact, it basically closes water right on top of the sediments that then you can see the chamber here. It closes water on top, and then we program the collection of samples over time in order to understand how the sediments are releasing nutrients to the water column. And then that can affect things like cycles of algae that are important for trapping carbon dioxide in the ocean rather than the atmosphere. So I just wanted to briefly show some of the technologies. So the sediments are completely different than the ocean water column in terms of the physics and the chemistry. And so what you often see, and especially with the things that I study, nutrients increase. So here we have things like ammonium and phosphate, or inorganic carbon, so carbon dioxide and alkalinity. And then this would be like the water column. And this is as you get deeper in sediments, as you go down in this sediment core here. And you see a lot of things increase. And so that generates a pressure that drives those nutrients into the water column from the sediments. And as I showed previously, this is another benthic lander that we use, where essentially we get a time series of inorganic carbon and total alkalinity. And then you can regress that, or just look at the change over time and understand how the sediments are impacting the water column over time. But it's all really complicated equipment and complicated environments. I'm going to go through this really quickly, but this is a paper that I'm publishing, or it's getting ready to be sent out now. But this was another piece of technology where we were looking at something that's called non-steady state, where we're looking at resuspension of sediments and how that relates to, as you get these really pink bars, they start to increase in around April in the late spring. You get an influx of chlorophyll or algae in the water column. And so what we found is that the sediments in this Lake Okeechobee system, in Lake Okeechobee, as they're resuspended, they're maybe causing algal blooms that are really impactful on local ecotourism, and then also local fish populations, because a lot of times these algae can produce toxins. And then to highlight some other work done in my lab, this is is a paper that's in revision right now in marine chemistry. You have acidification, as I mentioned previously, with carbon dioxide, and that can impact things like coral or these other algae, and because they can no longer calcify their shell. And so some work that my lab mate is publishing right now shows how in the Gulf of Mexico, you get a lot of variability between the relationship of alkalinity and acidification, which basically suggests that sediments are dynamic. And we do a lot of work that kind of looks at how that relationship shifts on a local scale. And so, yes, if you have a lot of inorganic carbon without alkalinity, then you're going to have die-off. So I'll skip past this because the big point here that I wanted to make was that there's a lot of teams that go into this work, and these teams are funded by NSF. And it's a lot of good work that we've done, but it's really NSF because oftentimes we just acknowledge our funders and it's kind of a mandatory thing. Whereas I wanted to take this time to really thank them for putting together the teams that I've been able to work on. So thank you.
All right, great. Thank you so much for sharing, Owen. I really enjoyed seeing all the behind the scenes of like your science, and I think that is always really hard for people to be able to grasp, not knowing about how the work might look like on a day-to-day basis for a scientist. So it's really exciting to see. Someone wanted to know if the equipment that you used is used for both oceans and lakes or other settings.
Yeah, so the equipment we use is highly specialized, but it can be used for both oceans and lakes, although there's different engineering components that you need to take into consideration. For example, the ocean is highly saline, and so oftentimes we have to deal for stuff like corrosion, especially in the ocean, and then having to study the environments without oxygen because sediments are anoxic.
Okay. So I think we're out of time for your talk, but that was really great. Everyone, please say thank you to our speaker. And thank you so much, Owen, for me personally. So for everyone here, we're going to be resetting the live stream to a new link. So make sure to go to our website. I think we should put it in the chat. I'm not 100% sure. Oh, there we go. And so make sure to rejoin us at this new link. I'm just waiting a second to for everyone to transfer over to the new link.